Section 17 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 4B, Other Factors Considered, Part 2. Hypergolic fuel spill. Concerns that hypergolic, ignite spontaneously when mixed, fuel contamination might have contributed to the accident led the board to investigate an August 20, 1999 hydrazine spill at Kennedy Space Center that occurred while Columbia was being prepared for shipment to the Boeing facility in Palmdale, California. The spill occurred when a maintenance technician disconnected a hydrazine fuel line without capping it. When the fuel line was placed on a maintenance platform, 2.25 ounces of the volatile, corrosive fuel dripped onto the trailing edge of the orbiter's left inboard elevon. After the spill was cleaned up, 2 tiles were removed for inspection. No damage to the control surface skin or structure was found, and the tiles were replaced. United Space Alliance briefed all employees working with these systems on procedures to prevent another spill, and on November 1, 1999, the Shuttle Operations Advisory Group was briefed on the corrective action that had been taken. Finding F4.2-7. The hypergolic spill was not a factor in this accident. Recommendations: none. Space weather. Space weather refers to the action of highly energetic particles in the outer layer of the Earth's atmosphere. Eruptions of particles from the sun are the primary source of space weather events, which fluctuate daily or even more frequently. The most common space weather concern is a potentially harmful radiation dose to astronauts during a mission. Particles can also cause structural damage to a vehicle, harm electronic components, and adversely affect communication links. After the accident, several researchers contacted the board and NASA with concerns about unusual space weather just before Columbia started its re-entry. A coronal mass ejection, or solar flare, of high-energy particles from the outer layers of the sun's atmosphere occurred on January 31, 2003. The shock wave from the solar flare passed Earth at about the same time that the orbiter began its de-orbit burn. To examine the possible effects of this solar flare, the board enlisted the expertise of the Space Environmental Center of the National Oceanic and Atmospheric Administration and the Space Vehicles Directorate of the Air Force Research Laboratory at Hanscom Air Force Base in Massachusetts. Measurements from multiple space and ground-based systems indicate that the solar flare occurred near the edge of the sun, as observed from Earth, reducing the impact of the subsequent shock wave to a glancing blow. Most of the effects of the solar flare were not observed on Earth until 6 or more hours after Columbia broke up. See Appendix D5 for more on space weather effects. Finding F4.2-8. Space weather was not a factor in this accident. Recommendations: none. Asymmetric boundary layer transition. Columbia had recently been through a complete refurbishment, including detailed inspection and certification of all lower wing surface dimensions. Any grossly protruding gap fillers would have been observed and repaired. Indeed, though investigators found that Columbia's reputation for a rough left wing was well deserved prior to STS-75, quantitative measurements show that the measured wing roughness was below the fleet average by the launch of STS-107. Finding F4.2-9. A rough wing was not a factor in this accident. Recommendations: none. Training and on-orbit performance. All mission-specific training requirements for STS-107 launch and flight control operators were completed before launch with no performance problems. However, 7 flight controllers assigned to the mission did not have current recertifications at the time of the Flight Readiness Review, nor were they certified by the mission date. Most flight controllers must recertify for their positions every 18 months. The board has determined that this oversight had no bearing on mission performance. See Chapter 6. The launch control team and crew members held a full dress rehearsal of the launch day during the terminal countdown demonstration test. See Appendix D.1 for additional details on training for STS-107. Because the majority of the mission was completed before re-entry, an assessment of the training preparation and flight readiness of the crew, launch controllers, and flight controllers was based on the documented performance of mission duties. All STS-107 personnel performed satisfactorily during the launch countdown, launch, and mission. Crew and mission controller actions were consistent with re-entry procedures. There were a few incorrect switch movements by a crew during the mission, including the configuration of an intercommunications switch and an accidental bump of a rotational hand controller, which affected the orbiter's attitude, after the deorbit burn, but prior to entry interface. The intercommunications switch error was identified and then corrected by the crew. Both the crew and mission control noticed the bump and took the necessary steps to place the orbiter in the correct attitude. Neither of these events was a factor in the accident, nor are they considered training or performance issues. Details on STS-107 on-orbit operations are in Appendix D2. Finding: F4.2-10. The board concludes that training and on-orbit considerations were not factors in this accident. Recommendations: none. Payloads. To ensure that a payload malfunction did not cause or contribute to the Columbia accident, the board conducted a thorough examination of all payloads and their integration with the orbiter's systems. The board reviewed all downlinked payload telemetry data during the mission, as well as all payload hardware technical documentation. Investigators assessed every payload readiness review, safety review, and payload integration process used by NASA, and interviewed individuals involved in the payload process at both Johnson and Kennedy Space Centers. The board's review of the STS-107 Flight Readiness Review, Payload Readiness Review, Payload Safety Review Panel, and integrated safety assessments of experiment payloads on STS-107 found that all payload-associated hazards were adequately identified, accounted for, and appropriately mitigated. Payload integration engineers encountered no unique problems during Space HAB integration, there were no payload constraints on the launch, and there were no guideline violations during the payload preparation process. The board evaluated 11 payload anomalies, one of which was significant. A Space HAB water separator assembly leak under the aft subfloor caused an electrical short and subsequent shutdown of both water separator assemblies. Ground and flight crew responses sufficiently addressed these anomalies during the mission. Circuit protection and telemetry data further indicate that during re-entry, this leak could not have produced a similar electrical short in Space HAB that might have affected the main orbiter power supply. The board determined that the powered payloads aboard STS-107 were performing as expected when the orbiter's signal was lost. In addition, all potential fault tree payload failures that could have contributed to the orbiter breakup were evaluated using real-time downlinked telemetry, debris analysis, or design specification analysis. These analyses indicate that no such failures occurred. Several experiments within Space HAB were flammable, used flames, or involved combustible materials. All downlinked Space HAB telemetry was normal through re-entry, indicating no unexpected rise in temperature within the module and no increases in atmospheric or hull pressures. All fire alarms and indicators within Space HAB were operational, and they detected no smoke or fire. Gas percentages within Spacehab were also within limits. Because a major shift in the orbiter's center of gravity could potentially cause flight control or heat management problems, researchers investigated a possible shifting of equipment in the payload bay. Telemetry during re-entry indicated that all payload cooling loops, electrical wiring, and communications links were functioning as expected, supporting the conclusion that no payload came loose during re-entry. In addition, there are no indications from the orbiter's telemetry that any flight control adjustments were made to compensate for a change in the orbiter's center of gravity, which indicates that the center of gravity in the payload bay did not shift during re-entry. The board explored whether the pressurized Spacehab module may have ruptured during re-entry. A rupture could breach the fuselage of the orbiter or force open the payload bay doors, allowing hot gases to enter the orbiter. All downlinked payload telemetry indicates there was no decompression of Spacehab prior to loss of signal, and no dramatic increase in internal temperature or change in the air composition. This analysis suggests that the pressurized Spacehab module did not rupture during re-entry. See Appendix D6. Finding F4.2-11. The payloads Columbia carried were not a factor in this accident. Recommendations: none. Willful damage and security. During the board's investigation, suggestions of willful damage, including the possibility of a terrorist act or sabotage by a disgruntled employee, surfaced in the media and on various websites. The board assessed such theories, giving particular attention to the unprecedented security precautions taken during the launch of STS-107 because of prevailing national security concerns and the inclusion of an Israeli crew member. Speculation that Columbia was shot down by a missile was easily dismissed. The orbiter's altitude and speed prior to breakup was far beyond the reach of any air-to-air or surface-to-air missile, and telemetry and orbiter support system data demonstrate that events leading to the breakup began at even greater altitudes. The board's evaluation of whether sabotage played any role included several factors: security planning and countermeasures, personnel and facility security, maintenance and processing procedures, and debris analysis. To rule out an act of sabotage by an employee with access to these facilities, maintenance and processing procedures were thoroughly reviewed. The board also interviewed employees who had access to the orbiter. The processes in place to detect anything unusual on the orbiter, from a planted explosive to a bolt incorrectly torqued, made it likely that anything unusual would be caught during the many checks that employees perform as the orbiter nears final closeout, closing and sealing panels that have been left open for inspection prior to launch. In addition, the process of securing various panels before launch and taking closeout photos of hardware, see Figure 4.2-5, almost always requires the presence of more than one person, which means a saboteur would need the complicity of at least one other employee, if not more. Debris from Columbia was examined for traces of explosives that would indicate a bomb on board. Federal Bureau of Investigation laboratories provided analysis. Laboratory technicians took multiple samples of debris specimens and compared them with swabs from Atlantis and Discovery. Visual examination and gas chromatography with chemiluminescence detection found no explosive residues on any specimens that could not be traced to the shuttle's pyrotechnic devices. Additionally, telemetry and other data indicate these pyrotechnic devices operated normally. In its review of willful damage scenarios mentioned in the press or submitted to the investigation, the board could not find any that were plausible. Most demonstrated a basic lack of knowledge of shuttle processing and the physics of explosives, altitude, and thermodynamics, as well as the processes of maintenance documentation and employee screening. NASA and its contractors have a comprehensive security system, outlined in documents like NASA's Policy Directive 1600.2a. Rules, procedures, and guidelines address topics ranging from foreign travel to information security, from security education to investigations, and from the use of force to security for public tours. The board examined security at NASA and its related facilities through a combination of employee interviews, site visits, briefing reviews, and discussions with security personnel. The board focused primarily on reviewing the capability of unauthorized access to shuttle system components. Facilities and programs examined for security and sabotage potential included ATK Thiokol in Utah and its reusable solid rocket motor production, the Michaud Assembly Facility in Louisiana and its external tank production, and the Kennedy Space Center in Florida for its orbiter and overall integration responsibilities. The board visited the Boeing facility in Palmdale, California, Edwards Air Force Base in California, Stennis Space Center in Bay St. Louis, Mississippi, Marshall Space Flight Center near Huntsville, Alabama, and Cape Canaveral Air Force Station in Florida. These facilities exhibited a variety of security processes, according to each site's unique demands. At Kennedy, access to secure areas requires a series of identification card exchanges that electronically record each entry. The Michaud Assembly Facility employs similar measures, with additional security limiting access to a completed external tank. The use of closed-circuit television systems, complemented by security patrols, is universal. Employee screening and tracking measures appear solid across NASA and at the contractors examined by the board. The agency relies on standard background and law enforcement checks to prevent the hiring of applicants with questionable records, and the dismissal of those who may accrue such a record. It is difficult for anyone to access critical shuttle hardware alone or unobserved by a responsible NASA or contractor employee. With the exception of two processes when foam is applied to the external tank at the Michaud Assembly Facility, there are no known final closeouts of any shuttle component that can be completed with fewer than 2 people. Most closeouts involve at least 5 to 8 employees before the component is sealed and certified for flight. All payloads also undergo an extensive review to ensure proper processing and to verify that they pose no danger to the crew or the orbiter. Security reviews also occur at locations such as the transoceanic abort landing facilities. These sites are assessed prior to launch, and appropriate measures are taken to guarantee they are secure in case an emergency landing is required. NASA also has contingency plans in place, including dealing with bioterrorism. Both daily and launch day security at the Kennedy Space Center has been tightened in recent years. Each shuttle launch has an extensive security countdown, with a variety of checks to guarantee that signs are posted, beaches are closed, and patrols are deployed. Canine patrols and helicopters guard the launch area against intrusion. Because the STS-107 manifest included Israel's first astronaut, security measures, developed with National Security Council approval, went beyond the normally stringent precautions, including the development of a security support plan. Military aircraft patrolled a 40-mile Federal Aviation Administration restricted area starting 9 hours before the launch of STS-107. 8 Coast Guard vessels patrolled a 3 nautical mile security zone around Kennedy Space Center and Cape Canaveral Air Force Station, and Coast Guard and NASA boats patrolled the inland waterways. Security forces were doubled on the day of the launch. Findings: F4.2-12. The board found no evidence that willful damage was a factor in this accident. F4.2-13. 2 closeout processes at the Michaud Assembly Facility are currently able to be performed by a single person. F4.2-14, photographs of every closeout activity are not routinely taken. Recommendation: R4.2-3. Require that at least 2 employees attend all final closeouts and intertank area handspraying procedures. Micrometeoroids and orbital debris risks. Micrometeoroids and space debris, often called space junk, are among the most serious risk factors in shuttle missions. While there is little evidence that micrometeoroids or space debris caused the loss of Columbia, and in fact a review of onboard accelerometer data rules out a major strike, micrometeoroids or space debris cannot be entirely ruled out as a potential or contributing factor. Micrometeoroids, each usually no larger than a grain of sand, are numerous and particularly dangerous to orbiting spacecraft. Traveling at velocities that can exceed 20,000 miles per hour, they can easily penetrate the orbiter's skin. In contrast to micrometeoroids, orbital debris generally comes from destroyed satellites, payload remnants, exhaust from solid rockets, and other man-made objects, and typically travel at far lower velocities. Pieces of debris 4 inches or larger are cataloged and tracked by the U.S. Air Force Space Command, so they can be avoided during flight. NASA has developed computer models to predict the risk of impacts. The Orbital Debris Model 2000, or DEM 2000, database is used to predict the probability of a micrometeoroid or space debris collision with an orbiter based on its flight trajectory, altitude, date, and duration. Development of the database was based on radar tracking of debris and satellite experiments, as well as inspections of returned orbiters. The computer code bumper translates expected debris hits from ORDEM 2000 into an overall risk probability for each flight. The worst-case scenario during orbital debris strikes is known as the critical penetration risk, which can include the depressurization of the crew module, venting or explosion of pressurized systems, breaching of the thermal protection system, and damage to control surfaces. NASA guidelines require the critical penetration risk to be better than 1 in 200, a number that has been the subject of several reviews. NASA has made changes to reduce the probability. For STS-107, the estimated risk was 1 in 370, though the actual as-flown value turned out to be 1 in 356. The current risk guideline of 1 in 200 makes space debris or micrometeoroid strikes by far the greatest risk factor in the probabilistic risk assessment used for missions. Although 1 in 200 flights may seem to be long odds, and many flights have exceeded the guideline, the cumulative risk for such a strike over the 113 flight history of the Space Shuttle program is calculated to be 1 in 3. The board considers this probability of a critical penetration to be unacceptably high. The space station's micrometeoroid and space debris protection system reduces its critical penetration risk to 5% or less over 10 years, which translates into a per-mission risk of 1 in 1,200 with 6 flights per year or 60 flights over 10 years. To improve crew and vehicle safety over the next 10 to 20 years, the board believes risk guidelines need to be changed to compel the shuttle program to identify and, more to the point, reduce the micrometeoroid and orbital debris threat to missions. Findings: F4.2-15. There is little evidence that Columbia encountered either micrometeoroids or orbital debris on this flight. F4.2-16. The board found markedly different criteria for margins of micrometeoroid and orbital debris safety between the International Space Station and the shuttle. Recommendation: R4.2-4. Require the space shuttle to be operated with the same degree of safety for micrometeoroid and orbital debris as the degree of safety calculated for the International Space Station. Change the micrometeoroid and orbital debris safety criteria from guidelines to requirements. Orbiter Major Modification. The board investigated concerns that mistakes, mishaps, or human error during Columbia's last orbiter major modification might have contributed to the accident. Orbiters are removed from service for inspection, maintenance, and modification approximately every 8 flights, or 3 years. Columbia began its last orbiter major modification in September 1999, completed it in February 2001, and had flown once before STS-107. Several aspects of the orbiter major modification process trouble the board and need to be addressed for future flights. These concerns are discussed in Chapter 10. Findings F4.2-17. Based on a thorough investigation of maintenance records and interviews with maintenance personnel, the board found no errors during Columbia's most recent orbiter major modification that contributed to the accident. Recommendations: none. Foreign object damage prevention. Problems with the Kennedy Space Center and United Space Alliance Foreign Object Damage Prevention Program, which in the Department of Defense and aviation industry typically falls under the auspices of quality assurance, are related to changes made in 2001. In that year, Kennedy and Alliance redefined the single term foreign object damage, an industry standard blanket term, into 2 terms, processing debris and foreign object debris. Processing debris then became, quote, any material, product, substance, tool, or aid generally used during the processing of flight hardware that remains in the work area when not directly in use, or that is left unattended in the work area for any length of time during the processing of tasks, or that is left remaining or forgotten in the work area after the completion of a task or at the end of a work shift. Also, any item, material, or substance in the work area that should be found and removed as part of standard housekeeping, hazard recognition and inspection program, HRIP, walkdowns, or as part of clean-as-you-go practices, end quote. Foreign object debris then became, quote, processing debris becomes FOD when it poses a potential risk to the shuttle or any of its components, and only occurs when the debris is found during or subsequent to a final flight closeout inspection or subsequent to OMI S0007 ET load SAF FAC walkdown, end quote. These definitions are inconsistent with those of other NASA centers, naval reactor programs, the Department of Defense, commercial aviation, and National Aerospace FOD Prevention Incorporation guidelines. They are unique to Kennedy Space Center and United Space Alliance. Because debris of any kind has critical safety implications, these definitions are important. The United Space Alliance Foreign Object Program includes daily debris checks by management to ensure that workers comply with United Space Alliance's clean-as-you-go policy, but United Space Alliance statistics reveal the success rate of daily debris checks is between 70 and 86%. The perception among many interviewees is that these novel definitions mitigate the impact of Kennedy Mission Assurance found foreign object debris on the United Space Alliance award fee. This is because processing debris statistics do not directly affect the award fee. Simply put, in splitting foreign object damage into 2 categories, many of the violations are tolerated. Indeed, with 18 problem reports generated on lost items during the processing of STS-107 alone, the need for an ongoing, thorough, and stringent foreign object debris program is indisputable. However, with 2 definitions of foreign objects, processing debris and foreign object debris, the former is portrayed as less significant and dangerous than the latter. The assumption that all debris will be found before flight fails to underscore the destructive potential of foreign object debris and creates an incentive to simply accept processing debris. Finding F 4.2-18. Since 2001, Kennedy Space Center has used a non-standard approach to define foreign object debris. The industry standard term, foreign object damage, has been divided into two categories, one of which is more permissive. Recommendation R 4.2-5. Kennedy Space Center Quality Assurance and United Space Alliance must return to the straightforward industry standard definition of foreign object debris and eliminate any alternate or statistically deceptive definitions like processing debris. End of section 17.
Section 18 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Part 2. Why the Accident Occurred. Chapter 5A, From Challenger to Columbia, Part 1. Many accident investigations did not go far enough. They identify the technical cause of the accident, and then connect it to a variant of operator error, the line worker who forgot to insert the bolt, the engineer who miscalculated the stress, or the manager who made the wrong decision. But this is seldom the entire issue. When the determinations of the causal chain are limited to the technical flaw and the individual failure, typically the actions taken to prevent a similar event in the future are also limited. Fix the technical problem or replace or retrain the individual responsible. Putting these corrections in place leads to another mistake, the belief that the problem is solved. The board did not want to make these errors. Attempting to manage high-risk technologies while minimizing failures is an extraordinary challenge. By their nature, these complex technologies are intricate, with many interrelated parts. Standing alone, the components may be well understood and have failure modes that can be anticipated. Yet when these components are integrated into a larger system, unanticipated interactions can occur that lead to catastrophic outcomes. The risk of these complex systems is increased when they are produced and operated by complex organizations that also break down in unanticipated ways. In our view, the NASA organizational culture had as much to do with this accident as the foam. Organizational culture refers to the basic values, norms, beliefs, and practices that characterize the functioning of an institution. At the most basic level, organizational culture defines the assumptions that employees make as they carry out their work. It is a powerful force that can persist through reorganizations and the change of key personnel. It can be a positive or a negative force. In a report dealing with nuclear wastes, the National Research Council quoted Alvin Weinberg's classic statement about the Faustian bargain that nuclear scientists made with society. The price that we demand of society for this magical energy source is both a vigilance and a longevity of our social institutions that we are quite unaccustomed to. This is also true of the space program. At NASA's urging, the nation committed to building an amazing, if compromised, vehicle called the Space Shuttle. When the agency did this, it accepted the bargain to operate and maintain the shuttle in the safest possible way. The board is not convinced that NASA has completely lived up to the bargain, or that Congress and the administration has provided the funding and support necessary for NASA to do so. This situation needs to be addressed. If the nation intends to keep conducting human space flight, it needs to live up to its part of the bargain. Part 2 of this report examines NASA's organizational, historical, and cultural factors, as well as how these factors contributed to the accident. As with Part 1, this part begins with history. Chapter 5 examines the post-Challenger history of NASA and its human spaceflight program. This includes reviewing the budget as well as organizational and management history, such as shifting management systems and locations. Chapter 6 documents management performance related to Columbia to establish events analyzed in later chapters. The chapter reviews the foam strikes, intense schedule pressure driven by an artificial requirement to deliver Node 2 to the International Space Station by a certain date, and NASA management's handling of concerns regarding Columbia during the STS-107 mission. In Chapter 7, the board presents its views of how high-risk activities should be managed and lists the characteristics of institutions that emphasize high-reliability results over economic efficiency or strict adherence to a schedule. This chapter measures the Space Shuttle program's organizational and management practices against these principles and finds them wanting. Chapter 7 defines the organizational cause and offers recommendations. Chapter 8 draws from the previous chapters on history, budgets, culture, organization, and safety practices, and analyzes how all these factors contributed to this accident. This chapter captures the board's views of the need to adjust management to enhance safety margins in shuttle operations, and reaffirms the board's position that without these changes, we have no confidence that other corrective actions will improve the safety of shuttle operations. The changes we recommend will be difficult to accomplish and will be internally resisted. From Challenger to Columbia. The board is convinced that the factors that led to the Columbia accident go well beyond the physical mechanisms discussed in Chapter 3. The causal roots of the accident can be traced in part to the turbulent post-Cold War policy environment in which NASA functioned during most of the years between the destruction of Challenger and the loss of Columbia. The end of the Cold War in the late 1980s meant that the most important political underpinning of NASA's human spaceflight program, the U.S.-Soviet space competition, was lost, with no equally strong political objective to replace it. No longer able to justify its projects with the kind of urgency that the superpower struggle had provided, the agency could not obtain budget increases through the 1990s. Rather than adjust its ambitions to this new state of affairs, NASA continued to push an ambitious agenda of space science and exploration, including a costly space station program. If NASA wanted to carry out that agenda, its only recourse, given its budget allocation, was to become more efficient, accomplishing more at less cost. The search for cost reduction led top NASA leaders over the past decade to downsize the shuttle workforce, outsource various shuttle program responsibilities, including safety oversight, and consider eventual privatization of the Space Shuttle program. The program's budget was reduced by 40% in purchasing power over the past decade, and repeatedly raided to make up for space station cost overruns, even as the program maintained a launch schedule in which the shuttle, a developmental vehicle, was used in an operational mode. In addition, the uncertainty of top policymakers in the White House, Congress, and NASA as to how long the shuttle would fly before being replaced resulted in the delay of upgrades needed to make the shuttle safer and to extend its service life. The Space Shuttle program has been transformed since the late 1980s implementation of post-Challenger management changes in ways that raise questions addressed here and in later chapters of Part 2 about NASA's ability to safely operate the Space Shuttle. While it would be inaccurate to say that NASA managed the Space Shuttle program at the time of the Columbia accident in the same manner it did prior to Challenger, there are unfortunate similarities between the agency's performance and safety practices in both periods. 5.1. The Challenger accident and its aftermath. The inherently vulnerable design of the Space Shuttle, described in Chapter 1, was a product of policy and technological compromises made at the time of its approval in 1972. That approval process also produced unreasonable expectations, even myths, about the shuttle's future performance, that NASA tried futilely to fulfill as the shuttle became operational in 1982. At first, NASA was able to maintain the image of the shuttle as an operational vehicle. During its early years of operation, the shuttle launched satellites, performed on-orbit research, and even took members of Congress into orbit. At the beginning of 1986, the goal of routine access to space, established by President Ronald Reagan in 1982, was ostensibly being achieved. That appearance soon proved illusory. On the cold morning of January 28, 1986, the shuttle Challenger broke apart 73 seconds into its climb towards orbit. On board were Francis R. Scobie, Michael J. Smith, Ellison S. Onizuka, Judith A. Resnick, Ronald E. McNair, Sharon Christa McAuliffe, and Gregory B. Jarvis. All perished. Rogers Commission. On February 3, 1986, President Reagan created the Presidential Commission on the Space Shuttle Challenger accident, which soon became known as the Rogers Commission, after its chairman, former Secretary of State William Rogers. The Commission's report, issued on June 6, 1986, concluded that the loss of Challenger was caused by the failure of the joint and seal between the two lower segments of the right solid rocket booster. Hot gases blew past a rubber O-ring in the joint, leading to a structural failure and the explosive burning of the shuttle's hydrogen fuel. While the Rogers Commission identified the failure of the solid rocket booster joint and seal as the physical cause of the accident, it also noted a number of NASA management failures that contributed to the catastrophe. The Rogers Commission concluded the decision to launch the Challenger was flawed. Communication failures, incomplete and misleading information, and poor management judgments all figured in a decision-making process that permitted, in the words of the Commission, internal flight safety problems to bypass key shuttle managers. As a result, if those making the launch decision had known all the facts, it is highly unlikely that they would have decided to launch. Far from meticulously guarding against potential problems, the Commission found that NASA had required a contractor to prove that it was not safe to launch, rather than proving that it was safe. The Commission also found that NASA had missed warning signs of the impending accident. When the joint began behaving in unexpected ways, neither NASA nor the solid rocket motor manufacturer Morton Thiokol adequately tested the joint to determine the source of these deviations from specifications or developed a solution to them, even though the problems frequently recurred. Nor did they respond to internal warnings about the faulty seal. Instead, Morton Thiokol and NASA management came to see the problems as an acceptable flight risk, a violation of a design requirement that could be tolerated. During this period of increasing uncertainty about the joint's performance, the Commission found that NASA's safety system had been silent. Of the management, organizational, and communication failures that contributed to the accident, 4 related to faults within the safety system, including a lack of problem reporting requirements, inadequate trend analysis, misrepresentation of criticality, and lack of involvement in critical discussions. The checks and balances the safety system was meant to provide were not working. Still another factor influenced the decisions that led to the accident. The Rogers Commission noted that the shuttle's increasing flight rate in the mid-1980s created a schedule pressure, including the compression of training schedules, a shortage of spare parts, and the focusing of resources on near-term problems. NASA managers may have forgotten, partly because of past success, partly because of their own well-nurtured image of the program, that the shuttle was still in a research and development phase. The Challenger accident had profound effects on the U.S. space program. On August 15, 1986, President Reagan announced that NASA will no longer be in the business of launching private satellites. The accident ended Air Force and intelligence community reliance on the shuttle to launch national security payloads, prompted the decision to abandon the yet-to-be-opened shuttle launch site at Vandenberg Air Force Base, and forced the development of improved expendable launch vehicles. A 1992 White House Advisory Committee concluded that the recovery from the Challenger disaster cost the country $12 billion, which included the cost of building the replacement orbiter Endeavour. It took NASA 32 months after the Challenger accident to redesign and requalify the solid rocket booster and to return the shuttle to flight. The first post-accident flight was launched on September 29, 1988. As the shuttle returned to flight, NASA Associate Administrator for Spaceflight, Richard Truly, commented, "We will always have to treat it, the shuttle, like an R&D test program, even many years into the future. I don't think calling it operational fooled anybody within the program. It was a signal to the public that shouldn't have been sent." Selected Rogers Commission recommendations. The faulty solid rocket motor joint and seal must be changed. This could be a new design eliminating the joint, or a redesign of the current joint and seal. No design options should be prematurely precluded because of schedule, cost, or reliance on existing hardware. All solid rocket motor joints should satisfy the following. The joints should be fully understood, tested, and verified. The certification of the new design should include tests which duplicate the actual launch configuration as closely as possible, tests over the full range of operating conditions, including temperature. Full consideration should be given to conducting static firings of the exact flight configuration in a vertical attitude. The shuttle program structure should be reviewed. The project managers for the various elements of the shuttle program felt more accountable to their center management than to the shuttle program organization. NASA should encourage the transition of qualified astronauts into agency management positions. NASA should establish an Office of Safety, Reliability, and Quality Assurance to be headed by an associate administrator, reporting directly to the NASA administrator. It would have direct authority for safety, reliability, and quality assurance throughout the agency. The office should be assigned the workforce to ensure adequate oversight of its functions, and should be independent of other NASA functional and program responsibilities. NASA should establish an STS Safety Advisory Panel reporting to the STS Program Manager. The charter of this panel should include shuttle operational issues, launch commit criteria, flight rules, flight readiness, and risk management. The Commission found that Marshall Space Flight Center project managers, because of a tendency at Marshall to management isolation, failed to provide full and timely information bearing on the safety of Flight 51L, the Challenger mission, to other vital elements of shuttle program management. NASA should take energetic steps to eliminate this tendency at Marshall Space Flight Center, whether by changes of personnel, organization, indoctrination, or all three. The nation's reliance on the shuttle as its principal space launch capability created a relentless pressure on NASA to increase the flight rate. NASA must establish a flight rate that is consistent with its resources. The shuttle program after return to flight. After the Rogers Commission report was issued, NASA made many of the organizational changes the Commission recommended. The space agency moved management of the Space Shuttle program from the Johnson Space Center to NASA headquarters in Washington, D.C. The intent of this change was to create a management structure resembling that of the Apollo program, with the aim of preventing communication deficiencies that had contributed to the Challenger accident. NASA also established an Office of Safety, Reliability, and Quality Assurance at its headquarters, although that office was not given the direct authority over all of NASA's safety operations as the Rogers Commission had recommended. Rather, NASA human spaceflight centers each retained their own safety organization, reporting to the center director. In the almost 15 years between the return to flight and the loss of Columbia, the shuttle was again being used on a regular basis to conduct space-based research, and in line with NASA's original 1969 vision to build and service a space station. The shuttle flew 87 missions during this period, compared to 24 before Challenger. Highlights from these missions include the 1990 launch, 1993 repair, and 1999 and 2002 servicing of the Hubble Space Telescope, the launch of several major planetary probes, a number of Shuttle Space Lab missions devoted to scientific research, 9 missions to rendezvous with the Russian space station Mir, the return of former Mercury astronaut Senator John Glenn to orbit in October 1998, and the launch of the first U.S. elements of the International Space Station. After the Challenger accident, the shuttle was no longer described as operational in the same sense as commercial aircraft. Nevertheless, NASA continued planning as if the shuttle could be readied for launch at or near whatever date was set. Tying the shuttle closely to International Space Station needs, such as crew rotation, added to the urgency of maintaining a predictable launch schedule. The shuttle is currently the only means to launch the already built European, Japanese, and remaining U.S. modules needed to complete the station assembly, and to carry and return most experiments and on-orbit supplies. Even after 3 occasions when technical problems grounded the shuttle fleet for a month or more, NASA continued to assume that the shuttle could regularly and predictably service the station. In recent years, this coupling between the station and the shuttle has become the primary driver of the shuttle launch schedule. Whenever a shuttle launch is delayed, it impacts the station assembly and operations. In September 2001, testimony on the shuttle's achievements during the preceding decade by NASA's then Deputy Associate Administrator for Spaceflight, William Reddy, indicated the assumptions under which NASA was operating during that period. The Space Shuttle has made dramatic improvements in the capabilities, operations, and safety of the system. The payload-to-orbit performance of the Space Shuttle has been significantly improved, by over 70% to the space station. The safety of the Space Shuttle has also been dramatically improved by reducing risk by more than a factor of 5. In addition, the operability of the system has been significantly improved, with 5-minute launch windows, which would not have been attempted a decade ago, now becoming routine. This record of success is a testament to the quality and dedication of the Space Shuttle management team and workforce, both civil servants and contractors. 5.2. The NASA Human Spaceflight Culture. Though NASA underwent many management reforms in the wake of the Challenger accident and appointed new directors at the Johnson, Marshall, and Kennedy centers, the agency's powerful human spaceflight culture remained intact, as did many institutional practices, even if in a modified form. As a close observer of NASA's organizational culture has observed, cultural norms tend to be fairly resilient. The norms bounce back into shape after being stretched or bent. Beliefs held in common throughout the organization resist alteration. This culture, as will become clear across the chapters of Part 2 of this report, acted over time to resist externally imposed change. By the eve of the Columbia accident, institutional practices that were in effect at the time of the Challenger accident, such as inadequate concern over deviations from expected performance, a silent safety program, and schedule pressure, had returned to NASA. Note: Organizational culture. Organizational culture refers to the basic values, norms, beliefs, and practices that characterize the functioning of a particular institution. At the most basic level, organizational culture defines the assumptions that employees make as they carry out their work. It defines the way we do things here. An organization's culture is a powerful force that persists through reorganizations and the departure of key personnel. End note. The human spaceflight culture within NASA originated in the Cold War environment. The space agency itself was created in 1958 as a response to the Soviet launch of Sputnik, the first artificial Earth satellite. In 1961, President John F. Kennedy charged the new space agency with the task of reaching the moon before the end of the decade, and asked Congress and the American people to commit the immense resources for doing so, even though, at the time, NASA had only accumulated 15 minutes of human spaceflight experience. With its efforts linked to the U.S.-Soviet competition for global leadership, there was a sense in the NASA workforce that the agency was engaged in a historic struggle central to the nation's agenda. The Apollo era created at NASA an exceptional can-do culture, marked by tenacity in the face of seemingly impossible challenges. This culture valued the interaction among research and testing, hands-on engineering experience, and a dependence on the exceptional quality of its workforce and leadership that provided in-house technical capability to oversee the work of contractors. The culture also accepted risk and failure as inevitable aspects of operating in space, even as it held as its highest value attention to detail in order to lower the chances of failure. The dramatic Apollo 11 lunar landing in July 1969 fixed NASA's achievements in the national consciousness and in history. However, the numerous accolades in the wake of the moon landing also helped reinforce the NASA staff's faith in their organizational culture. Apollo successes created the powerful image of the space agency as a perfect place, as the best organization that human beings could create to accomplish selected goals. During Apollo, NASA was in many respects a highly successful organization, capable of achieving seemingly impossible feats. The continuing image of NASA as a perfect place in the years after Apollo left NASA employees unable to recognize that NASA never had been and still was not perfect, nor was it as symbolically important in the continuing Cold War struggle as it had been for the first decade of its existence. NASA personnel maintained a vision of their agency that was rooted in the glories of an earlier time, even as the world, and thus the context within which the space agency operated, changed around them. As a result, NASA's human spaceflight culture never fully adapted to the Space Shuttle program, with its goal of routine access to space, rather than further exploration beyond low Earth orbit. The Apollo-era organizational culture came to be in tension with the more bureaucratic space agency of the 1970s, whose focus had turned from designing new spacecraft at any expense to repetitively flying a reusable vehicle on an ever-tightening budget. This trend toward bureaucracy and the associated increased reliance on contracting necessitated more effective communications and more extensive safety oversight processes than had been in place during the Apollo era. But the Rogers Commission found that such features were lacking. In the aftermath of the Challenger accident, these contradictory forces prompted a resistance to externally imposed changes and an attempt to maintain the internal belief that NASA was still a perfect place, alone in its ability to execute a program of human spaceflight. Within NASA centers, as human spaceflight program managers strove to maintain their view of the organization, they lost their ability to accept criticism, leading them to reject the recommendations of many boards and blue ribbon panels, the Rogers Commission among them. External criticism and doubt, rather than spurring NASA to change for the better, instead reinforced the will to impose the party-line vision on the environment, not to reconsider it, according to one authority on organizational behavior. This in turn led to flawed decision-making, self-deception, introversion, and a diminished curiosity about the world outside the perfect place. The NASA human spaceflight culture the board found during its investigation manifested many of these characteristics, In particular, a self-confidence about NASA possessing unique knowledge about how to safely launch people into space. As will be discussed later in this chapter, as well as in chapters 6, 7, and 8, the board views this cultural resistance as a fundamental impediment to NASA's effective organizational performance. What the experts have said. Warnings of a shuttle accident. Shuttle reliability is uncertain, but has been estimated to range between 97 and 99%. If the shuttle reliability is 98%, there would be a 50-50 chance of losing an orbiter within 34 flights. The probability of maintaining at least 3 orbiters in the shuttle fleet declines to less than 50% after Flight 113. The Office of Technology Assessment, 1989. And although it is a subject that meets with reluctance to open discussion and has therefore too often been relegated to silence, the statistical evidence indicates that we are likely to lose another space shuttle in the next several years, probably before the planned space station is completely established on orbit. This would seem to be the weak link in the civil space program, unpleasant to recognize, involving all the uncertainties of statistics and difficult to resolve. The Augustine Committee, 1990. Shuttle as a developmental vehicle. Shuttle is also a complex system that has yet to demonstrate an ability to adhere to a fixed schedule. The Augustine Committee, 1990. NASA human spaceflight culture. NASA has not been sufficiently responsive to valid criticism and to the need for change. The Augustine Committee, 1990. 5.3. An agency trying to do too much with too little. A strong indicator of the priority the national political leadership assigns to a federally funded activity is its budget. By that criterion, NASA's space activities have not been high on the list of national priorities over the past 3 decades. See Figure 5.3-1. After a peak during the Apollo program, when NASA's budget was almost 4% of the federal budget, NASA's budget since the early 1970s has hovered at 1% of federal spending or less. Particularly in recent years, as the national leadership has confronted the challenging task of allocating scarce public resources across many competing demands, NASA has had difficulty obtaining a budget allocation adequate to its continuing ambitions. In 1990, the White House chartered a Blue Ribbon Committee chaired by aerospace executive Norman Augustine to conduct a sweeping review of NASA and its programs in response to shuttle problems and the flawed mirror on the Hubble Space Telescope. The review found that NASA's budget was inadequate for all the programs the agency was executing, saying that NASA is currently overcommitted in terms of program obligations relative to resources available. In short, it is trying to do too much and allowing too little margin for the unexpected. A reinvigorated space program, the Augustine Committee went on to say, will require real growth in the NASA budget of approximately 10% per year through the year 2000, reaching a peak spending level of about $30 billion per year in constant 1990 dollars by about the year 2000. Translated into the actual dollars of fiscal year 2000, that recommendation would have meant a NASA budget of over $40 billion. The actual NASA budget for that year was $13.6 billion. During the past decade, neither the White House nor Congress has been interested in a reinvigorated space program. Instead, the goal has been a program that would continue to produce valuable scientific and symbolic payoffs for the nation without the need for increased budgets. Recent budget allocations reflect this continuing policy reality. Between 1993 and 2002, the government's discretionary spending grew in purchasing power by more than 25%, defense spending by 15%, and non-defense spending by 40%. See Figure 5.3-2. NASA's budget, in comparison, showed little change, going from $14.31 billion in fiscal year 1993 to a low of $13.6 billion in fiscal year 2000, and increasing to $14.87 billion in fiscal year 2002. This represented a loss of 13% in purchasing power over the decade. See Figure 5.3-3. The lack of top-level interest in the space program led a 2002 review of the U.S. aerospace sector to observe that a sense of lethargy has affected the space industry and community. Instead of the excitement and exuberance that dominated our early ventures into space, we at times seem almost apologetic about our continued investments in the space program. Faced with this budget situation, NASA had the choice of either eliminating major programs or achieving greater efficiencies while maintaining its existing agenda. Agency leaders chose to attempt the latter. They continued to develop the space station, continued robotic planetary and scientific missions, and continued shuttle-based missions for both scientific and symbolic purposes. In 1994, they took on the responsibility for developing an advanced technology launch vehicle in partnership with the private sector. They tried to do this by becoming more efficient. Faster, better, cheaper became the NASA slogan of the 1990s. The flat budget at NASA particularly affected the human spaceflight enterprise. During the decade before the Columbia accident, NASA rebalanced the share of its budget allocated to human spaceflight from 48% of agency funding in fiscal year 1991 to 38% in fiscal year 1999, with the remainder going mainly to other science and technology efforts. On NASA's fixed budget, that meant the Space Shuttle and the International Space Station were competing for decreasing resources. In addition, at least $650 million of NASA's human spaceflight budget was used to purchase Russian hardware and services related to U.S.-Russian space cooperation. This initiative was largely driven by the Clinton administration's foreign policy and national security objectives of supporting the administration of Boris Yeltsin and halting the proliferation of nuclear weapons and the means to deliver them. Earmarks. Pressure on NASA's budget has come not only from the White House but also from Congress. In recent years, there has been an increasing tendency for the Congress to add earmarks, congressional additions to the NASA budget request that reflect targeted members' interests. These earmarks come out of already appropriated funds, reducing the amounts available for the original tasks. For example, as Congress considered NASA's fiscal year 2002 appropriation, the NASA administrator told the House Appropriations Subcommittee with jurisdiction over the NASA budget that the agency was extremely concerned regarding the magnitude and number of congressional earmarks in the House and Senate versions of the NASA Appropriations Bill. He noted the total number of House and Senate earmarks is approximately 140 separate items, an increase of nearly 50% over fiscal year 2001. These earmarks reflected an increasing fraction of items that circumvent the peer review process or involve construction or other activities that have no relation to NASA mission objectives. The potential fiscal year 2002 earmarks represented a net total of $540 million in reductions to ongoing NASA programs to fund this extremely large number of earmarks. Space Shuttle program budget patterns. For the past 30 years, the Space Shuttle program has been NASA's single most expensive activity, and of all NASA's efforts, that program has been the hardest hit by the budget constraints of the past decade. Given the high priority assigned after 1993 to completing the costly International Space Station, NASA managers have had little choice but to attempt to reduce the costs of operating the Space Shuttle. This left little funding for shuttle improvements. The squeeze on the shuttle budget was even more severe after the Office of Management and Budget in 1994 insisted that any cost overruns in the International Space Station budget be made up from within the budget allocation for human spaceflight, rather than from the agency's budget as a whole. The shuttle was the only other large program within that budget category. Figures 5.3-4 and 5.3-5 show the trajectory of the shuttle budget over the past decade. In fiscal year 1993, the outgoing Bush administration requested $4.128 billion for the Space Shuttle program. 5 years later, the Clinton administration request was for $2.977 billion, a 27% reduction. By fiscal year 2003, the budget request had increased to $3.208 billion, still a 22% reduction from a decade earlier. With inflation taken into account, over the past decade, there has been a reduction of approximately 40% in the purchasing power of the program's budget, compared to a reduction of 13% in the NASA budget overall. This budget squeeze also came at a time when the Space Shuttle program exhibited a trait common to most aging systems: increased costs due to greater maintenance requirements, a declining second- and third-tier contractor support base, and deteriorating infrastructure. Maintaining the shuttle was becoming more expensive at a time when shuttle budgets were decreasing or being held constant. Only in the last few years have those budgets begun a gradual increase. As Figure 5.3-5 indicates, most of the steep reductions in the shuttle budget date back to the first half of the 1990s. In the second half of the decade, the White House Office of Management and Budget and NASA headquarters held the shuttle budget relatively level by deferring substantial funding for shuttle upgrades and infrastructure improvements, while keeping pressure on NASA to limit increases in operating costs. End of Section 18. Recording by Maria Kasper. Section 19 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Part 2, Why the Accident Occurred, Chapter 5B, From Challenger to Columbia, Part 2. Congressional budget reductions. In most years, Congress appropriates slightly less for the Space Shuttle program than the President requested. In some cases, these reductions have been requested by NASA during the final stages of budget deliberations. After its budget was passed by Congress, NASA further reduced the shuttle budget in the agency's operating plan, the plan by which NASA actually allocates its appropriated budget during the fiscal year to react to changing program needs. These released funds were allocated to other activities, both within the human spaceflight program and in other parts of the agency. Changes in recent years include: fiscal year 1997, NASA transferred $190 million to the International Space Station, ISS. Fiscal year 1998, at NASA's request, Congress transferred $50 million to ISS. NASA transferred $15 million to ISS. Fiscal year 1999, at NASA's request, Congress reduced Shuttle $31 million so NASA could fund other requirements. NASA reduced Shuttle $32 million by deferring 2 flights, funds transferred to ISS. NASA added $2.3 million from ISS to previous NASA request. Fiscal year 2000, Congress added $25 million to Shuttle budget for upgrades and transferred $25 million from operations to upgrades. NASA reduced Shuttle $11.5 million per government-wide rescission requirement and transferred $15.3 million to ISS. Fiscal year 2001. At NASA's request, Congress reduced shuttle budget by $40 million to fund Mars Initiative. NASA reduced shuttle $6.9 million per rescission requirement. Fiscal year 2002. Congress reduced shuttle budget $50 million to reflect cancellation of Electric Auxiliary Power Unit and added $20 million for shuttle upgrades and $25 million for vehicle assembly building repairs. NASA transferred $7.6 million to fund headquarters requirements and cut $1.2 million per rescission requirement. 5.4. Turbulence in NASA hits the Space Shuttle program. In 1992, the White House replaced NASA Administrator Richard Truly with Aerospace Executive Daniel S. Golden, a self-proclaimed agent of change, who held office from April 1, 1992 to November 17, 2001, in the process becoming the longest-serving NASA administrator. Seeing space exploration, manned and unmanned, as NASA's principal purpose, with Mars as a destiny, as one management scholar observed, and favoring administrative transformation of NASA, Golden engineered not one or two policy changes, but a torrent of changes. This was not evolutionary change, but radical or discontinuous change. His tenure at NASA was one of continuous turmoil, to which the Space Shuttle program was not immune. Of course, turbulence does not necessarily degrade organizational performance. In some cases, it accompanies productive change, and that is what Golden hoped to achieve. He believed in the management approach advocated by W. Edwards Deming, who had developed a series of widely acclaimed management principles based on his work in Japan during the economic miracle of the 1980s. Golden attempted to apply some of those principles to NASA, including the notion that a corporate headquarters should not attempt to exert bureaucratic control over a complex organization, but rather set strategic directions and provide operating units with the authority and resources needed to pursue those directions. Another Deming principle was that checks and balances in an organization were unnecessary and sometimes counterproductive, and those carrying out the work should bear primary responsibility for its quality. It is arguable whether these business principles can readily be applied to a government agency operating under civil service rules and in a politicized environment. Nevertheless, Golden sought to implement them throughout his tenure. Golden made many positive changes in his decade at NASA. By bringing Russia into the space station partnership in 1993, Golden developed a new post-Cold War rationale for the agency, while managing to save a program that was politically faltering. The International Space Station became NASA's premier program, with the shuttle serving in a supporting role. Golden was also instrumental in gaining acceptance of the faster, better, cheaper approach to the planning of robotic missions and downsizing an agency that was considered bloated and bureaucratic when he took it over. Golden described himself as sharp-edged, and could often be blunt. He rejected the criticism that he was sacrificing safety in the name of efficiency. In 1994, he told an audience at the Jet Propulsion Laboratory, "When I ask for the budget to be cut, I'm told it's going to impact safety on the space shuttle. I think that's a bunch of crap." One of Golden's high-priority objectives was to decrease involvement of the NASA engineering workforce with the space shuttle program, and thereby free up those skills for finishing the space station and beginning work on his preferred objective, human exploration of Mars. Such a shift would return NASA to its exploratory mission. He was often at odds with those who continued to focus on the centrality of the shuttle to NASA's future. Initial shuttle workforce reductions. With NASA leadership choosing to maintain existing programs within a no-growth budget, Golden's faster, better, cheaper motto became the agency slogan of the 1990s. NASA leaders, however, had little maneuvering room in which to achieve efficiency gains. Attempts by NASA headquarters to shift functions or to close one of the 3 human spaceflight centers were met with strong resistance from the centers themselves, the aerospace firms they used as contractors, and the congressional delegations of the states in which the centers were located. This alliance resembles the classic iron triangle of bureaucratic politics: a conservative coalition of bureaucrats, interest groups, and congressional subcommittees working together to promote their common interests. With center infrastructure off limits, this left the Space Shuttle budget as the obvious target for cuts. Because the shuttle required a large standing army of workers to keep it flying, reducing the size of the shuttle workforce became the primary means by which top leaders lowered the shuttle's operating costs. These personnel reduction efforts started early in the decade and continued through most of the 1990s. They created substantial uncertainty and tension within the shuttle workforce, as well as the transitional difficulties inherent in any large-scale workforce reassignment. In early 1991, even before Golden assumed office and less than 3 years after the shuttle had been returned to flight after the Challenger accident, NASA announced a goal of saving 3 to 5% per year in the shuttle budget over 5 years. This move was in reaction to a perception that the agency had overreacted to the Rogers Commission recommendations. For example, the notion that the many layers of safety inspections involved in preparing a shuttle for flight had created a bloated and costly safety program. From 1991 to 1994, NASA was able to cut shuttle operating costs by 21%. Contractor personnel working on the shuttle declined from 28,394 to 22,387 in these 3 years, and NASA shuttle staff decreased from 4,031 to 2,959. Figure 5.4-1 shows the changes in Space Shuttle workforce over the past decade. A 1994 National Academy of Public Administration review found that these cuts were achieved primarily through operational and organizational efficiencies and consolidations, with resultant reductions in staffing levels and other actions which do not significantly impact basic program content or capabilities. NASA considered additional staff cuts in late 1994 and early 1995 as a way of further reducing the Space Shuttle program budget. In early 1995, as the national leadership focused its attention on balancing the federal budget, the projected 5-year shuttle budget requirements exceeded by $2.5 billion the budget that was likely to be approved by the White House Office of Management and Budget. Despite its already significant progress in reducing costs, NASA had to make further workforce cuts. Anticipating this impending need, a 1994-1995 NASA Functional Workforce Review concluded that removing an additional 5,900 people from the NASA and contractor shuttle workforce, just under 13% of the total, could be done without compromising safety. These personnel cuts were made in fiscal years 1996 and 1997. By the end of 1997, the NASA shuttle civilian workforce numbered 2,195, and the contractor workforce 17,281. Shifting shuttle management arrangements. Workforce reductions were not the only modifications to the shuttle program in the middle of the decade. In keeping with Golden's philosophy that headquarters should concern itself primarily with strategic issues, in February 1996, Johnson Space Center was designated as lead center for the Space Shuttle program, a role it held prior to the Challenger accident. This shift was part of a general move of all program management responsibilities from NASA headquarters to the agency's field centers. Among other things, this change meant that Johnson Space Center managers would have authority over the funding and management of shuttle activities at the Marshall and Kennedy centers. Johnson and Marshall had been rivals since the days of Apollo, and long-term Marshall employees and managers did not easily accept the return of Johnson to the lead role. The shift of the Space Shuttle program management to Johnson was worrisome to some. The head of the Space Shuttle program at NASA headquarters, Brian O'Connor, argued that transfer of the management function to the Johnson Space Center would return the shuttle program management to the flawed structure that had been in place before the Challenger accident. "It is a safety issue," he said. "We ran it that way, with program management at headquarters as recommended by the Rogers Commission, for 10 years without a mishap, and I didn't see any reason why we should go back to the way we operated in the pre-Challenger days." Golden gave O'Connor several opportunities to present his arguments against a transfer of management responsibility, but ultimately decided to proceed. O'Connor felt he had no choice but to resign. O'Connor returned to NASA in 2002 as Associate Administrator for Safety and Mission Assurance. In January 1996, Golden appointed as Johnson's director his close advisor George W.S. Abbey. Abbey, a space program veteran, was a firm believer in the values of the original human spaceflight culture, and as he assumed the directorship, he set about recreating as many of the positive features of that culture as possible. For example, he and Golden initiated, as a way for young engineers to get hands-on experience, an in-house X-38 development program as a prototype for a space station crew rescue vehicle. Abbey was a powerful leader who, through the rest of the decade, exerted substantial control over all aspects of Johnson Space Center operations, including the Space Shuttle program. Space Flight Operations Contract. By the middle of the decade, spurred on by Vice President Al Gore's Reinventing Government initiative, the goal of balancing the federal budget, and the views of a Republican-led House of Representatives, managers throughout the government sought new ways of making public sector programs more efficient and less costly. One method considered was transferring significant government operations and responsibilities to the private sector, or privatization. NASA led the way toward privatization, serving as an example to other government agencies. In keeping with his philosophy that NASA should focus on its research and development role, Golden wanted to remove NASA employees from the repetitive operations of various systems, including the Space Shuttle. Giving primary responsibility for Space Shuttle operations to the private sector was therefore consistent with White House and congressional priorities and attractive to Golden on its own terms. Beginning in 1994, NASA considered the feasibility of consolidating many of the numerous shuttle operations contracts under a single prime contractor. At that time, the Space Shuttle program was managing 86 separate contracts held by 56 different firms. Top NASA managers thought that consolidating these contracts could reduce the amount of redundant overhead, both for NASA and for the contractors themselves. They also wanted to explore whether there were functions being carried out by NASA that could be more effectively and inexpensively carried out by the private sector. An advisory committee, headed by early spaceflight veteran Christopher Kraft, recommended such a step in its March 1995 report, which became known as the Kraft Report. The report characterized the Space Shuttle in a way that the board judges to be at odds with the realities of the shuttle program. The report made the following findings and recommendations. The shuttle has become a mature and reliable system, about as safe as today's technology will provide. Given the maturity of the vehicle, a change to a new mode of management with considerably less NASA oversight is possible at this time. Many inefficiencies and difficulties in the current shuttle program can be attributed to the diffuse and fragmented NASA contractor structure. Numerous contractors exist supporting various program elements, resulting in ambiguous lines of communication and diffused responsibilities. NASA should consolidate operations under a single business entity. The program remains in a quasi-development mode, and yearly costs remain higher than required. NASA should freeze the current vehicle configuration, minimizing future modifications, with such modifications delivered in block updates. Future block updates should implement modifications required to make the vehicle more reusable and operational. NASA should restructure and reduce the overall safety, reliability, and quality assurance elements without reducing safety. When he released the committee's report, Kraft said that if NASA wants to make more substantive gains in terms of efficiency, cost savings, and better service to its customers, we think it's imperative they act on these recommendations, and we believe that these savings are real, achievable, and can be accomplished with no impact to the safe and successful operation of the shuttle system. Although the Kraft report stressed that the dramatic changes it recommended could be made without compromising safety, there was considerable dissent about this claim. NASA's Aerospace Safety Advisory Panel, independent but often not very influential, was particularly critical. In May 1995, the panel noted that the assumption in the Kraft report that the space shuttle systems are now mature smacks of a complacency which may lead to serious mishaps. The fact is that the space shuttle may never be mature enough to totally freeze the design. The panel also noted that the report dismisses the concerns of many credible sources by labeling honest reservations and the people who have made them as being partners in an unneeded safety shield conspiracy. Since only one more accident would kill the program and destroy far more than the spacecraft, it is extremely callous to make such an accusation. The notion that NASA would further reduce the number of civil servants working on the shuttle program prompted senior Kennedy Space Center engineer Jose Garcia to send to President Bill Clinton on August 25, 1995, a letter that stated, "The biggest threat to the safety of the crew since the Challenger disaster is presently underway at NASA." Garcia's particular concern was NASA's efforts to delete the checks and balances system of processing shuttles as a way of saving money. Historically, NASA has employed two engineering teams at KSC, one contractor and one government, to cross-check each other and prevent catastrophic errors. Although this technique is expensive, it is effective, and it is the single most important factor that sets the shuttle's success above that of any other launch vehicle. Anyone who doesn't have a hidden agenda or fear of losing his job would admit that you can't delete NASA's checks and balances system of shuttle processing without affecting the safety of the shuttle and its crew. NASA leaders accepted the advice of the Kraft report and in August 1995 solicited industry bids for the assignment of shuttle prime contractor. In response, Lockheed Martin and Rockwell, the two major space shuttle operations contractors, formed a limited liability corporation with each firm a 50% owner to compete for what was called the Spaceflight Operations Contract. The new corporation would be known as United Space Alliance. In November 1995, NASA awarded the operations contract to United Space Alliance on a sole source basis. When Boeing bought Rockwell's aerospace group in December 1996, it also took over Rockwell's 50% ownership of United Space Alliance. The company was responsible for 61% of the shuttle operations contracts. Some in Congress were skeptical that safety could be maintained under the new arrangement, which transferred significant NASA responsibilities to the private sector. Despite these concerns, Congress ultimately accepted the reasoning behind the contract. NASA then spent much of 1996 negotiating the contract's terms and conditions with United Space Alliance. The Spaceflight Operations Contract was designed to reward United Space Alliance for performance successes and penalize its performance failures. Before being eligible for any performance fees, United Space Alliance would have to meet a series of safety gates, which were intended to ensure that safety remained the top priority in shuttle operations. The contract also rewarded any cost reductions that United Space Alliance was able to achieve, with NASA taking 65% of any savings and United Space Alliance 35%. NASA and United Space Alliance formally signed the spaceflight operations contract on October 1, 1996. Initially, only the major Lockheed Martin and Rockwell shuttle contracts and a smaller Allied Signal Unisys contract were transferred to United Space Alliance. The initial contractual period was 6 years, from October 1996 to September 2002. NASA exercised an option for a 2-year extension in 2002, and another 2-year option exists. The total value of the contract through the current extension is estimated at $12.8 billion. United Space Alliance currently has approximately 10,000 employees. The contract provided for additional consolidation and then privatization, when all remaining shuttle operations would be transferred from NASA. Phase 2, scheduled for 1998 to 2000, called for the transfer of Johnson Space Center managed flight software and flight crew equipment contracts, and the Marshall Space Center managed contracts for the external tank, Space Shuttle main engine, reusable solid rocket motor, and solid rocket booster. However, Marshall and its contractors, with the concurrence of the Space Shuttle Program Office at Johnson Space Center, successfully resisted the transfer of its contracts. Therefore, the spaceflight operations contract's initial efficiency and integrated management goals have not been achieved. The major annual savings resulting from the spaceflight operations contract, which in 1996 were touted to be some $500 million to $1 billion per year by the early 2000s, have not materialized. These projections assumed that by 2002, NASA would have put all shuttle contracts under the auspices of United Space Alliance and would be moving toward shuttle privatization. Although the spaceflight operations contract has not been as successful in achieving cost efficiencies as its proponents hoped, it has reduced some shuttle operating costs and other expenses. By one estimate, in its first 6 years, the contract has saved NASA a total of more than $1 billion. Spaceflight Operations Contract. The Spaceflight Operations Contract has 2 major areas of innovation. It replaced the previous cost-plus contracts, in which a firm was paid for the costs of its activity plus a negotiated profit, with a complex contract structure that included performance-based and cost-reduction incentives. Performance measures include safety, launch readiness, on-time launch, solid rocket booster recovery, proper orbital insertion, and successful landing. It gave additional responsibilities for shuttle operation, including safety and other inspections and integration of the various elements of the shuttle system, to United Space Alliance. Many of these responsibilities were previously within the purview of NASA employees. Under the spaceflight operations contract, United Space Alliance had overall responsibility for processing selected shuttle hardware, including inspecting and modifying the orbiters, installing the Space Shuttle main engines on orbiters, assembling the sections that make up the solid rocket boosters, attaching the external tank to the solid rocket boosters, and then the orbiter to the external tank, recovering expended solid rocket boosters. In addition to processing shuttle hardware, United Space Alliance is responsible for mission design and planning, astronaut and flight controller training, design and integration of flight software, payload integration, flight operations, launch and recovery operations, vehicle sustaining engineering, flight crew equipment processing, and operation and maintenance of shuttle-specific facilities, such as the vehicle assembly building, the orbiter processing facility, and the launch pads. United Space Alliance also provides spare parts for the orbiters, maintains shuttle flight simulators, and provides tools and supplies, including consumables such as food, for the shuttle missions. Under the Spaceflight Operations Contract, NASA has the following responsibilities and roles: maintaining ownership of the shuttles and all other assets of the shuttle program, providing to United Space Alliance the Space Shuttle main engines, the external tanks, and the redesigned solid rocket motor segments for assembly into the solid rocket boosters, managing the overall process of ensuring shuttle safety, developing requirements for major upgrades to all assets, participating in the planning of shuttle missions, the directing of launches, and the execution of flights, performing surveillance and audits and obtaining technical insight into contractor activities, deciding if and when to commit to flight for each mission. Privatizing the Space Shuttle. To its proponents, the spaceflight operations contract was only a beginning. In October 1997, United Space Alliance submitted to the Space Shuttle Program Office a contractually required plan for privatizing the shuttle, which the program did not accept. But the notion of shuttle privatization lingered at NASA headquarters and in Congress, where some members advocated a greater private sector role in the space program. Congress passed the Commercial Space Act of 1998, which directed the NASA administrator to plan for the eventual privatization of the Space Shuttle program. By August 2001, NASA headquarters prepared for White House consideration a privatization white paper that called for transferring all shuttle hardware, pilot and commander astronauts, and launch and operations teams to a private operator. In September 2001, Space Shuttle Program Manager Ron Ditmore released his report on a concept of privatization of the Space Shuttle program, which argued that for the Space Shuttle to remain safe and viable, it is necessary to merge the required NASA and contractor skill bases into a single private organization that would manage human spaceflight. This perspective reflected Ditmore's belief that the split of responsibilities between NASA and United Space Alliance was not optimal, and that it was unlikely that NASA would ever recapture the shuttle responsibilities that had been transferred in the spaceflight operations contract. Ditmore's plan recommended transferring 700 to 900 NASA employees to the private organization, including astronauts, including the flight crew members who operate the shuttle, program and project management, including Space Shuttle main engine, external tank, redesigned solid rocket booster, and extravehicular activity, mission operations, including flight directors and flight controllers, ground operations and processing, including launch director, process engineering, and flow management, and responsibility for safety and mission assurance. After such a shift occurred, according to the Ditmore plan, the primary role for NASA in space shuttle operations will be to provide an SMA, Safety and Mission Assurance, independent assessment, utilizing audit and surveillance techniques. With a change in NASA administrators at the end of 2001 and the new Bush administration's emphasis on competitive sourcing of government operations, the notion of wholesale privatization of the space shuttle was replaced with an examination of the feasibility of both public and private sector program management. This competitive sourcing was under examination at the time of the Columbia accident. Workforce transformation and the end of downsizing. Workforce reductions instituted by Administrator Golden as he attempted to redefine the agency's mission and its overall organization also added to the turbulence of his reign. In the 1990s, the overall NASA workforce was reduced by 25% through normal attrition, early retirements and buyouts, cash bonuses for leaving NASA employment. NASA operated under a hiring freeze for most of the decade, making it difficult to bring in new and younger people. Figure 5.4-2 shows the downsizing of the overall NASA workforce during this period, as well as the associated shrinkage in NASA's technical workforce. NASA headquarters was particularly affected by workforce reductions. More than half its employees left or were transferred in parallel with the 1996 transfer of program management responsibilities back to the NASA centers. The Space Shuttle program bore more than its share of headquarters personnel cuts. Headquarters civil service staff working on the Space Shuttle program went from 120 in 1993 to 12 in 2003. While the overall workforce at the NASA centers involved in human spaceflight was not radically reduced, the combination of the general workforce reduction and the introduction of the Spaceflight Operations Contract significantly impacted the center's Space Shuttle Program civil service staff. Johnson Space Center went from 1,330 in 1993 to 738 in 2002. Marshall Space Flight Center from 874 to 337, and Kennedy Space Center from 1,373 to 615. Kennedy Director Roy Bridges argued that personnel cuts were too deep and threatened to resign unless the downsizing of his civil service workforce, particularly of those involved with safety issues, was reversed. By the end of the decade, NASA realized that staff reductions had gone too far. By early 2000, internal and external studies convinced NASA leaders that the workforce needed to be revitalized. These studies noted that 5 years of buyouts and downsizing have led to serious skill imbalances and an overtaxed core workforce. As more employees have departed, the workload and stress on those remaining have increased, with a corresponding increase in the potential for impact to operational capacity and safety. NASA announced that NASA workforce downsizing would stop short of the 17,500 target, and that its human spaceflight centers would immediately hire several hundred workers. End of Section 19. Recording by Maria Kasper. Section 20 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Part 2, Why the Accident Occurred, Chapter 5C, From Challenger to Columbia, Part 3. 5.5. When to replace the Space Shuttle. In addition to budget pressures, workforce reductions, management changes, and the transfer of government functions to the private sector, the Space Shuttle program was beset during the past decade by uncertainty about when the shuttle might be replaced. National policy has vacillated between treating the shuttle as a going-out-of-business program and anticipating 2 or more decades of shuttle use. As a result, limited and inconsistent investments have been made in shuttle upgrades and in revitalizing the infrastructure to support the continued use of the shuttle. Even before the 1986 Challenger accident, when and how to replace the Space Shuttle with a second-generation reusable launch vehicle was a topic of discussion among space policy leaders. In January 1986, the congressionally chartered National Commission on Space expressed the need for a shuttle replacement, suggesting that the shuttle fleet will become obsolescent by the turn of the century. Shortly after the Challenger accident, but not as a reaction to it, President Reagan announced his approval of the new Orient Express, Figure 5.5-1. This reusable launch vehicle, later known as the National Aerospace Plane, could, by the end of the decade, take off from Dulles Airport, accelerate up to 25 times the speed of sound, attaining low Earth orbit, or fly to Tokyo within 2 hours. This goal proved too ambitious, particularly without substantial funding. In 1992, after a $1.7 billion government investment, the National Aerospace Plane project was canceled. This pattern, optimistic pronouncements about a revolutionary shuttle replacement, followed by insufficient government investment and then program cancellation due to technical difficulties, was repeated again in the 1990s. In 1994, NASA listed alternatives for access to space through 2030. Upgrade the Space Shuttle to enable flights through 2030. Develop a new expendable launcher. Replace the Space Shuttle with a leapfrog next-generation advanced technology system that would achieve order-of-magnitude improvements in the cost-effectiveness of space transportation. Reflecting its leadership's preference for bold initiatives, NASA chose the third alternative. With White House support, NASA began the X-33 project in 1996 as a joint effort with Lockheed Martin. NASA also initiated the less ambitious X-34 project with Orbital Sciences Corporation. At the time, the future of commercial space launches was bright, and political sentiment in the White House and Congress encouraged an increasing reliance on private sector solutions for limiting government expenditures. In this context, these unprecedented joint projects appeared less risky than they actually were. The hope was that NASA could replace the shuttle through private investments without significant government spending. Both the X-33 and X-34 incorporated new technologies. The X-33 was to demonstrate the feasibility of an aerospike engine, new thermal protection systems, and composite rather than metal propellant tanks. These radically new technologies were in turn to become the basis for a new orbital vehicle called VentureStar that could replace the Space Shuttle by 2006. See Figure 5.5-2. The X-33 and X-34 ran into technical problems and never flew. In 2001, after spending $1.3 billion, NASA abandoned both projects. In all three projects, National Aerospace Plane, X-33, and X-34, national leaders had set ambitious goals in response to NASA's ambitious proposals. These programs relied on the invention of revolutionary technology, had run into major technical problems, and had been denied the funds needed to overcome these problems, assuming they could be solved. NASA had spent nearly 15 years and several $billion, and yet had made no meaningful progress toward a space shuttle replacement. In 2000, as the agency ran into increasing problems with the X-33, NASA initiated the Space Launch Initiative, a $4.5 billion multi-year effort to develop new space launch technologies. By 2002, after spending nearly $800 million, NASA again changed course. The Space Launch Initiative failed to find technologies that could revolutionize space launch, forcing NASA to shift its focus to an orbital space plane developed with existing technology that would complement the shuttle by carrying crew, but not cargo, to and from orbit. Under a new integrated space transportation plan, the shuttle might continue to fly until 2020 or beyond. See Section 5.6 for a discussion of this plan. As a result of the haphazard policy process that created these stillborn developmental programs, the uncertainty over shuttle replacement persisted. Between 1986 and 2002, the planned replacement date for the Space Shuttle was consistent only in its inconsistency. It changed from 2002 to 2006 to 2012, and before the Columbia accident to 2020 or later. Safety concerns and upgrading the Space Shuttle. This shifting date for shuttle replacement has severely complicated decisions on how to invest in shuttle program upgrades. More often than not, investment in upgrades were delayed or deferred on the assumption that they would be a waste of money if the shuttle were to be retired in the near future. See Figure 5.5-3. In 1995, for instance, the Kraft Report embraced the principle that NASA should freeze the design of the shuttle and defer upgrades due to the vehicle's mature status and the need for NASA to concentrate scarce resources on developing potential replacements for the shuttle. NASA subsequently halted a number of planned upgrades, only to reverse course a year later to take advantage of technologies to improve shuttle safety and the need for a robust space shuttle to assemble the International Space Station. In a June 1999 letter to the White House, NASA Administrator Daniel Goldin declared that the nation faced a space launch crisis. He reported on a NASA review of shuttle safety that indicated the budget for shuttle upgrades in fiscal year 2000 was inadequate to accommodate upgrades necessary to yield significant safety improvements. After two close calls during STS-93 in July 1999, Goldin also chartered a Shuttle Independent Assessment Team, SIAT, chaired by Harry MacDonald, director of NASA Ames Research Center. Among the team's findings, reported in March 2000. Over the course of the shuttle program, processes, procedures, and training have continuously been improved and implemented to make the system safer. The SIAT has a major concern that this critical feature of the shuttle program is being eroded. The major factor leading to this concern is the reduction in allocated resources and appropriate staff. There are important technical areas that are one deep. Also, the SIAT feels strongly that workforce augmentation must be realized principally with NASA personnel rather than with contractor personnel. The SIAT was concerned with success-engendered safety optimism. The SSP must rigorously guard against the tendency to accept risk solely because of prior success. The SIAT was very concerned with what it perceived as risk management process erosion created by the desire to reduce costs. The SIAT feels strongly that NASA safety and mission assurance should be restored to its previous role of an independent oversight body and not be simply a safety auditor. The size and complexity of the shuttle system and of NASA contractor relationships place extreme importance on understanding communication and information handling. Communication of problems and concerns upward to the SSP from the floor also appeared to leave room for improvement. The Shuttle Independent Assessment Team report also stated that the shuttle clearly cannot be thought of as operational in the usual sense. Extensive maintenance, major amounts of touch labor, and a high degree of skill and expertise will always be required. However, the workforce has received a conflicting message due to the emphasis on achieving cost and staff reductions and the pressures placed on increasing scheduled flights as a result of the space station. Responding to NASA's concern that the shuttle required safety-related upgrades, the President's proposed NASA budget for fiscal year 2001 proposed a Safety Upgrades Initiative. That initiative had a short lifespan. In its fiscal year 2002 budget request, NASA proposed to spend $1.836 billion on shuttle upgrades over 5 years. A year later, the fiscal 2003 request contained a plan to spend $1.220 billion, a 34% reduction. The reductions were primarily a response to rising shuttle operating costs and the need to stay within a fixed shuttle budget. Cost growth in shuttle operations forced NASA to use funds intended for space shuttle safety upgrades to address operational supportability, obsolescence, and infrastructure needs. At its March 2001 meeting, NASA's Spaceflight Advisory Committee advised that the Space Shuttle program must make larger, more substantial safety upgrades than currently planned. A budget on the order of 3 times the budget currently allotted for improving the shuttle systems was needed. Later that year, 5 senators complained that the shuttle program is being penalized, despite its outstanding performance, in order to conform to a budget strategy that is dangerously inadequate to ensure safety in America's human spaceflight program. See Chapter 7 for additional discussion of shuttle safety upgrades. Deteriorating shuttle infrastructure. The same ambiguity about investing in shuttle upgrades has also affected the maintenance of shuttle program ground infrastructure. much of which dates to Project Apollo and 1970s shuttle program construction. Figure 5.5-4 depicts the age of the shuttle's infrastructure as of 2000. Most ground infrastructure was not built for such a protracted lifespan. Maintaining infrastructure has been particularly difficult at Kennedy Space Center, where it is constantly exposed to a saltwater environment. Board investigators have identified deteriorating infrastructure associated with the launch pads, vehicle assembly building, and the crawler transporter. Figures 5.5-5 and 5.5-6 depict some of this deterioration. For example, NASA has installed nets and even an entire sub-roof inside the vehicle assembly building to prevent concrete from the building's ceiling from hitting the orbiter and shuttle stack. In addition, the corrosion control challenge results in zinc primer on certain launch pad areas being exposed to the elements. When rain falls on these areas, it carries away zinc, runs onto the leading edge of the orbiter's wings, and causes pinholes in the reinforced carbon-carbon panels. See Chapter 3. In 2000, NASA identified 100 infrastructure items that demanded immediate attention. NASA briefed the Spaceflight Advisory Committee on this infrastructure revitalization initiative in November of that year. The committee concluded that deteriorating infrastructure is a serious, major problem, and upon touring several Kennedy Space Center facilities, declared them in deplorable condition. NASA subsequently submitted a request to the White House Office of Management and Budget during fiscal year 2002 budget deliberations for $600 million to fund the infrastructure initiative. No funding was approved. In fiscal year 2002, Congress added $25 million to NASA's budget for vehicle assembly building repairs. NASA has reallocated limited funds from the shuttle budget to pressing infrastructure repairs and intends to take an integrated look at infrastructure as part of its new shuttle service life extension program. Nonetheless, like space shuttle upgrades, infrastructure revitalization has been mired by the uncertainty surrounding the shuttle program's lifetime. Considering that the shuttle will likely be flying for many years to come, NASA, the White House, and Congress alike now face the specter of having to deal with years of infrastructure neglect. 5.6. A change in NASA leadership. Daniel Golden left NASA in November 2001 after more than 9 years as administrator. The White House chose Sean O'Keefe, the Deputy Director of the White House Office of Management and Budget, as his replacement. O'Keefe stated as he took office that he was not a rocket scientist, but rather that his expertise was in the management of large government programs. His appointment was an explicit acknowledgement by the new Bush administration that NASA's primary problems were managerial and financial. By the time O'Keefe arrived, NASA managers had come to recognize that 1990's funding reductions to the Space Shuttle program had resulted in an excessively fragile program, and also realized that a Space Shuttle replacement was not on the horizon. In 2002, with these issues in mind, O'Keefe made a number of changes to the Space Shuttle program. He transferred management of both the Space Shuttle program and the International Space Station from Johnson Space Center to NASA headquarters. O'Keefe also began considering whether to expand the spaceflight operations contract to cover additional Space Shuttle elements, or to pursue competitive sourcing, a Bush administration initiative that encouraged government agencies to compete with the private sector for management responsibilities of publicly funded activities. To research whether competitive sourcing would be a viable approach for the Space Shuttle program, NASA chartered the Space Shuttle Competitive Sourcing Task Force through the RAND Corporation, a federally funded think tank. In its report, the task force recognized the many obstacles to transferring the Space Shuttle to non-NASA management, primarily NASA's reticence to relinquish control. but concluded that NASA must pursue competitive sourcing in one form or another. NASA began a strategic management of human capital initiative to ensure the quality of the future NASA workforce. The goal is to address the various external and internal challenges that NASA faces as it tries to ensure an appropriate mix and depth of skills for future program requirements. A number of aspects to its strategic human capital plan require legislative approval and are currently before the Congress. The new NASA leadership also began to compare Space Shuttle program practices with the practices of similar high-technology, high-risk enterprises. The Navy nuclear submarine program was the first enterprise selected for comparative analysis. An interim report on this benchmarking effort was presented to NASA in December 2002. In November 2002, NASA made a fundamental change in strategy. In what was called the Integrated Space Transportation Plan, see Figure 5.6-1, NASA shifted money from the Space Launch Initiative to the Space Shuttle and International Space Station programs. The plan also introduced the orbital space plane as a complement to the shuttle for the immediate future. Under this strategy, the shuttle is to fly through at least 2010, when a decision will be made on how long to extend shuttle operations, possibly through 2020 or even beyond. As a step in implementing the plan, NASA included $281.4 million in its fiscal year 2004 budget submission to begin a shuttle service life extension program, which NASA describes as a strategic and proactive program designed to keep the Space Shuttle flying safely and efficiently. The program includes high-priority projects for safety, supportability, and infrastructure in order to combat obsolescence of vehicle, ground systems, and facilities. 5.7. The return of schedule pressure. The International Space Station has been the centerpiece of NASA's human spaceflight program in the 1990s. In several instances, funds for the shuttle program have paid for various International Space Station items. The space station has also affected the Space Shuttle program schedule. By the time the functional cargo block, Zarya, the space station's first element, was launched from the Baikonur Cosmodrome in Kazakhstan in November 1998, the space station was 2 years behind schedule. The launch of STS-88, the first of many shuttle missions assigned to station assembly, followed a month later. Another 4 assembly missions in 1999 and 2000 readied the station for its first permanent crew, Expedition 1, which arrived in late 2000. When the Bush administration came to the White House in January 2001, the International Space Station program was $4 billion over its projected budget. The administration's fiscal year 2002 budget, released in February 2001, declared that the International Space Station would be limited to a U.S. core complete configuration, a reduced design that could accommodate only 3 crew members. The last step in completing the U.S. portion of this configuration would be the addition of the Italian-supplied but U.S.-owned Node 2, which would allow Europe and Japan to connect their laboratory modules to the station. Launching Node 2 and thereby finishing core complete configuration became an important political and programmatic milestone. See Figure 5.7-1. During congressional testimony in May of 2001, Sean O'Keefe, who was then Deputy Director of the White House Office of Management and Budget, presented the administration's plan to bring International Space Station costs under control. The plan outlined a reduction in assembly and logistics flights to reach core complete configuration from 36 to 30. It also recommended redirecting about $1 billion in funding by canceling U.S. elements not yet completed, such as the habituation module and the X-38 crew return vehicle. The X-38 would have allowed emergency evacuation and landing capability for a 7-member station crew. Without it, the crew was limited to 3, the number that could fit into a Russian Soyuz crew rescue vehicle. In his remarks, O'Keefe stated, "NASA's degree of success in gaining control of cost growth on space station will not only dictate the capabilities that the station will provide, but will send a strong signal about the ability of NASA's human spaceflight program to effectively manage large development programs. NASA's credibility with the administration and the Congress for delivering on what is promised, and the longer-term implications that such credibility may have on the future of human spaceflight, hang in the balance." At the request of the White House Office of Management and Budget, in July 2001, NASA Administrator Dan Goldin formed an International Space Station Management and Cost Evaluation Task Force. The International Space Station Management and Cost Evaluation Task Force was to assist NASA in identifying the reforms needed to restore the station program's fiscal and management credibility. While the primary focus of the task force was on the space station program management, its November 2001 report issued a general condemnation of how NASA, and particularly Johnson Space Center, had managed the International Space Station, and, by implication, NASA's overall human spaceflight effort. The report noted existing deficiencies in management structure, institutional culture, cost estimating, and program control, and that the institutional needs of the human spaceflight centers are driving the program, rather than program requirements being served by the centers. The task force suggested that, as a cost control measure, the Space Shuttle be limited to 4 flights per year, and that NASA revise the station crew rotation period to 6 months. The cost savings that would result from eliminating flights could be used to offset cost overruns. NASA accepted a reduced flight rate. The Space Shuttle Program Office concluded that based on a rate of 4 flights a year, Node 2 could be launched by February 19, 2004. In testimony before the House Committee on Science on November 7, 2001, Task Force Chairman Thomas Young identified what became known as a performance gate. He suggested that over the next 2 years, NASA should plan and implement a credible core-complete program. In fall 2003, an assessment would be made concerning the International Space Station program performance and NASA's credibility. If satisfactory, resource needs would be assessed, and an ISS end state that realized the science potential would become the baseline. If unsatisfactory, the core complete program would become the end state. Testifying the same day, Office of Management and Budget Deputy Director Sean O'Keefe indicated the administration's agreement with the planned performance gate. The concept presented by the task force of a decision gate in 2 years that could lead to an end state other than the U.S. core complete station is an innovative approach and one the administration will adopt. It calls for NASA to make the necessary management reforms to successfully build the core complete station and operate it within the $8.3 billion available through fiscal year 2006, plus other human spaceflight resources. If NASA fails to meet the standards, then an end state beyond core complete is not an option. The strategy places the burden of proof on NASA performance to ensure that NASA fully implements the needed reforms. Mr. O'Keefe added in closing, "A most important next step, one on which the success of all these reforms hinges, is to provide new leadership for NASA and its human spaceflight activities. NASA has been well served by Dan Goldin. New leadership is now necessary to continue moving the ball down the field with the goal line in sight. The administration recognizes the importance of getting the right leaders in place as soon as possible, and I am personally engaged in making sure that this happens." A week later, Sean O'Keefe was nominated by President Bush as the new NASA administrator. To meet the new flight schedule, in 2002, NASA revised its shuttle manifest, calling for a docking adapter to be installed in Columbia after the STS-107 mission so that it could make an October 2003 flight to the International Space Station. Columbia was not optimal for station flights. The orbiter could not carry enough payload, but it was assigned to this flight because Discovery was scheduled for 18 months of major maintenance. To ensure adequate shuttle availability for the February 2004 Node 2 launch date, Columbia would fly an International Space Station resupply mission. The White House and Congress had put the International Space Station program, the Space Shuttle program, and indeed NASA on probation. NASA had to prove it could meet schedules within cost or risk halting space station construction at core complete, a configuration far short of what NASA anticipated. The new NASA management viewed the achievement of an on-schedule Node 2 launch as an endorsement of its successful approach to shuttle and station programs. Any suggestions that it would be difficult to meet that launch date were brushed aside. This insistence on a fixed launch schedule was worrisome. The International Space Station Management and Cost Evaluation Task Force, in particular, was concerned with the emphasis on a specific launch date. It noted in its 2002 review of progress toward meeting its recommendations that significant progress has been made in nearly all aspects of the ISS program, but that there was significant risk with the Node 2 February 04 schedule. By November 2002, NASA had flown 16 space shuttle missions dedicated to station assembly and crew rotation. 5 crews had lived on board the station, the last 4 of them delivered via space shuttles. As the station had grown, so had the complexity of the missions required to complete it. With the International Space Station assembly more than half complete, the station and shuttle programs had become irreversibly linked. Any problems with or perturbations to the planned schedule of one program reverberated through both programs. For the shuttle program, this meant that the conduct of all missions, even non-station missions like STS-107, would have an impact on the Node 2 launch date. In 2002, this reality and the events of the months that would follow began to place additional schedule pressures on the Space Shuttle program. Those pressures are discussed in Section 6.2. 5.8. Conclusion. Over the last decade, the Space Shuttle program has operated in a challenging and often turbulent environment. As discussed in this chapter, there were at least 3 major contributing factors to that environment. Throughout the decade, the shuttle program has had to function within an increasingly constrained budget. Both the shuttle budget and workforce have been reduced by over 40% during the past decade. The White House, Congress, and NASA leadership exerted constant pressure to reduce or at least freeze operating costs. As a result, there was little margin in the budget to deal with unexpected technical problems or make shuttle improvements. The shuttle was mischaracterized by the 1995 Kraft Report as a mature and reliable system about as safe as today's technology will provide. Based on this mischaracterization, NASA believed that it could turn increased responsibilities for shuttle operations over to a single prime contractor and reduce its direct involvement in ensuring safe shuttle operations, instead monitoring contractor performance from a more detached position. NASA also believed that it could use the mature shuttle to carry out operational missions without continually focusing engineering attention on understanding the mission-by-mission anomalies inherent in a developmental vehicle. In the 1990s, the planned date for replacing the shuttle shifted from 2006 to 2012 and then to 2015 or later. Given the uncertainty regarding the shuttle's service life, there has been policy and budgetary ambivalence on investing in the vehicle. Only in the past year has NASA begun to provide the resources needed to sustain extended shuttle operations. Previously, safety and support upgrades were delayed or deferred, and shuttle infrastructure was allowed to deteriorate. The board observes that this is hardly an environment in which those responsible for safe operation of the shuttle can function without being influenced by external pressures. It is to the credit of Space Shuttle managers and the shuttle program workforce that the vehicle was able to achieve its program objectives for as long as it did. An examination of the shuttle program's history, from Challenger to Columbia, raises the question: did the Space Shuttle program budgets, constrained by the White House and Congress, threaten safe shuttle operations? There is no straightforward answer. In 1994, an analysis of the shuttle budget concluded that reductions made in the early 1990s represented a healthy tightening up of the program. Certainly those in the Office of Management and Budget and in NASA's Congressional Authorization and Appropriations subcommittees thought they were providing enough resources to operate the shuttle safely, while also taking into account the expected shuttle lifetime and the many other demands on the federal budget. NASA headquarters agreed, at least until Administrator Golden declared a space launch crisis in June 1999 and asked that additional resources for safety upgrades be added to the NASA budget. By 2001, however, one experienced observer of the space program described the shuttle workforce as the few, the tired, and suggested that a decade of downsizing and budget tightening has left NASA exploring the universe with a less experienced staff and older equipment. It is the board's view that this latter statement is an accurate depiction of the Space Shuttle program at the time of STS-107. The program was operating too close to too many margins. The board also finds that recent modest increases in the shuttle program's budget are necessary and overdue steps toward providing the resources to sustain the program for its now extended lifetime. Similarly, NASA has recently recognized that providing an adequately sized and appropriately trained workforce is critical to the agency's future success. An examination of the program's management changes also leads to the question: did turmoil in the management structure contribute to the accident? The board found no evidence that the transition from many space shuttle contractors to a partial consolidation of contracts under a single firm has by itself introduced additional technical risk into the space shuttle program. The transfer of responsibilities that has accompanied the spaceflight operations contract has, however, complicated an already complex program structure and created barriers to effective communication. Designating the Johnson Space Center as the lead center for the Space Shuttle program did resurrect some of the center rivalries and communication difficulties that existed before the Challenger accident. The specific ways in which this complexity and lack of an integrated approach to shuttle management impinged on NASA's performance during and before the flight of STS-107 are discussed in Chapters 6 and 7. As the 21st century began, NASA's deeply ingrained human spaceflight culture, one that has evolved over 30 years as the basis for a more conservative, less technically and organizationally capable organization than the Apollo-era NASA, remained strong enough to resist external pressures for adaptation and change. At the time of the launch of STS-107, NASA retained too many negative, and also many positive, aspects of its traditional culture: flawed decision-making, self-deception, introversion, and a diminished curiosity about the world outside the perfect place. These characteristics were reflected in NASA's less than stellar performance before and during the STS-107 mission, which is described in the following chapters. End of Section 20. Recording by Maria Kasper.
Section 21 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick McHaffie, Chicago, USA. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6A, Decision Making at NASA, Part 1. Chapter 6, Decision Making at NASA. The dwindling post-Cold War shuttle budget that launched NASA leadership on a crusade for efficiency in the decade before Columbia's final flight powerfully shaped the environment in which shuttle managers worked. The increased organizational complexity, transitioning authority structures, and ambiguous working relationships that defined the restructured Space Shuttle program in the 1990s created turbulence that repeatedly influenced decisions made before and during STS-107. This chapter connects Chapter 5's analysis of NASA's broader policy environment to a focused scrutiny of Space Shuttle program decisions that led to the STS-107 accident. Section 6.1 illustrates how foam debris losses that violated design requirements came to be defined by NASA management as an acceptable aspect of shuttle missions, one that posed merely a maintenance turnaround problem rather than a safety of flight concern. Section 6.2 shows how, at a pivotal juncture just months before the Columbia accident, the management goal of completing Node 2 of the International Space Station on time encouraged shuttle managers to continue flying even after a significant bipod foam debris strike on STS-112. Section 6.3 notes the decisions made during STS-107 in response to the bipod foam strike and reveals how engineers' concerns about risk and safety were competing with and were defeated by management's belief that foam could not hurt the orbiter, as well as the need to keep on schedule. In relating a rescue and repair scenario that might have enabled the crew's safe return, Section 6.4 grapples with yet another latent assumption held by shuttle managers during and after STS-107, that even if the foam strike had been discovered, nothing could have been done. 6.1 A History of Foam Anomalies. The shedding of external tank foam, the physical cause of the Columbia accident, had a long history. Damage caused by debris has occurred on every space shuttle flight, and most missions have had insulating foam shed during ascent. This raises an obvious question. Why did NASA continue flying the shuttle with a known problem that violated design requirements? It would seem that the longer the shuttle program allowed debris to continue striking the orbiters, the more opportunity existed to detect the serious threat it posed. But this is not what happened. Although engineers have made numerous changes in foam design and application in the 25 years that the external tank has been in production, the problem of foam shedding has not been solved, nor has the orbiter's ability to tolerate impacts from foam or other debris been significantly improved. The need for foam insulation. The external tank contains liquid oxygen and hydrogen propellants stored at -297 and -423 degrees Fahrenheit. Were the super-cold external tank not sufficiently insulated from the warm air, its liquid propellants would boil, and atmospheric nitrogen and water vapor would condense and form thick layers of ice on its surface. Upon launch, the ice could break off and damage the orbiter. See Chapter 3. To prevent this from happening, large areas of the external tank are machine sprayed with 1 or 2 inches of foam, while specific fixtures, such as the bipod ramps, are hand sculpted with thicker coats. Most of these insulating materials fall into a general category of foam and are outwardly similar to hardware store sprayable foam insulation. The problem is that foam does not always stay where the external tank manufacturer, Lockheed Martin, installs it. During flight, popcorn to briefcase-sized chunks detach from the external tank. Original design requirements. Early in the Space Shuttle program, foam loss was considered a dangerous problem. Design engineers were extremely concerned about potential damage to the orbiter and its fragile thermal protection system, parts of which are so vulnerable to impacts that lightly pressing a thumbnail into them leaves a mark. Because of these concerns, the baseline design requirements in the shuttle's Flight and Ground System Specification, Book 1, Requirements, precluded foam shedding by the external tank, specifically 3.2.1.2.14, debris prevention. The Space Shuttle system, including the ground systems, shall be designed to preclude the shedding of ice and/or other debris from the shuttle elements during pre-launch and flight operations that would jeopardize the flight crew, vehicle, mission success, or would adversely impact turnaround operations. 3.2.1.1.17 External tank debris limits. No debris shall emanate from the critical zone of the external tank on the launch pad or during ascent, except for such material which may result from normal thermal protection system recession due to ascent heating. The assumption that only tiny pieces of debris would strike the orbiter was also built into original design requirements, which specified that the thermal protection system, the tiles and reinforced carbon-carbon or RCC panels, would be built to withstand impacts with a kinetic energy less than 0.006 foot-pounds. Such a small tolerance leaves the orbiter vulnerable to strikes from birds, ice, launch pad debris, and pieces of foam. Despite the design requirements that the external tank shed no debris, and that the orbiter not be subjected to any significant debris hits, Columbia sustained damage from debris strikes on its inaugural 1981 flight. More than 300 tiles had to be replaced. Engineers stated that they had known in advance that the external tank was going to produce the debris shower that occurred during launch. They would have had a difficult time clearing Columbia for flight. Discussion of foam strikes prior to the Rogers Commission. Foam strikes were a topic of management concern at the time of the Challenger accident. In fact, during the Rogers Commission accident investigation, Shuttle Program Manager Arnold Aldrich cited a contractor's concerns about foam shedding to illustrate how well the shuttle program manages risk. Quote, on a series of 4 or 5 external tanks, the thermal insulation around the inner tank had large divots of insulation coming off and impacting the orbiter. We found significant amount of damage to one orbiter after a flight, and on the subsequent flight, we had a camera in the equivalent of the wheel well, which took a picture of the tank after separation, and we determined that this was in fact the cause of the damage. At that time, we wanted to be able to proceed with the launch program if it was acceptable. So we undertook discussions of what would be acceptable in terms of potential field repairs. And during those discussions, Rockwell was very conservative because, rightly, damage to the orbiter TPS, thermal protection system, is damage to the orbiter system, and it has a very stringent environment to experience during the re-entry phase. Aldrich described the pieces of foam as half a foot square or a foot by half a foot, and some of them much smaller and localized to a specific area, but fairly high up on the tank. So they had a good shot at the orbiter underbelly, and this is where we had the damage. Continuing foam loss. Despite the high level of concern after STS-1 and through the Challenger accident, foam continued to separate from the external tank. Photographic evidence of foam shedding exists for 65 of the 79 missions for which imagery is available. Of the 34 missions for which there are no imagery, 8 missions where foam loss is not seen in the imagery, and 6 missions where imagery is inconclusive, foam loss can be inferred from the number of divots on the orbiter's lower surfaces. Over the life of the Space Shuttle program, orbiters have returned with an average of 143 divots in the upper and lower surfaces of the thermal protection system tiles, with 31 divots averaging over an inch in one dimension. The orbiter's lower surfaces have an average of 101 hits, 23 of which are larger than an inch in diameter. Though the orbiter is also struck by ice and pieces of launch pad hardware during launch, by micrometeoroids and orbital debris in space, and by runway debris during landing, the board concludes that foam is likely responsible for most debris hits. With each successful landing, it appears that NASA engineers and managers increasingly regarded the foam shedding as inevitable, and as either unlikely to jeopardize safety or simply an acceptable risk. The distinction between foam loss and debris events also appears to have become blurred. NASA and contractor personnel came to view foam strikes not as a safety of flight issue, but rather a simple maintenance or turnaround issue. In Flight Readiness Review documentation, Mission Management Team Minutes, in-flight anomaly disposition reports, and elsewhere, what was considered a serious threat to the orbiter came to be treated as in-family. A reportable problem that was within the known experience base was believed to be understood and was not regarded as a safety of flight issue. Bipod ramp foam loss events. Chunks of foam from the external tank's forward bipod attachment, which connects the orbiter to the external tank, are some of the largest pieces of debris that have struck the orbiter. To place the foam loss from STS-107 in a broader context, the board examined every known instance of foam shedding from this area. Foam loss from the left bipod ramp, called the Y ramp in NASA parlance, has been confirmed by imagery on 7 of the 113 missions flown. However, only on 72 of these missions was available imagery of sufficient quality to determine left bipod ramp foam loss. Therefore, foam loss from the left bipod area occurred on approximately 10% of flights, 7 events out of 72 imaged flights. On the 66 flights that imagery was available for the right bipod area, foam loss was never observed. NASA could not explain why the only left bipod experienced foam loss. See Figure 6.1-1. The first known bipod ramp foam loss occurred during STS-7, Challenger's second mission. See Figure 6.1-2. Images taken after external tank separation revealed that a 19 by 12 inch piece of the left bipod ramp was missing, and that the external tank had some 25 shallow divots in the foam just forward of the bipod struts and another 40 divots in the foam covering the lower external tank. After the mission was completed, the Program Requirements Control Board cited the foam loss as an in-flight anomaly. Citing an event as an in-flight anomaly means that before the next launch, A specific NASA organization must resolve the problem or prove that it does not threaten the safety of the vehicle or crew. At the Flight Readiness Review for the next mission, Orbiter Project Management reported that, based on the completion of repairs to the orbiter thermal protection system, the bipod ramp foam loss in-flight anomaly was resolved, or closed. However, although the closure documents detailed the repairs made to the orbiter, neither the Certificate of Flight Readiness documentation nor the Flight Readiness Review documentation referenced correcting the cause of the damage, the shedding of foam. The second bipod ramp foam loss occurred during STS-32R, Columbia's ninth flight, on January 9, 1990. A post-mission review of STS-32R photography revealed 5 divots in the intertank foam ranging from 6 to 28 inches in diameter, the largest of which extended into the left bipod ramp foam. A post-mission inspection of the lower surface of the orbiter revealed 111 hits, 13 of which were 1 inch or greater in one dimension. An in-flight anomaly assigned to the external tank project was closed out at the Flight Readiness Review for the next mission, STS-36, on the basis that there may have been local voids in the foam bipod ramp where it attached to the metal skin of the external tank. To address the foam loss, NASA engineers poked small vent holes through the intertank foam to allow trapped gases to escape voids in the foam where they otherwise might build up pressure and cause the foam to pop off. However, NASA is still studying this hypothesized mechanism of foam loss. Experiments conducted under the board's purview indicate that other mechanisms may be at work. See foam fracture under hydrostatic pressure in Chapter 3. As discussed in Chapter 3, the board notes that the persistent uncertainty about the causes of foam loss and potential orbiter damage results from a lack of thorough hazard analysis and engineering attention. The third bipod foam loss occurred on January 25, 1992, during the launch of Columbia on STS-50, when an approximately 26 by 10 inch piece separated from the left bipod ramp area. Post-mission inspection revealed a 9 inch by 4.5 inch by 0.5 inch divot in the tile, the largest area of tile damage in shuttle history. The external tank project at Marshall Space Flight Center and the integration office at Johnson Space Center cited separate in-flight anomalies. The integration office closed out its in-flight anomaly 2 days before the next flight, STS-46, by deeming damage to the thermal protection system an accepted flight risk. In Integration Hazard Report 37, the integration office noted that impact damage was shallow, the tile loss was not a result of excessive aerodynamic loads, and the external tank thermal protection system failure was the result of inadequate venting. The external tank project closed out its in-flight anomaly with the rationale that foam loss during ascent was not considered a flight or safety issue. Note the difference in how each program addressed the foam shedding problem. While the integration office deemed it an accepted risk, the external tank project considered it not a safety of flight issue. Hazard Report 37 would figure in the STS-113 Flight Readiness Review, where the crucial decision was made to continue flying with the foam loss problem. This inconsistency would reappear 10 years later after bipod foam shedding during STS-112. The fourth and fifth bipod ramp foam loss events went undetected until the board directed NASA to review all available imagery for other instances of bipod foam shedding. This review of imagery from tracking cameras, the umbilical well camera, and video and still images from flight crew handheld cameras revealed bipod foam loss on STS-52 and STS-62, both of which were flown by Columbia. STS-52, launched on October 22, 1992, lost an 8 by 4 inch corner of the left bipod ramp, as well as portions of foam covering the left jack pad, a piece of external tank hardware that facilitates the orbiter attachment process. The STS-52 post-mission inspection noted a higher than average 290 hits on upper and lower thermal protection system tiles, 16 of which were greater than 1 inch in one dimension. External tank separation videos of STS-62 launched on March 4, 1994, revealed that a 1 by 3 inch piece of foam in the rear face of the left bipod ramp was missing, as were small pieces of foam around the bipod ramp. Because these incidents of missing bipod foam were not detected until after the STS-107 accident, no in-flight anomalies had been written. The board concludes that NASA's failure to identify these bipod foam losses at the time they occurred means the agency must examine the adequacy of its film review, post-flight inspection, and program requirements control board processes. The sixth and final bipod ramp event before STS-107 occurred during STS-112 on October 7, 2002. See Figure 6.1-3. At 33 seconds after launch, when Atlantis was at 12,500 feet and traveling at Mach 0.75, ground cameras observed an object traveling from the external tank that subsequently impacted the solid rocket booster external tank attachment ring. After impact, the debris broke into multiple pieces that fell along the solid rocket booster exhaust plume. Post-mission inspection of the solid rocket booster confirmed damage to foam on the forward face of the external tank attachment ring. The impact was approximately 4 inches wide and 3 inches deep. Post-external tank separation photography by the crew showed that a 4 by 5 by 12 inch, 240 cubic inch corner section of the left bipod ramp was missing, which exposed the super lightweight ablator coating on the bipod housing. This missing chunk of foam was believed to be the debris that impacted the external tank attachment ring during ascent. The post-launch review of photos and video identified these debris events, but the mission evaluation room logs and mission management team minutes do not reflect any discussions of them. Umbilical cameras and the statistics of bipod ramp loss. Over the course of the 113 Space Shuttle missions, the left bipod ramp has shed significant pieces of foam at least 7 times. Foam shedding from the right bipod ramp has never been confirmed. The right bipod ramp may be less subject to foam shedding because it is partially shielded from aerodynamic forces by the external tank's liquid oxygen line. The fact that 5 of these left bipod shedding events occurred on missions flown by Columbia sparked considerable board debate. Although initially this appeared to be an improbable coincidence that would have caused the board to fault NASA for improper trend analysis and lack of engineering curiosity. On closer inspection, the board concluded that this coincidence is probably the result of a bias in the sample of known bipod foam shedding. Before the Challenger accident, only Challenger and Columbia carried umbilical well cameras that imaged the external tank after separation, so there are more images of Columbia than of the other orbiters. The bipod was imaged 26 of 28 of Columbia's missions. In contrast, Challenger had 7 of 10, Discovery had only 14 of 30, Atlantis only 14 of 26, and Endeavour 12 of 19. STS-113 Flight Readiness Review, a pivotal decision. Because the bipod ramp shedding on STS-112 was significant both in size and in the damage it caused, and because it occurred only 2 flights before STS-107, the board investigated NASA's rationale to continue flying. This decision made by the Program Requirements Control Board at the STS-113 Flight Readiness Review is among those most directly linked to the STS-107 accident. Had the foam loss during STS-112 been classified as a more serious threat, managers might have responded differently when they heard about the foam strike on STS-107. Alternately, in the face of the increased risk, STS-107 might not have flown at all. However, at STS-113's Flight Readiness Review, managers formally accepted a flight rationale that stated it was safe to fly with foam losses. This decision enabled, and perhaps even encouraged, mission management team members to use similar reasoning when evaluating whether the foam strike on STS-107 posed a safety of flight issue. At the Program Requirements Control Board meeting following the return of STS-112, the Inter-Center Photo Working Group recommended that the loss of bipod foam be classified as an in-flight anomaly. In a meeting chaired by Shuttle Program Manager Ron Dittemore and attended by many of the managers who would be actively involved with STS-107, including Linda Ham, the Program Requirements Control Board ultimately decided against such classification. Instead, after discussions with the Integration Office and the External Tank Project, the Program Requirements Control Board Chairman assigned an action to the External Tank Project to determine the root cause of the foam loss and to propose corrective action. This was inconsistent with previous practice, in which all other known bipod foam shedding was designated as in-flight anomalies. The Program Requirements Control Board initially set December 5, 2002 as the date to report back on this action, even though STS-113 was scheduled to launch on November 10th. The due date subsequently slipped until after the planned launch and return of STS-107. The Space Shuttle program decided to fly not 1 but 2 missions before resolving the STS-112 foam loss. The board wondered why NASA would treat the STS-112 foam loss differently than all others. What drove managers to reject the recommendation that the foam loss be deemed an in-flight anomaly? Why did they take the unprecedented step of scheduling not 1 but eventually 2 missions to fly before the External Tank Project was to report back on foam losses? It seems that shuttle managers had become conditioned over time to not regard foam loss or debris as a safety of flight concern. As will be discussed in Section 6.2, the need to adhere to the Node 2 launch schedule also appears to have influenced their decision. Had the STS-113 mission been delayed beyond early December 2002, the Expedition 5 crew on board the space station would have exceeded its 180-day on-orbit limit, and the Node 2 launch date, a major management goal, would not be met. Even though the results of the external tank project engineering analysis were not due until after STS-113, the foam shedding was reported or briefed at STS-113's Flight Readiness Review on October 31, 2002, a meeting that Dittemore and Ham attended. Two slides from this brief, Figure 6.1-5, explain the disposition of bipod ramp foam loss on STS-112. This rationale is seriously flawed. The first and third statements listed under Rationale for Flight are incorrect. Contrary to the chart, which was presented by Jerry Smelser, the program manager for the external tank project, the bipod ramp design had changed as of external tank 76. This casts doubt on the implied argument that because the design had not changed, future bipod foam events were unlikely to occur. Although the other points may be factually correct, they provide an exceptionally weak rationale for safe flight. The fact that ramp closeout work was performed by experienced practitioners, or that application involves craftsmanship in the use of validated application processes, in no way decreases the chances of recurrent foam loss. The statement that the probability of loss of ramp thermal protection system is no higher, no lower than previous flights could be just as accurately stated. The probability of bipod foam loss on the next flight is just as high as it was on previous flights. With no engineering analysis, shuttle managers used past success as a justification for future flights and made no change to the external tank configurations planned for STS-113 and subsequently for STS-107. Along with this chart, the NASA Headquarters Safety Office presented a report that estimated a 99% probability of foam not being shed from the same area, even though no corrective action had been taken following the STS-112 foam shedding. The ostensible justification for the 99% figure was a calculation of the actual rate of bipod loss over 61 flights. This calculation was a sleight-of-hand effort to make the probability of bipod foam loss appear low, rather than a serious grappling with the probability of bipod ramp foam separating. For one thing, the calculation equates the probability of left and right bipod loss, when right bipod loss has never been observed, and the amount of imagery available for left and right bipod events differs. The calculation also miscounts the actual number of bipod ramp losses in two ways. First, by restricting the sample size to flights between STS-112 and the last known bipod ramp loss, it excludes known bipod ramp losses from STS-7, STS-32R, and STS-50. Second, by failing to project the statistical rate of bipod loss across the many missions for which no bipod imagery is available, The calculation assumes a "what you don't see won't hurt you" mentality, when in fact the reverse is true. When the statistical rate of bipod foam loss is projected across missions for which imagery is not available, and the sample size is extended to include every mission from STS-1 on, the probability of bipod loss increases dramatically. The board's review after STS-107, which included the discovery of 2 additional bipod ramp losses that NASA had not previously noted, concluded that bipod foam loss occurred on approximately 10% of all missions. During the brief at STS-113's Flight Readiness Review, the Associate Administrator for Safety and Mission Assurance scrutinized the Integration Hazard Report 37 conclusion that debris shedding was an accepted risk, as well as the external tank project's rationale for flight. After conferring, STS-113 Flight Readiness Review participants ultimately agreed that foam shedding should be characterized as an accepted risk rather than a not a safety of flight issue. Space Shuttle Program Management accepted this rationale, and STS-113's Certificate of Flight Readiness was signed. The decision made at the STS-113 Flight Readiness Review seemingly acknowledged that the foam posed a threat to the orbiter, although the continuing disagreement over whether foam was not a safety of flight issue versus an accepted risk demonstrates how the two terms became blurred over time, clouding the precise conditions under which an increase in risk would be permitted by shuttle program management. In retrospect, the bipod foam that caused a 4 by 3 inch gouge in the foam on one of Atlantis' solid rocket boosters just months before STS-107 was a strong signal of potential future damage that shuttle engineers ignored. Despite the significant bipod foam loss on STS-112, shuttle program engineers made no external tank configuration changes, no moves to reduce the risk of bipod ramp shedding or potential damage to the orbiter on either of the next 2 flights, STS-113 and STS-107, and did not update Integrated Hazard Report 37. The board notes that although there is a process for conducting hazard analyses when the system is designed, and a process for reevaluating them when a design is changed or the component is replaced, no process addresses the need to update a hazard analysis when anomalies occur. A stronger integration office would likely have insisted that Integrated Hazard Analysis 37 be updated. In the course of that update, engineers would be forced to consider the cause of foam shedding and the effects of shedding on other shuttle elements, including the orbiter thermal protection system. STS-113 launched at night, and although it is occasionally possible to image the orbiter from light given off by the solid rocket motor plume, in this instance no imagery was obtained, and it is possible that foam could have been shed. The acceptance of the rationale to fly cleared the way for Columbia's launch and provided a method for mission managers to classify the STS-107 foam strike as a maintenance and turnaround concern rather than a safety of flight issue. It is significant that in retrospect, several NASA managers identified their acceptance of this flight rationale as a serious error. The foam loss issue was considered so insignificant by some shuttle program engineers and managers that the STS-107 Flight Readiness Review documents include no discussion of the still unresolved STS-112 foam loss. According to program rules, this discussion was not a requirement because the STS-112 incident was only identified as an action, not an in-flight anomaly. However, because the action was still open and the date of its resolution had slipped, the board believes that shuttle program managers should have addressed it. Had the foam issue been discussed in STS-107 pre-launch meetings, mission managers may have been more sensitive to the foam shedding and may have taken more aggressive steps to determine the extent of the damage. The seventh and final known bipod ramp foam loss occurred on January 16, 2003, during the launch of Columbia on STS-107. After the Columbia bipod loss, the Program Requirements Control Board deemed the foam loss an in-flight anomaly to be dealt with by the External Tank Project. End of Chapter 6A. Decision Making at NASA, Part 1.
Section 22 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6B. Decision-Making at NASA, Part 2. Other foam debris events. To better understand how NASA's treatment of debris strikes evolved over time, the board investigated missions where debris was shed from locations other than the external tank bipod ramp. The number of debris strikes to the orbiter's lower surface thermal protection system that resulted in tile damage greater than 1 inch in diameter is shown in Figure 6.1-6. The number of debris strikes may be small, but a single strike could damage several tiles. See Figure 6.1-7. One debris strike, in particular, foreshadows the STS-107 event. When Atlantis was launched on STS-27R on December 2, 1988, the largest debris event up to that time significantly damaged the orbiter. Post-launch analysis of tracking camera imagery by the Intercenter Photo Working Group identified a large piece of debris that struck the thermal protection system tile at approximately 85 seconds into the flight. On Flight Day 2, Mission Control asked the flight crew to inspect Atlantis with a camera mounted on the remote manipulator arm, a robotic device that was not installed on Columbia for STS-107. Mission Commander R.L. Hoot Gibson later stated that Atlantis looked like it had been blasted by a shotgun. Concerned that the orbiter's thermal protection system had been breached, Gibson ordered that the video be transferred to Mission Control so that NASA engineers could evaluate the damage. When Atlantis landed, engineers were surprised by the extent of the damage. Post-mission inspections deemed it the most severe of any mission yet flown. The orbiter had 707 dings, 298 of which were greater than an inch in one dimension. Damage was concentrated outboard of a line right of the bipod attachment to the liquid oxygen umbilical line. Even more worrisome, the debris had knocked off a tile, exposing the orbiter's skin to the heat of re-entry. Post-flight analysis concluded that structural damage was confined to the exposed cavity left by the missing tile, which happened to be at the location of a thick aluminum plate covering an L-band navigation antenna. Were it not for the thick aluminum plate, Gibson stated during a presentation to the board that a burn-through may have occurred. The board notes the distinctly different ways in which the STS-27R and STS-107 debris strike events were treated. After the discovery of the debris strike on Flight Day 2 of STS-27R, the crew was immediately directed to inspect the vehicle. More severe thermal damage, perhaps even a burn-through, may have occurred were it not for the aluminum plate at the site of the tile loss. 14 years later, when a debris strike was discovered on Flight Day 2 of STS-107, Shuttle Program Management declined to have the crew inspect the orbiter for damage, declined to request on-orbit imaging, and ultimately discounted the possibility of a burn-through. In retrospect, the debris strike on STS-27R is a strong signal of the threat debris posed that should have been considered by shuttle management when STS-107 suffered a similar debris strike. The board views the failure to do so as an illustration of the lack of institutional memory in the Space Shuttle program that supports the board's claim, discussed in Chapter 7, that NASA is not functioning as a learning organization. After the STS-27R damage was evaluated during a post-flight inspection, the Program Requirements Control Board assigned in-flight anomalies to the orbiter and solid rocket booster projects. Marshall Sprayable Ablator, MSA-1, material found embedded in an insulation blanket on the right orbital maneuvering system pod confirmed that the ablator on the right solid rocket booster nose cap was the most likely source of the debris. Because an improved ablator material, MSA-2, would now be used on the solid rocket booster nose cap, the issue was considered closed by the time of the next mission's flight readiness review. The Orbiter Thermal Protection System review team concurred with the use of the improved ablator without reservation. An STS-27R investigation team notation mirrors a Columbia Accident Investigation Board finding. The STS-27R investigation noted, "It is observed that program emphasis and attention to tile damage assessments varies with severity, and that detailed records could be augmented to ease trend maintenance." Emphasis added. In other words, Space Shuttle program personnel knew that the monitoring of tile damage was inadequate and that clear trends could be more readily identified if monitoring was improved, but no such improvements were made. The board also noted that an STS-27R investigation team recommendation correlated to the Columbia accident 14 years later. It is recommended that the program actively solicit design improvements directed toward eliminating debris sources or minimizing damage potential. Another instance of non-bipod foam damage occurred on STS-35. Post-flight inspections of Columbia after STS-35 in December 1990 showed a higher-than-average amount of damage on the orbiter's lower surface. A review of external tank separation film revealed approximately 10 areas of missing foam on the flange connecting the liquid hydrogen tank to the intertank. An in-flight anomaly was assigned to the external tank project, which closed it by stating that there was no increase in orbiter thermal protection system damage and that it was not a safety of flight concern. The board notes that it was in a discussion of the STS-36 Flight Readiness Review that NASA first identified this problem as a turnaround issue. Per established procedures, NASA was still designating foam loss events as in-flight anomalies and continued to make various corrective actions, such as drilling more vent holes and improving the foam application process. Discovery was launched on STS-42 on January 22, 1992. A total of 159 hits on the orbiter thermal protection system were noted after landing. 2 8 to 12-inch diameter divots in the external tank intertank area were noted during post-external tank separation photo evaluation, and these pieces of foam were identified as the most probable sources of the damage. The external tank project was assigned an in-flight anomaly, and the incident was later described as an unexplained or isolated event. However, at later flight readiness reviews, the Marshall Space Flight Center briefed this as being not a safety of flight concern. The next flight, STS-45, would be the first mission launched before the foam loss in-flight anomaly was closed. On March 24, 1992, Atlantis was launched on STS-45. Post-mission inspection revealed exposed substrata on the upper surface of right-wing leading-edge reinforced carbon-carbon RCC Panel 10, caused by two gouges, one 1.9 inches by 1.6 inches, and the other 0.4 inches by 1 inch. Before the next flight, an in-flight anomaly assigned to the orbiter project was closed as unexplained but most likely orbital debris. Despite this closure, the Safety and Mission Assurance Office expressed concern as late as the pre-launch mission management team meeting 2 days before the launch of STS-49. Nevertheless, the mission was cleared for launch. Later laboratory tests identified pieces of man-made debris lodged in the RCC, including stainless steel, aluminum, and titanium, but no conclusion was made about the source of the debris. The board notes that this indicates there were transport mechanisms available to determine the path the debris took to impact the wing leading edge. See Section 3.4. The Program Requirements Control Board also assigned the external tank project an in-flight anomaly after foam loss on STS-56, Discovery, and STS-58, Columbia, both of which were launched in 1993. These missions demonstrate the increasingly casual ways in which debris impacts were dispositioned by shuttle program managers. After post-flight analysis determined that on both missions the foam had come from the intertank and bipod jackpad areas, the rationale for closing the in-flight anomalies included notations that external tank foam debris was in family or within the experience base. During the launch of STS-87 Columbia on November 19, 1997, a debris event focused NASA's attention on debris shedding and damage to the orbiter. Post-external tank separation photography revealed a significant loss of material from both thrust panels, which are fastened to the solid rocket booster forward attachment points on the intertank structure. Post-landing inspection of the orbiter noted 308 hits, with 244 on the lower surface and 109 larger than an inch. The foam loss from the external tank thrust panels was suspected as the most probable cause of the orbiter thermal protection system damage. Based on data from post-flight inspection reports, as well as comparisons with statistics from 71 similarly configured flights, the total number of damage sites and the number of damage sites 1 inch or larger were considered out of family. An investigation was conducted to determine the cause of the material loss and the actions required to prevent a recurrence. The foam loss problem on STS-87 was described as popcorning because of the numerous popcorn-size foam particles that came off the thrust panels. Popcorning has always occurred, but it began earlier than usual in the launch of STS-87. The cause of the earlier-than-normal popcorning, but not the fundamental cause of popcorning, was traced to a change in foam-blowing agents that caused pressure buildups and stress concentrations within the foam. In an effort to reduce its use of chlorofluorocarbons, CFCs, NASA had switched from a CFC-11 chlorofluorocarbon blowing agent to an HCFC-141b blowing agent, beginning with external tank 85, which was assigned to STS-84. The change in blowing agent affected only mechanically applied foam. Foam that is hand-sprayed, such as on the bipod ramp, is still applied using CFC-11. The Program Requirements Control Board issued a directive, and the external tank project was assigned an in-flight anomaly to address the intertank thrust panel foam loss. Over the course of 9 missions, the external tank project first reduced the thickness of the foam on the thrust panels to minimize the amount of foam that could be shed, and due to a misunderstanding of what caused foam loss at that time, put vent holes in the thrust panel foam to relieve trapped gas pressure. The in-flight anomaly remained open during these changes, and foam shedding occurred on the 9 missions that tested the corrective actions. Following STS-101, the 10th mission after STS-87, the Program Requirements Control Board concluded that foam shedding from the thrust panel had been reduced to an acceptable level by sanding and venting, and the in-flight anomaly was closed. The Orbiter Project, External Tank Project, and Space Shuttle Program Management all accepted this rationale without question. The board notes that these interventions merely reduced foam shedding to previously experienced levels, which have remained relatively constant over the shuttle's lifetime. Making the orbiter more resistant to debris strikes. If foam shedding could not be prevented entirely, what did NASA do to make the thermal protection system more resistant to debris strikes? A 1990 study by Dr. Elizabeth Pate-Cornell and Paul Fischbach attempted to quantify the risk of a thermal protection system failure using probabilistic analysis. The data they used included 1. The probability that a tile would become debonded by either debris strikes or a poor bond, 2. The probability of then losing adjacent tiles, 3. Depending on the final size of the failed area, the probability of a burn-through, and 4. The probability of failure of a critical subsystem if burn-through occurs. The study concluded that the probability of losing an orbiter on any given mission due to a failure of thermal protection system tiles was approximately 1 in 1,000. Debris-related problems accounted for approximately 40% of the probability, while 60% was attributable to tile debonding caused by other factors. An estimated 85% of the risk could be attributed to 15% of the acreage, or larger areas of tile, meaning that the loss of any one of a relatively small number of tiles posed a relatively large amount of risk to the orbiter. In other words, not all tiles are equal. Losing certain tiles is more dangerous. While the actual risk may be different than that computed in the 1990 study due to the limited amount of data and the underlying simplified assumptions, this type of analysis offers insight that enables management to concentrate their resources on protecting the orbiter's critical areas. 2 years after the conclusion of that study, NASA wrote to Pate-Cornell and Fischbach, describing the importance of their work, and stated that it was developing a long-term effort to use probabilistic risk assessment and related disciplines to improve programmatic decisions. Though NASA has taken some measures to invest in probabilistic risk assessment as a tool, it is the board's view that NASA has not fully exploited the insights that Pate-Cornell's and Fischbach's work offered. Impact-resistant tile. NASA also evaluated the possibility of increasing thermal protection system tile resistance to debris hits, lowering the possibility of tile debonding, and reducing tile production and maintenance costs. Indeed, tiles with a tough coating are currently used on the orbiters. This coating, known as toughened unipiece fibrous insulation, or TUFI, was patented in 1992 and developed for use on high-temperature rigid insulation. TUFI is used on a tile material known as Alumina Enhanced Thermal Barrier, AETB, and has a debris impact resistance that is greater than the current acreage tile's resistance by a factor of approximately 6 to 20. At least 772 of these advanced tiles have been installed on the orbiter's base heat shields and upper body flaps. However, due to its higher thermal conductivity, tufi-coated AETB cannot be used as a replacement for the larger areas of tile coverage. Boeing, Lockheed Martin, and NASA are developing a lightweight, impact-resistant, low-conductivity tile. Because the impact requirements for these next-generation tiles do not appear to be based on resistance to specific and probable damage sources, it is the board's view that certification of the new tile will not adequately address the threat posed by debris. Conclusion. Despite original design requirements that the external tank not shed debris, and the corresponding design requirement that the orbiter not receive debris hits exceeding a trivial amount of force, debris has impacted the shuttle on each flight. Over the course of 113 missions, foam shedding and other debris impacts came to be regarded more as a turnaround or maintenance issue, and less as a hazard to the vehicle and crew. Assessments of foam shedding and strikes were not thoroughly substantiated by engineering analysis, and the process for closing in-flight anomalies is not well documented and appears to vary. Shuttle program managers appear to have confused the notion of foam posing an accepted risk with foam not being a safety of flight issue. At times, the pressure to meet flight schedule appeared to cut short engineering efforts to resolve the foam shedding problem. NASA's lack of understanding of foam properties and behavior must also be questioned. Although tests were conducted to develop and qualify foam for use on the external tank, it appears there were large gaps in NASA's knowledge about this complex and variable material. Recent testing conducted at Marshall Space Flight Center and under the auspices of the board indicate that mechanisms previously considered a prime source of foam loss, cryopumping and cryoingestion, are not feasible in the conditions experienced during tanking, launch, and ascent. Also, dissections of foam bipod ramps on external tanks yet to be launched reveal subsurface flaws and defects that only now are being discovered and identified as contributing to the loss of foam from the bipod ramps. While NASA properly designated key debris events as in-flight anomalies in the past, more recent events indicate that NASA engineers and management did not appreciate the scope or lack of scope of the hazard reports involving foam shedding. Ultimately, NASA's hazard analyses, which were based on reducing or eliminating foam shedding, were not succeeding. Shuttle program management made no adjustments to the analyses to recognize this fact. The acceptance of events that are not supposed to happen has been described by sociologist Diane Vaughan as the normalization of deviance. The history of foam problem decisions shows how NASA first began and then continued flying with foam losses, so that flying with these deviations from design specifications was viewed as normal and acceptable. Dr. Richard Feynman, a member of the Presidential Commission on the Space Shuttle Challenger accident, discusses this phenomenon in the context of the Challenger accident. The parallels are striking. The phenomenon of accepting flight seals that had shown erosion and blow-by in previous flights is very clear. The Challenger flight is an excellent example. There are several references to flights that had gone before. The acceptance and success of these flights is taken as evidence of safety. But erosions and blow-by are not what the design expected. They are warnings that something is wrong. The O-rings of the solid rocket booster were not designed to erode. Erosion was a clue that something was wrong. Erosion was not something from which safety can be inferred. If a reasonable launch schedule is to be maintained, engineering often cannot be done fast enough to keep up with the expectations of originally conservative certification criteria designed to guarantee a very safe vehicle. In these situations, subtly and often with apparently logical arguments, the criteria are altered so that flights may still be certified in time. They therefore fly in a relatively unsafe condition with a chance of failure on the order of 1%. It is difficult to be more accurate. Findings. F 6.1-1. NASA has not followed its own rules and requirements on foam shedding. Although the agency continuously worked on the foam shedding problem, the debris impact requirements have not been met on any mission. F 6.1-2. Foam shedding, which had initially raised serious safety concerns, evolved into an in-family or no safety of flight event and were deemed an accepted risk. F 6.1-3. 5 of the 7 bipod ramp events occurred on missions flown by Columbia, a seemingly high number. This observation is likely due to Columbia having been equipped with umbilical cameras earlier than the other orbiters. F 6.1-4. There is lack of effective processes for feedback or integration among project elements in the resolution of in-flight anomalies. F 6.1-5. Foam bipod debris shedding incidents on STS-52 and STS-62 were undetected at the time they occurred and were not discovered until the board directed NASA to examine external tank separation images more closely. F 6.1-6. Foam bipod debris shedding events were classified as in-flight anomalies up until STS-112, which was the first known bipod foam shedding event not classified as an in-flight anomaly. F 6.1-7. The STS-112 assignment for the external tank project to identify the cause and corrective action of the bipod ramp foam loss event was not due until after the planned launch of STS-113, and then slipped to after the launch of STS-107. F 6.1-8. No external tank configuration changes were made after the bipod foam loss on STS-112. F 6.1-9. Although it is sometimes possible to obtain imagery of night launches because of light provided by the solid rocket motor plume, no imagery was obtained for STS-113. F 6.1-10. NASA failed to adequately perform trend analysis on foam losses. This greatly hampered the agency's ability to make informed decisions about foam losses. F 6.1-11. Despite the constant shedding of foam, the shuttle program did little to harden the orbiter against foam impacts through upgrades to the thermal protection system. Without impact resistance and strength requirements that are calibrated to the energy of the debris likely to impact the orbiter, certification of new thermal protection system tile will not adequately address the threat posed by debris. Recommendations. None. End of Section 22. Recording by Maria Kasper. Section 23 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6C. Decision-Making by NASA, Part 3. 6.2. Schedule Pressure. Countdown to Space Station Core Complete. A Workforce Under Pressure. During the course of this investigation, the board received several unsolicited comments from NASA personnel regarding pressure to meet a schedule. These comments all concerned a date more than a year after the launch of Columbia that seemed etched in stone, February 19, 2004, the scheduled launch date of STS-120. This flight was a milestone in the minds of NASA management, since it would carry a section of the International Space Station called Node 2. This would configure the International Space Station to its U.S. Core Complete status. At first glance, the Core Complete configuration date seemed noteworthy but unrelated to the Columbia accident. However, as the investigation continued, it became apparent that the complexity and political mandates surrounding the International Space Station program, as well as shuttle program management's responses to them, resulted in pressure to meet an increasingly ambitious launch schedule. In mid-2001, NASA adopted plans to make the over-budget and behind-schedule International Space Station credible to the White House and Congress. The space station program and NASA were on probation and had to prove they could meet schedules and budgets. The plan to regain credibility focused on the February 19, 2004 date for the launch of Node 2 and the resultant Core Complete status. If this goal was not met, NASA would risk losing support from the White House and Congress for subsequent space station growth. By the late summer of 2002, a variety of problems caused space station assembly work and shuttle flights to slip beyond their target dates. With the Node 2 launch endpoint fixed, these delays caused the schedule to become ever more compressed. Meeting U.S. Core Complete by February 19, 2004, would require preparing and launching 10 flights in less than 16 months. With the focus on retaining support for the space station program, little attention was paid to the effects the aggressive Node 2 launch date would have on the shuttle program. After years of downsizing and budget cuts, Chapter 5, this mandate and events in the months leading up to STS-107 introduced elements of risk to the program. Columbia and the STS-107 crew, who had seen numerous launch slips due to missions that were deemed higher priorities, were further affected by the mandatory Core Complete date. The high-pressure environments created by NASA headquarters unquestionably affected Columbia, even though it was not flying to the International Space Station. February 19, 2004. A line in the sand. Schedules are essential tools that help large organizations effectively manage their resources. Aggressive schedules, by themselves, are often a sign of a healthy institution. However, other institutional goals, such as safety, sometimes compete with schedules, so the effects of schedule pressure in an organization must be carefully monitored. The board posed the question, was there undue pressure to nail the Node 2 launch date to the February 19, 2004 signpost? The management and workforce of the shuttle and space station programs each answered the question differently. Various members of NASA upper management gave a definite no. In contrast, the workforce within both programs thought there was considerable management focus on Node 2 and resulting pressure to hold firm to that launch date, and individuals were becoming concerned that safety might be compromised. The weight of evidence supports the workforce view. Employees attributed the Node 2 launch date to the new administrator, Sean O'Keefe, who was appointed to execute a space station management plan he had proposed as Deputy Director of the White House Office of Management and Budget. They understood the scrutiny that NASA, the new administrator, and the space station program were under, but now it seemed to some that budget and schedule were of paramount concern. As one employee reflected, "I guess my frustration was, I know the importance of showing that you manage your budget, and that's an important impression to make to Congress so you can continue the future of the agency. But to a lot of people, February 19th just seemed like an arbitrary date. It doesn't make sense to me why at all costs we were marching to this date. The importance of this date was stressed from the very top. The Space Shuttle and Space Station program managers briefed the new NASA administrator monthly on the status of their programs, and a significant part of those briefings was the days of margin remaining in a schedule to the launch of Node 2, still well over a year away. The Node 2 schedule margin typically accounted for more than half of the briefing slides. Figure 6.2-1 is one of the charts presented by the Shuttle Program Manager to the NASA Administrator in December 2002. The chart shows how the days of margin in the existing schedule were being managed to meet the requirement of a Node 2 launch on the prescribed date. The triangles are events that affected the schedule, such as the slip of a Russian Soyuz flight. The squares indicate actions taken by management to regain the lost time, such as authorizing work over the 2002 winter holidays. Figure 6.2-2 shows a slide from the International Space Station Program Manager's portion of the briefing. It indicates that International Space Station Program Management was also taking actions to regain the margin. Over the months, the extent of some testing at Kennedy was reduced, the number of tasks done in parallel was increased, and a third shift of workers would be added in 2003 to accomplish the processing. These charts illustrate that both the Space Shuttle and the Space Station programs were being managed to a particular launch date, February 19, 2004. Days of margin in that schedule were one of the principal metrics by which both programs came to be judged. NASA headquarters stressed the importance of this date in other ways. A screensaver, see Figure 6.2-3, was mailed to managers in NASA's human spaceflight program that depicted a clock counting down to February 19, 2004, U.S. core complete. While employees found this amusing because they saw it as a date that could not be met, it also reinforced the message that NASA headquarters was focused on and promoting the achievement of that date. This schedule was on the minds of the shuttle managers in the months leading up to STS-107. The background: schedule complexity and compression. In 2001, the International Space Station Cost and Management Evaluation Task Force report recommended as a cost-saving measure a limit of 4 shuttle flights to the International Space Station per year. To meet this requirement, managers began adjusting the shuttle and station manifests to get back in the budget box. They rearranged the station assembly sequences, moving some elements forward and taking others out. When all was said and done, the launch of STS-120, which would carry Node 2 to the International Space Station, fell on February 19, 2004. The core complete date simply emerged from this planning effort in 2001. By all accounts, it was a realistic and achievable date when first approved. At that time, there was more concern that 4 shuttle flights a year would limit the capability to carry supplies to and from the space station, to rotate its crew, and to transport remaining space station segments and equipment. Still, managers felt it was a reasonable goal, and assumed that if circumstances warranted a slip of that date, it would be granted. Shuttle and station managers worked diligently to meet the schedule. Events gradually ate away at the schedule margin. Unlike the old days before the station-shuttle partnership created problems that had a ripple effect on both programs' manifests. As one employee described it, the serial nature of having to fly space station assembly missions in a specific order made staying on schedule more challenging. Before the space station, if a shuttle flight had to slip, it would. Other missions that had originally followed it could be launched in the meantime. Missions could be flown in any sequence. Now the manifests were a delicate balancing act. Missions had to be flown in a certain order and were constrained by the availability of the launch site, the Russian Soyuz and Progress schedules, and a myriad of other processes. As a result, employees stated they were now experiencing a new kind of pressure. Any necessary change they made on one mission was now impacting future launch dates. They had a sense of being under the gun. Shuttle and station program personnel ended up with manifests that one employee described as changing all the time. One of the biggest issues they faced entering 2002 was up mass, the amount of cargo the shuttle can carry to the station. Up mass was not a new problem, but when the shuttle flight rate was reduced to 4 per year, up mass became critical. Working groups were actively evaluating options in the summer of 2002 and bartering to get each flight to function as expected. Sometimes the up mass being traded was actual space station crew members. A crew rotation, planned for STS-118, was moved to a later flight because STS-118 was needed for other cargo. This resulted in an increase of the crew's duration on the space station, which was creeping past the 180-day limit agreed to by the astronaut office, flight surgeons, and Space Station International partners. A space station worker described how this one change created many other problems, and added, "We had a train wreck coming." Future on-orbit crew time was being projected at 205 days or longer to maintain the assembly sequence and meet the schedule. By July 2002, the shuttle and space station programs were facing a schedule with very little margin. 2 setbacks occurred when technical problems were found during routine maintenance on Discovery. STS-107 was 4 weeks away from launch at the time, but the problems grounded the entire shuttle fleet. The longer the fleet was grounded, the more shuttle margin was lost, which further compounded the complexity of the intertwined shuttle and station schedules. As one worker described the situation, "A 1-week hit on a particular launch can start a steamroll effect, including all the constraints, and by the time you get out of here, that 1-week slip has turned into a couple of months." In August 2002, the shuttle program realized it would be unable to meet the space station schedule with the available shuttles. Columbia had never been outfitted to make a space station flight, so the other 3 orbiters flew the station missions. But Discovery was in its orbiter maintenance down period and would not be available for another 17 months. All space station flights until then would have to be made by Atlantis and Endeavour. As managers looked ahead to 2003, they saw that after STS-107, these 2 orbiters would have to alternate flying 5 consecutive missions, STS-114 through STS-118. To alleviate this pressure and regain their schedule margin, shuttle program managers elected to modify Columbia to enable it to fly space station missions. These modifications were to take place immediately after STS-107, so that Columbia would be ready to fly its first space station mission 8 months later. This decision put Columbia directly in the path of core complete. As the autumn of 2002 began, both the Space Shuttle and Space Station programs began to use what some employees termed tricks to regain their schedule margin. Employees expressed concern that their ability to gain schedule margin using existing measures was waning. In September 2002, it was clear to Space Shuttle and Space Station program managers that they were not going to meet the schedule as it was laid out. The 2 programs proposed a new set of launch dates, documented in an email, that included moving STS-120, the Node 2 flight, to mid-March 2004. Note that the first paragraph ends with, "The 10A U.S. Core Complete Node 2 launch remains February 19, 2004. These launch date changes made it possible to meet the early part of the schedule, but compressed the late 2003, early 2004 schedule even further. This did not make sense to many in the program. One described the system as at an uncomfortable point, noted having to go to great lengths to reduce vehicle processing time at Kennedy, and added, "I don't know what Congress communicated to O'Keefe. I don't really understand the criticality of February 19th, that if we didn't make that date, did that mean the end of NASA? I don't know. I would like to think that the technical issues and safely resolving the technical issues can take priority over any budget issue or scheduling issue." When the shuttle fleet was cleared to return to flight, attention turned to STS-112, STS-113, and STS-107, set for October, November, and January. Workers were uncomfortable with the rapid sequence of flights. The thing that was beginning to concern me is I wasn't convinced that people were being given enough time to work the problems correctly. The problems that had grounded the fleet had been handled well, but the program nevertheless lost the rest of its margin. As the pressure to keep to the Node 2 schedule continued, some were concerned that this might influence the future handling of problems. One worker expressed the concern, and I have to think that subconsciously, that even though you don't want it to affect decision-making, it probably does. This was the environment for October and November of 2002. During this time, a bipod foam event occurred on STS-112. For the first time in the history of the shuttle program, the Program Requirements Control Board chose to classify that bipod foam loss as an action rather than as a more serious in-flight anomaly. At the STS-113 Flight Readiness Review, managers accepted with little question the rationale that it was safe to fly with the known foam problem. The operations tempo following STS-107. After STS-107, the tempo was only going to increase. The vehicle processing schedules, training schedules, and mission control flight staffing assignments were all overburdened. The vehicle processing schedule for flights from February 2003 through February 2004 was optimistic. The schedule could not be met with only 2 shifts of workers per day. In late 2002, NASA headquarters approved plans to hire a 3rd shift. There were 4 shuttle launches to the space station scheduled for the 5 months from October 2003 through the launch of Node 2 in February 2004. To put this in perspective, the launch rate in 1985, for which NASA was criticized by the Rogers Commission, was 9 flights in 12 months, and that was accomplished with 4 orbiters and a manifest that was not complicated by a space station assembly. Endeavour was the orbiter on the critical path. Figure 6.2-4 shows the schedule margin for STS-115, STS-117, and STS-120, the Node 2 flight. To preserve the margin going into 2003, the vehicle processing team would be required to work the late 2002, early 2003 winter holidays. The 3rd shift of workers at Kennedy would be available in March 2003 and would buy 8 more days of margin for STS-117 and STS-120. The workforce would likely have to work on the 2003 winter holidays to meet the Node 2 date. Figure 6.2-5 shows the margin for each vehicle. Discovery, OV-103, was in extended maintenance. The large boxes indicate the margin to critical path, that is to Node 2 launch date. The 3 smaller boxes underneath indicate, from left to right, the vehicle processing margin, holiday margin, and Dryden margin. The vehicle processing margin indicates how many days there are in addition to the days required for that mission's vehicle processing. Endeavour, OV-105, had 0 days of margin for the processing flows for STS-115, STS-117, and STS-120. The holiday margin is the number of days that could be gained by working holidays. The Dryden margin is the 6 days that are always reserved to accommodate an orbiter landing at Edwards Air Force Base in California and having to be ferried to Kennedy. If the orbiter landed at Kennedy, those 6 days would automatically be regained. Note that the Dryden margin had already been surrendered in the STS-114 and STS-115 schedules. If bad weather at Kennedy forced those 2 flights to land at Edwards, the schedule would be directly affected. The clear message in these charts is that any technical problem that resulted in a slip to one launch would now directly affect the Node 2 launch. The lack of housing for the orbiters was becoming a factor as well. Prior to launch, an orbiter can be placed in an orbiter processing facility, the vehicle assembly building, or on one of the 2 shuttle launch pads. Maintenance and refurbishment is performed in the 3 orbiter processing facilities at Kennedy. One of these was occupied by Discovery during its scheduled extended maintenance. This left 2 to serve the other 3 orbiters over the next several months. The 2003 schedule indicated plans to move Columbia, after its return from STS-107, from an orbiter processing facility to the vehicle assembly building and back several times in order to make room for Atlantis, OV-104, and Endeavour, OV-105, and prepare them for missions. Moving an orbiter is tedious, time-consuming, carefully orchestrated work. Each move introduces an opportunity for problems. Those 2003 moves were often slated to occur without a single day of margin between them, another indication of the additional risks that managers were willing to incur to meet the schedule. The effect of the compressed schedule was also evident in the Mission Operations Directorate. The plans for flight controller staffing of Mission Control showed that of the 7 flight controllers who lacked current certifications during STS-107, see Chapter 4, 5 were scheduled to work the next mission, and 3 were scheduled to work the next 3 missions, STS-114, 115, and 116. These controllers would have been constantly either supporting missions or supporting mission training, and were unlikely to have the time to complete their recertification requirements. With the pressure of the schedule, the things perceived to be less important, like recertification, which was not done before STS-107, would likely continue to be deferred. As a result of the schedule pressure, managers either were willing to delay recertification or were too busy to notice that deadlines for recertification had passed. Columbia, caught in the middle. STS-112 flew in October 2002. At 33 seconds into flight, a piece of the bipod foam from the external tank struck one of the solid rocket boosters. As described in Section 6.1, the STS-112 foam strike was discussed at the Program Requirements Control Board following the flight. Although the initial recommendation was to treat the foam loss as an in-flight anomaly, the shuttle program instead assigned it as an action, with a due date after the next launch. This was the first instance of bipod foam loss that was not designated an in-flight anomaly. The action was noted at the STS-113 Flight Readiness Review. Those Flight Readiness Review charts, see Section 6.1, provided a flawed flight rationale by concluding that the foam loss was not a safety of flight issue. Interestingly, during Columbia's mission, the chair of the mission management team, Linda Ham, would characterize that reasoning as lousy, though neither she nor shuttle program manager Ron Ditmore, who were both present at the meeting, questioned it at the time. The pressing need to launch STS-113 to retrieve the International Space Station Expedition 5 crew before they surpassed the 180-day limit, and to continue the countdown to Node 2, were surely in the back of managers' minds during these reviews. By December 2002, every bit of padding in the schedule had disappeared. Another chart from the shuttle and station program manager's briefing to the NASA administrator summarizes the schedule dilemma. See Figure 6.2-6. Summary. Critical path to U.S. core complete driven by shuttle launch. Program station assessment up to 14 days late. Program shuttle assessment up to 45 days late. Program proactively managing schedule threats. Most probable launch date is March 19th through April 19th. Program target remains February 19th, 2004. Even with work scheduled on holidays, a third shift of workers being hired and trained, future crew rotations drifting beyond 180 days, and some tests previously deemed requirements being skipped or deferred, program managers estimated that Node 2 launch would be 1 to 2 months late. They were slowly accepting additional risk in trying to meet a schedule that probably could not be met. Interviews with workers provided insight into how this situation occurred. They noted that people who work at NASA have the legendary can-do attitude, which contributes to the agency's successes, but it can also cause problems. When workers are asked to find days of margin, they work furiously to do so and are praised for each extra day they find. But those same people and this same culture have difficulty admitting that something can't or shouldn't be done, and that the margin has been cut too much or that resources are being stretched too thin. No one at NASA wants to be the one to stand up and say, "We can't make that date." STS-107 was launched on January 16, 2003. Bipod foam separated from the external tank and struck Columbia's left wing 81.9 seconds after liftoff. As the mission proceeded over the next 16 days, critical decisions about that event would be made. The STS-107 Mission Management Team Chair, Linda Ham, had been present at the Program Requirements Control Board discussing the STS-112 foam loss and the STS-113 Flight Readiness Review. So had many of the other shuttle program managers who had roles in STS-107. Ham was also the Launch Integration Manager for the next mission, STS-114. In that capacity, she would chair many of the meetings leading up to the launch of that flight, and many of those individuals would have to confront Columbia's foam strike and its possible impact on the launch of STS-114. Would the Columbia foam strike be classified as an in-flight anomaly? Would the fact that foam had detached from the bipod ramp on 2 out of the last 3 flights have made this problem a constraint to flight which would need to be solved before the next launch? Could the program develop a solid rationale to fly STS-114, or would additional analysis be required to clear that flight for launch? Original message from Ham, Linda J., sent Wednesday, January 22, 2003, 10:16 a.m. to Ditmore, Ronald D. Subject, External Tank Briefing, STS-112 Foam Loss. Yes, I remember. It was not good. I told Jerry to address it at the Orbiter Rollout Review next Tuesday, even though he won't have any more data, and it doesn't really impact Orbiter roll to the Vehicle Assembly Building. I just want him to be thinking hard about this now, not wait until in-flight anomaly review to get a formal action. In fact, most of Linda Ham's inquiries about the foam strike were not to determine what action to take during Columbia's mission, but to understand the implications for STS-114. During a mission management team meeting on January 21st, she asked about the rationale put forward at the STS-113 Flight Readiness Review which she had attended. Later that morning, she reviewed the charts presented at that Flight Readiness Review. Her assessment, which she emailed to Shuttle Program Manager Ron Ditmore on January 21st, was, rationale was lousy then and still is. See Section 6.3 for that email. One of Ham's STS-114 duties was to chair a review to determine if the mission's orbiter, Atlantis, should be rolled from the orbiter processing facility to the vehicle assembly building per its pre-launch schedule. In the above email to Ron Ditmore, Ham indicates a desire to have the same individual responsible for the lousy STS-113 flight rationale start working on the foam shedding issue and presumably present a new flight rationale very soon. As STS-107 prepared for re-entry, shuttle program managers prepared for STS-114 flight rationale by arranging to have post-flight photographs taken of Columbia's left wing rushed to Johnson Space Center for analysis. As will become clear in the next section, most of the shuttle program's concern about the Columbia foam strike were not about the threat it might pose to the vehicle in orbit, but about the threat it might pose to the schedule. Conclusion. The agency's commitment to hold firm to a February 19, 2004 launch date for Node 2 influenced many of the decisions in the months leading up to the launch of STS-107, and may well have subtly influenced the way managers handled the STS-112 foam strike and Columbia's as well. When a program agrees to spend less money or accelerate a schedule beyond what the engineers and program managers think is reasonable, a small amount of overall risk is added. These little pieces of risk add up until managers are no longer aware of the total program risk and are, in fact, gambling. Little by little, NASA was accepting more and more risk in order to stay on schedule. Findings. F6.2-1. NASA headquarters focus was on the Node 2 launch date, February 19, 2004. F6.2-2. The intertwined nature of the Space Shuttle and Space Station programs significantly increased the complexity of the schedule and made meeting the schedule far more challenging. F6.2-3. The capabilities of the system were being stretched to the limit to support the schedule. Projections into 2003 showed stress on vehicle processing at the Kennedy Space Center, on flight controller training at Johnson Space Center, and on space station crew rotation schedules. Effects of this stress included neglecting flight controllers' recertification requirements, extending crew rotation schedules, and adding incremental risk by scheduling additional orbiter movement at Kennedy. F6.2-4. The 4 flights scheduled in the 5 months from October 2003 to February 2004 would have required a processing effort comparable to the effort immediately before the Challenger accident. F6.2-5. There was no schedule margin to accommodate unforeseen problems. When flights come in rapid succession, there is no assurance that anomalies on one flight will be identified and appropriately addressed before the next flight. F6.2-6. The environment of the countdown to Node 2 and the importance of maintaining the schedule may have begun to influence managers' decisions, including those made about the STS-112 foam strike. F6.2-7. During STS-107, shuttle program managers were concerned with the foam strike's possible effect on the launch schedule. Recommendation. R6.2-1. Adopt and maintain a shuttle flight schedule that is consistent with available resources. Although schedule deadlines are an important management tool, those deadlines must be regularly reevaluated to ensure that any additional risk incurred to meet the schedule is recognized, understood, and acceptable. End of section 23. Recording by Maria Kasper. Section 24 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6D, Decision-Making at NASA, Part 4. 6.3. Decision-Making During the Flight of STS-107. Initial Foam Strike Identification. As soon as Columbia reached orbit on the morning of January 16, 2003, NASA's Intercenter Photo Working Group began reviewing liftoff imagery by video and film cameras on the launch pad and at other sites at and nearby the Kennedy Space Center. The debris strike was not seen during the first review of video imagery by tracking cameras, but it was noticed at 9:30 a.m. Eastern Standard Time the next day, Flight Day 2, by Intercenter Photo Working Group engineers at Marshall Space Flight Center. Within an hour, Intercenter Photo Working Group personnel at Kennedy also identified the strike on higher-resolution film images that had just been developed. The images revealed that a large piece of debris from the left bipod area of the external tank had struck the orbiter's left wing. Because the resulting shower of post-impact fragments could not be seen passing over the top of the wing, analysts concluded that the debris had apparently impacted the left wing below the leading edge. Intercenter Photo Working Group members were concerned about the size of the object and the apparent momentum of the strike. In searching for better views, Intercenter Photo Working Group members realized that none of the other cameras provided a higher quality view of the impact and the potential damage to the orbiter. Of the dozen ground-based camera sites used to obtain images of the ascent for engineering analyses, each of which has film and video cameras, 5 are designed to track the shuttle from liftoff until it is out of view. Due to expected angle of view and atmospheric limitations, 2 sites did not capture the debris event. Of the remaining 3 sites, positioned to see at least a portion of the event, none provided a clear view of the actual debris impact to the wing. The first site lost track of Columbia on ascent, the second site was out of focus because of an improperly maintained lens, and the third site captured only a view of the upper side of Columbia's left wing. The board notes that camera problems also hindered the Challenger investigation. Over the years, it appears that due to budget and camera team staff cuts, NASA's ability to track ascending shuttles has atrophied, a development that reflects NASA's disregard of the developmental nature of the shuttle's technology. See Recommendation R 3.4-1. Because they had no sufficiently resolved pictures with which to determine potential damage, and having never seen such a large piece of debris strike the orbiter so late in ascent, Intercenter Photo Working Group members decided to ask for ground-based imagery of Columbia. Imagery Request 1. To accomplish this, the Intercenter Photo Working Group's chair, Bob Page, contacted Wayne Hale, the shuttle program manager for launch integration at Kennedy Space Center, to request imagery of Columbia's left wing on orbit. Hale, who agreed to explore the possibility, holds a top-secret clearance and was familiar with the process for requesting military imaging from his experience as a mission control flight director. This would be the first of 3 discrete requests for imagery by a NASA engineer or manager. In addition to these 3 requests, there were, by the board's count, at least 8 missed opportunities where actions may have resulted in the discovery of debris damage. Shortly after confirming the debris hit, Intercenter Working Group members distributed an L+1, Launch plus 1 day report, and digitized clips of the strike via email throughout the NASA and contractor communities. This report provided the initial view of the foam strike and served as the basis for subsequent decisions and actions. Mission Management's response to the foam strike. As soon as the Intercenter Working Group report was distributed, engineers and technical managers from NASA, United Space Alliance, and Boeing began responding. Engineers and managers from Kennedy Space Center called engineers and program managers at Johnson Space Center. United Space Alliance and Boeing employees exchanged emails with details of the initial film analysis and the work in progress to determine the result of the impact. Details of the strike, actions taken in response to the impact, and records of telephone conversations were documented in the Mission Control Operational Log. The following section recounts in chronological order many of these exchanges and provides insight into why, in spite of the debris strike's severity, NASA managers ultimately declined to request images of Columbia's left wing on orbit. Flight Day 2, January 17, 2003. In the Mission Evaluation Room, a support function of the Shuttle Program Office that supplies engineering expertise for missions in progress, a set of consoles are staffed by engineers and technical managers from NASA and contractor organizations. For record-keeping, each Mission Evaluation Room member types mission-related comments into a running log. A log entry by a Mission Evaluation Room manager at 10:58 a.m. Central Standard Time noted that the vehicle may have sustained damage from a debris strike. John Disler, a Photolab engineer at Johnson Space Center, called to report a debris hit on the vehicle. The debris appears to originate from the external tank forward bipod area, travels down the left side, and hits the left wing leading edge near the fuselage. The launch video review team at Kennedy Space Center think that the vehicle may have been damaged by the impact. Bill Reeves and Mike Stoner, United Space Alliance Subsystem Area Manager, were notified. At 3:15 p.m., Bob Page, chair of the Intercenter Photo Working Group, contacted Wayne Hale, the Shuttle Program Manager for Launch Integration at Kennedy Space Center, and Lambert Austin, the head of the Space Shuttle Systems Integration at Johnson Space Center, to inform them that Boeing was performing an analysis to determine trajectories, velocities, angles, and energies for the debris impact. Page also stated that photo analysis would continue over the Martin Luther King Jr. holiday weekend as additional film from tracking cameras was developed. Shortly thereafter, Wayne Hale telephoned Linda Ham, chair of the Mission Management Team, and Ron Ditmore, Space Shuttle Program Manager, to pass along information about the debris strike and to let them know that a formal report would be issued at the end of the day. John Disler, a member of the Intercenter Photo Working Group, notified the Mission Evaluation Room manager that a newly formed group of analysts, to be known as the Debris Assessment Team, needed the entire weekend to conduct a more thorough analysis. Meanwhile, early opinions about reinforced carbon-carbon (RCC) resiliency were circulated via email between United Space Alliance technical managers and NASA engineers, which may have contributed to a mindset that foam hitting the RCC was not a concern. Original message from Stoner 1 Michael D., sent Friday, January 17, 2003, 4:03 p.m., to Woodworth Warren H., Reeves William D., copied to Wilder James, White Doug, Bittner Barbara K., Blank Donald E., Cooper Kurt W., Gordon Michael P. Subject, STS-107 debris. Just spoke with Calvin and Mike Gordon, reinforced carbon-carbon subsystem manager, about the impact. Basically, the RCC is extremely resilient to impact-type damage. The piece of debris, most likely foam or ice, looked like it most likely impacted the wing leading edge RCC and broke apart. It didn't look like a big enough piece to pose any serious threat to the system, and Mike Gordon, the RCC subsystem manager, concurs. At T plus 81 seconds, the piece wouldn't have had enough energy to create a large damage to the RCC wing leading edge system. Plus, they have analysis that says they have a single mission safe re-entry in case of impact that penetrates the system. As far as the tiles go in the wing leading edge area, they are thicker than required, taper in the outer mold line, and can handle a large area of shallow damage, which is what this event most likely would have caused. They have impact data that says the structure would get slightly hotter but still be okay. Mike Stoner, USA Thermal Protection System Subsystem Area Manager. Engineering coordination at NASA and United Space Alliance. After United Space Alliance became contractually responsible for most aspects of shuttle operations, NASA developed procedures to ensure that its own engineering expertise was coordinated with that of contractors for any out-of-family issue. In the case of the foam strike on STS-107, which was classified as out-of-family, clearly defined written guidance led United Space Alliance technical managers to liaise with their NASA counterparts. Once NASA managers were officially notified of the foam strike classification, and NASA engineers joined their contractor peers in the early analysis, the resultant group should, according to standing procedures, become a Mission Evaluation Room Tiger Team. Tiger Teams have clearly defined roles and responsibilities. Instead, the group of analysts came to be called a Debris Assessment Team. While they were the right group of engineers, working the problem at the right time, by not being classified as a Tiger Team, they did not fall under the shuttle program procedures described in Tiger Team checklists, and as a result, they were not owned or led by shuttle program managers. This left the Debris Assessment Team in a kind of organizational limbo, with no guidance except the date by which program managers expected to hear their results, January 24th. Already by Friday afternoon, shuttle program managers and working engineers had different levels of concern about what the foam strike might have meant. After reviewing available film, Inter-Center Photo Working Group engineers believed the orbiter may have been damaged by the strike. They wanted on-orbit images of Columbia's left wing to confirm their suspicions, and initiated action to obtain them. Boeing and United Space Alliance engineers decided to work through the holiday weekend to analyze the strike. At the same time, high-level managers, Ralph Rowe, head of the Space Program Office of Vehicle Engineering, and Bill Reeves from United Space Alliance, voiced a lower level of concern. It was at this point, before any analysis had started, that shuttle program managers officially shared their belief that the strike posed no safety issues and that there was no need for a review to be conducted over the weekend. The following is a 4:28 p.m. Mission Evaluation Room manager log entry. Bill Reeves called, after a meeting with Ralph Rowe, "It is confirmed that USA Boeing will not work the debris issue over the weekend, but will wait till Monday when the films are released. The launch commit criteria constraints on ice, the energy speed of impact at plus 81 seconds, and the toughness of the reinforced carbon-carbon are two main factors for the low concern. Also, analysis supports single-mission safe re-entry for an impact that penetrates the system." The following is a 4:37 p.m. Mission Evaluation Room manager log entry. Bob Page told Mission Evaluation Room that Kennedy Space Center Thermal Protection System engineers were sent by USA Subsystem Area Manager Woody Woodworth to review the video and films, indicated that Page had said that Woody had said this was an action from the Mission Evaluation Room to work this issue, and a possible early landing on Tuesday. Mission Evaluation Room manager told Bob that no official action was given by USA or Boeing, and they had no concern about landing early. Woody indicated that the Thermal Protection System engineers at Kennedy Space Center have been turned away from reviewing the films. It was stated that the film reviews wouldn't be finished till Monday. The Mission Evaluation Room manager also wrote, "I also confirmed that there was no rush on this issue and that it was okay to wait till the film reviews are finished on Monday to do a thermal protection system review. In addition to individual log entries by Mission Evaluation Room members, managers prepared handover notes for delivery from one working shift to the next. Handovers from Shift 1 to 2 on January 17th included the following entry under the problem category. Dissler report. Debris impact on port wing edge appears to have originated at the external tank forward bipod. Foam? If so, it shouldn't be a problem. Video link will be available on the web soon. We'll look at high-speed film today. Shortly after these entries were made, the deputy manager of Johnson Space Center Shuttle Engineering notified Rodney Rocha, NASA's designated chief engineer for the thermal protection system, of the strike and the approximate debris size. It was Rocha's responsibility to coordinate NASA engineering resources and work with contract engineers at United Space Alliance, who together would form a debris assessment team that would be co-chaired by United Space Alliance Engineering Manager Pam Madeira. The United Space Alliance Deputy Manager of Shuttle Engineering signaled that the debris strike was initially classified as out of family and therefore of greater concern than previous debris strikes. At about the same time, the Intercenter Photo Working Group's L+1 report, containing both video clips and still images of the debris strike, was emailed to engineers and technical managers both inside and outside of NASA. Flight days 3 and 4, Saturday and Sunday, January 18th and 19th, 2003. Though senior United Space Alliance manager Bill Reeves had told Mission Evaluation Room personnel that the debris problem would not be worked over the holiday weekend, engineers from Boeing did in fact work through the weekend. Boeing analysts conducted a preliminary damage assessment on Saturday. Using video and photo images, they generated two estimates of possible debris size, 20 inches by 20 inches by 2 inches, and 20 inches by 16 inches by 6 inches, and determined that the debris was traveling at approximately 750 feet per second, or 511 miles per hour, when it struck the orbiter at an estimated impact angle of less than 20 degrees. These estimates later proved remarkably accurate. To calculate the damage that might result from such a strike, the analysts turned to a Boeing mathematical modeling tool called Crater that uses a specially developed algorithm to predict the depth of a thermal protection system tile to which debris will penetrate. This algorithm, suitable for estimating small, on the order of 3 cubic inches, debris impacts, had been calibrated by the results of foam, ice, and metal debris impact testing. A similar crater-like algorithm was also developed and validated with test results to assess the damage caused by ice projectiles impacting the reinforced carbon-carbon leading edge panels. These tests showed that within certain limits, the crater algorithm predicted more severe damage than was observed. This led engineers to classify Crater as a conservative tool, one that predicts more damage than will actually occur. Until STS-107, Crater was normally used only to predict whether small debris, usually ice on the external tank, would pose a threat to the orbiter during launch. The use of Crater to assess the damage caused by foam during the launch of STS-107 was the first use of the model while a mission was on orbit. Also of note is that engineers used Crater during STS-107 to analyze a piece of debris that was at maximum 640 times larger in volume than the pieces of debris used to calibrate and validate the Crater model. The board's best estimate is that it was actually 400 times larger. Therefore, the use of Crater in this new and very different situation compromised NASA's ability to accurately predict debris damage in ways that debris assessment team engineers did not fully comprehend. Over the weekend, an engineer certified by Boeing to use Crater entered two estimated debris dimensions, the estimated debris velocity and the estimated angle of impact. The engineer had received formal training on crater from senior Houston-based Boeing engineering staff, but he had only used the program twice before and had reservations about using it to model the piece of foam debris that struck Columbia. The engineer did not consult with more experienced engineers from Boeing's Huntington Beach, California facility, who, up until the time of STS-107, had performed or overseen crater analysis. Boeing completed the transfer of responsibilities for crater analysis from its Huntington Beach engineers to its Houston office in January 2003. STS-107 was the first mission that the Huntington Beach engineers were not directly involved with. For the thermal protection system tile, crater predicted damage deeper than the actual tile thickness. This seemingly alarming result suggested that the debris that struck Columbia would have exposed the orbiter's underlying aluminum airframe to extreme temperatures, resulting in a possible burn-through during re-entry. Debris assessment team engineers discounted the possibility of burn-through for two reasons. First, the results of calibration tests with small projectiles showed that crater predicted deeper penetrations than would actually occur. Second, the crater equation does not take into account the increased density of a tile's lower densified layer, which is much stronger than the tile's fragile outer layer. Therefore, engineers judged that the actual damage from the large piece of foam lost on STS-107 would not be as severe as crater predicted, and assumed that the debris did not penetrate the orbiter's skin. This uncertainty, however, meant that determining the precise location of the impact was paramount for an accurate damage estimate. Some areas on the orbiter's lower surface, such as the seals around the landing gear doors, are more vulnerable than others. Only by knowing precisely where the debris struck could the analysts more accurately determine if the orbiter had been damaged. To determine potential reinforced carbon-carbon damage, analysts used a crater-like algorithm that was calibrated in 1984 to impact data from ice projectiles. At the time the algorithm was empirically tested, ice was considered the only realistic threat to RCC integrity. The debris assessment team analysis indicated that impact angles greater than 15 degrees would result in RCC penetration. A separate transport analysis, which attempts to determine the path the debris took, identified 15 strike regions and angles of impact. 12 of the transport scenarios predicted an impact in regions of shuttle tile. Only one scenario predicted an impact on the RCC leading edge at a 21-degree angle. Because the foam that struck Columbia was less dense than ice, debris assessment team analysts used a qualitative extrapolation of the test data and engineering judgment to conclude that a foam impact angle up to 21 degrees would not penetrate the RCC. Although some engineers were uncomfortable with this extrapolation, no other analyses were performed to assess RCC damage. The debris assessment team focused on analyzing the impact at locations other than the RCC leading edge. This may have been due, at least in part, to the transport analysis presentation and the long-standing belief that foam was not a threat to RCC panels. The assumptions and uncertainty embedded in this analysis were never fully presented to the mission evaluation room or the mission management team. End of Section 24. Recording by Maria Kasper. Section 25 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6E, Decision-Making at NASA, Part 5. Missed Opportunity 1. On Sunday, Rodney Rocha emailed a Johnson Space Center Engineering Directorate manager to ask if a mission action request was in progress for Columbia's crew to visually inspect the left wing for damage. Rocha never received an answer. Flight Day 5, Monday, January 20th, 2003. On Monday morning, the Martin Luther King Jr. holiday, the debris assessment team held an informal meeting before its first formal meeting, which was scheduled for Tuesday afternoon. The team expanded to include NASA and Boeing transport analysts expert in the movement of debris in airflows, tile and RCC experts from Boeing and NASA, aerothermal and thermal engineers from NASA, United Space Alliance, and Boeing, and a safety representative from the NASA contractor Science Applications International Corporation. Engineers emerged from that informal meeting with a goal of obtaining images from ground-based assets. Uncertainty as to precisely where the debris had struck Columbia generated concerns about the possibility of a breach in the left main landing gear door seal. They conducted further analysis using angle and thickness variables and thermal data obtained by personnel at Boeing's Huntington Beach facility for STS-87 and STS-50, the two missions that had incurred thermal protection system damage. See Section 6.1. Debris Assessment Team co-chair Pam Madeira distributed an email summarizing the day's events and outlined the agenda for Tuesday's first formal Debris Assessment Team meeting. Included on the agenda was the desire to obtain on-orbit images of Columbia's left wing. According to an 11:39 a.m. entry in the Mission Evaluation Room Manager's log, the debris blob is estimated at 20 inches, plus or minus 10 inches in some direction, using the orbiter hatch as a basis. It appears to be similar size as that seen in STS-112. There will be more comparison work done and more info and details in tomorrow's report. This entry illustrates in NASA language an initial attempt by managers to classify this bipod ramp foam strike as close to being within the experience base, and therefore being almost an in-family event, not necessarily a safety concern. While the size and source of STS-107 debris was somewhat similar to what STS-112 had experienced, the impact sites, the wing versus the solid rocket booster, differed, a distinction not examined by mission managers. Flight Day 6, Tuesday, January 21st, 2003. At 7 a.m., the Debris Assessment Team briefed Don McCormick, the Chief Mission Evaluation Room Manager, that the foam source and size was similar to what struck STS-112, and that an analysis of measured versus predicted tile damage from STS-87 was being scrutinized by Boeing. An hour later, McCormick related this information to the mission management team at its first post-holiday meeting. Although Space Shuttle program requirements state that the mission management team will convene daily during a mission, the STS-107 mission management team met only on January 17th, 21st, 24th, 27th, and 31st. The transcript below is the first record of an official discussion of the debris impact at a mission management team meeting. Before even referring to the debris strike, the mission management team focused on end-of-mission downweight. The orbiter was 150 pounds over the limit, a leaking water separator, a jammed Hasselblad camera, payload and experiment status, and a communications downlink problem. McCormick then stated that engineers planned to determine what could be done if Columbia had sustained damage. STS-107 Mission Management Team Chair Linda Ham suggested the team learn what rationale had been used to fly after external tank foam losses on STS-87 and STS-112. Transcript excerpts from January 21st Mission Management Team meeting. Ham: All right, I know you guys are looking at the debris. McCormick: Yeah, as everybody knows, we took a hit on somewhere on the left wing leading edge, and the photo TV guys have completed, I think, pretty much their work, although I'm sure they're reviewing their stuff. And they've given us an approximate size for the debris, and approximate area for where it came from, and approximately where it hit. So we are talking about doing some sort of parametric type of analysis, and also we're talking about what you can do in the event we have some damage there. Ham: That comment, I was thinking that the flight rationale at the FRR from tank and orbiter from STS-112 was, I'm not sure that the area is exactly the same where the foam came from, but the carrier properties and density of the foam wouldn't do any damage. So we ought to pull that along with the 87 data where we had some damage, pull this data from 112 or whatever flight it was, and make sure that, I hope that we had good flight rationale then. McCormick: Yeah, and we'll look at that. You mentioned 87. We saw some fairly significant damage in the area between RCC panels 8 and 9 and the main landing gear door on the bottom on STS-87. We did some analysis prior to STS-89, so, Ham: And I don't think there is much we can do, so it's not really a factor during the flight because there is not much we can do about it. But what I'm really interested in is making sure our flight rationale to go was good, and maybe this is foam from a different area, and I'm not sure, and it may not be correlated. But you can try to see what we have. McCormick: Okay. After the meeting, the rationale for continuing to fly after the STS-112 foam loss was sent to Ham for review. She then exchanged emails with her boss, Space Shuttle Program Manager Ron Ditmore. Original message from Ditmore, Ronald D., sent Wednesday, January 22, 2003, 9:14 a.m., to Ham, Linda J., subject, Re-ET briefing, STS-112 foam loss. You remember the briefing. Jerry did it and had to go out and say that the hazard report had not changed and that the risk had not changed, but it is worth looking at again. Original message from Ham, Linda J., sent Tuesday, January 21, 2003, 11:14 a.m., to Ditmore, Ronald D., subject, forward, ET briefing, STS-112 foam loss. You probably can't open the attachment, but the ET rationale for the flight of STS-112 loss of foam was lousy. Rationale states we haven't changed anything. We haven't experienced any safety of flight damage in 112 flights. Risk of loss of bipod ramp TPS is same as previous flights. So ET is safe to fly with no added risk. Rationale was lousy then and still is. Original message from McCormick Donald L., sent January 21, 2003, 9:45 a.m., to Ham, Linda J., subject, forward, ET briefing, STS-112 foam loss. Importance, high. FYI, it kinda says that it will probably be all right. Ham's focus on examining the rationale for continuing to fly after the foam problems with STS-87 and STS-112 indicates that her attention had already shifted from the threat the foam posed to STS-107 to the downstream implications of the foam strike. Ham was due to serve along with Wayne Hale as the launch integration manager for the next mission, STS-114. If the shuttle program's rationale to fly with foam loss was found to be flawed, STS-114, due to be launched in about a month, would have to be delayed, per NASA rules that require serious problems to be resolved before the next flight. An STS-114 delay could in turn delay completion of the International Space Station's Node 2, which was a high-priority goal for NASA managers. See Section 6.2 for a detailed description of schedule pressures. During this same Mission Management Team meeting, the Space Shuttle Integration Office's Lambert Austin reported that engineers were reviewing long-range tracking film and that the foam debris that appeared to hit the left wing leading edge may have come from the bipod area of the external tank. Austin said that the engineering directorate would continue to run analyses and compare this foam loss to that of STS-112. Austin also said that after STS-107 landed, engineers were anxious to see the crew-filmed footage of external tank separation that might show the bipod ramp and therefore could be checked for missing foam. Missed Opportunity 2. Reviews of flight deck footage confirm that on Flight Day 1, mission specialist David Brown filmed parts of the external tank separation with a Sony PD-100 camcorder, and payload commander Mike Anderson photographed it with a Nikon F5 camera with a 400mm lens. Brown later downlinked 35 seconds of this video to the ground as part of his Flight Day 1 mission summary, but the bipod ramp area had rotated out of view, so no evidence of missing foam was seen when this footage was reviewed during the mission. However, after the Inter-Center Photo Working Group caught the debris strike on January 17th, ground personnel failed to ask Brown if he had additional footage of external tank separation. Based on how crews are trained to film external tank separation, the board concludes that Brown did in fact have more film than the 35 seconds he downlinked. Such footage may have confirmed that foam was missing from the bipod ramp area, or could have identified other areas of missing foam. Austin's mention of the crew's filming of external tank separation should have prompted someone at the meeting to ask Brown if he had more external tank separation film, and if so, to downlink it immediately. Flight Director Steve Stitch discussed the debris strike with Phil Engelhoff, a member of the Mission Operations Directorate, after Engelhoff returned from the Mission Management Team meeting. As written in a timeline Stitch composed after the accident, the conversation included the following. Phil said the Space Shuttle program community is not concerned, and that Orbiter Project is analyzing ascent debris, relayed that there had been no direction for Mission Operations Directorate to ask Department of Defense for any photography of possible damaged tiles. No direction for Department of Defense photography seems to refer to either a previous discussion of photography with mission managers or an expectation of future activity, since the interagency agreement on imaging support stated that the Flight Dynamics Officer is responsible for initiating such a request. Engelhoff's comments demonstrate that an informal chain of command, in which the Mission Operations Directorate figures prominently, was at work. About an hour later, Calvin Schomburg, a Johnson Space Center engineer with close connections to shuttle management, sent the following email to other Johnson engineering managers. Original message from Schomburg, Calvin, sent Tuesday, January 21, 2003, 9:26 a.m. to Shack, Paul E., Cyril Grush, Joyce M., Hamilton, David A. Subject, forward, STS-107 Post-Launch Film Review, Day 1. For your information, thermal protection system took a hit. Should not be a problem. Status by end of week. Shuttle program managers regarded Schomburg as an expert on the thermal protection system. His message downplays the possibility that foam damaged the thermal protection system. However, the board notes that Schomburg was not an expert on reinforced carbon-carbon, RCC, which initial debris analysis indicated the foam may have struck. Because neither Schomburg nor shuttle management rigorously differentiated between tiles and RCC panels, the bounds of Schomburg's expertise were never properly qualified or questioned. 7 minutes later, Paul Schack, manager of the Shuttle Engineering Office, Johnson Engineering Directorate, emailed to Rocha and other Johnson engineering managers information on how previous bipod ramp foam losses were handled. Original message from Schack Paul E., sent Tuesday, January 21, 2003, 9:33 a.m. to Rocha Alan R., Ceriali Grush Joyce M., Kramer Julie A., Miller Glenn J., Rickman Stephen L., Madden Christopher B. Subject: Re STS-107 Debris Analysis Team Plans. This reminded me that at the STS-113 Flight Readiness Review, the external tank project reported on foam loss from the bipod ramp during STS-112. The foam, estimated 4 by 5 by 12 inches, impacted the external tank attach ring and dented a solid rocket booster electronics box cover. Their charts stated, external tank thermal protection system foam loss over the life of the shuttle program has never been a safety of flight issue. They were severely wire brushed over this, and Brian O'Connor, Associate Administrator for Safety, asked for a hazard assessment for loss of foam. The suspected cause for foam loss is trapped air pockets which expand due to altitude and aerothermal heating. Schack's message informed Rocha that during the STS-113 Flight Readiness Review, foam loss was not considered to be a safety of flight issue. The wire brushing that the external tank project received for stating that foam loss has never been a safety of flight issue refers to the wording used to justify continuing to fly. Officials at the Flight Readiness Review insisted on classifying the foam loss as an accepted risk rather than not a safety of flight problem, to indicate that although the shuttle would continue to fly, the threat posed by foam is not zero, but rather a known and acceptable risk. It is here that the decision to fly before resolving the foam problem at the STS-113 Flight Readiness Review influences decisions made during STS-107. Having at hand a previously accepted rationale, reached just one mission ago, that foam strikes are not a safety of flight issue, provides a strong incentive for mission managers and working engineers to use that same judgment for STS-107. If managers and engineers were to argue that foam strikes are a safety of flight issue, they would contradict an established consensus that was a product of the shuttle program's most rigorous review, a review in which many of them were active participants. An entry in a mission evaluation room console log included a 10:30 a.m. report that compared the STS-107 foam loss to previous foam losses and subsequent tile damage, which reinforced management acceptance about foam strikes by indicating that the foam strike appeared to be more of an in-family event. STS-107 debris measured at 22 inches long plus or minus 10 inches. On STS-112, the debris spray pattern was a lot smaller than that of STS-107. On STS-50, debris that was determined to be the bipod ramp, which measured 26 inches by 10 inches, caused damage to the left wing, to one tile and 20% of the adjacent tile. Same event occurred on STS-7, no data available. Missed Opportunity 3. The foam strike to STS-107 was mentioned by a speaker at an unrelated meeting of NASA headquarters and National Imagery and Mapping Agency personnel, who then discussed a possible NASA request for Department of Defense imagery support. However, no action was taken. Imagery Request 2. Responding to concerns from his employees who were participating in the debris assessment team, United Space Alliance manager Bob White called Lambert Austin on Flight Day 6 to ask what it would take to get imagery of Columbia on orbit. They discussed the analytical debris damage work plan, as well as the belief of some integration team members that such imaging might be beneficial. Austin subsequently telephoned the Department of Defense Manned Spaceflight Support Office representative to ask about actions necessary to get imagery of Columbia on orbit. Austin emphasized that this was merely information gathering, not a request for action. This call indicates that Austin was unfamiliar with NASA National Imagery and Mapping Agency imagery request procedures. An email that Lieutenant Colonel Timothy Lee sent to Don McCormick the following day shows that the Defense Department had begun to implement Austin's request. Original message from Lee, Timothy F., Lieutenant Colonel, USAF, sent Wednesday, January 22, 2003, 9:01 a.m. to McCormick, Donald L., NASA. Subject, NASA request for Department of Defense. Don, for your information, Lambert Austin called me yesterday requesting Department of Defense photo support for STS-107. Specifically, he is asking us if we have a ground or satellite asset that can take a high-resolution photo of the shuttle while on orbit to see if there is any foreign object debris damage on the wing. We are working on his request. Tim. At the same time, managers Ralph Rowe, Lambert Austin, and Linda Ham referred to conversations with Calvin Schomburg, whom they referred to as a thermal protection system expert. They indicated that Schomburg had advised that any tile damage should be considered a turnaround maintenance concern and not a safety of flight issue, and that imagery of Columbia's left wing was not necessary. There was no discussion of potential reinforced carbon-carbon damage. First Debris Assessment Team meeting. On Flight Day 6, the Debris Assessment Team held its first formal meeting to finalize orbiter damage estimates and their potential consequences. Some participants joined the proceedings via conference call. Imagery Request 3. After 2 hours of discussing the crater results and the need to learn precisely where the debris had hit Columbia, the Debris Assessment Team assigned its NASA co-chair, Rodney Rocha, to pursue a request for imagery of the vehicle on orbit. Each team member supported the idea to seek imagery from an outside source. Rather than working the request up the usual mission chain of command, through the mission evaluation room to the mission management team to the flight dynamics officer, the debris assessment team agreed, largely due to a lack of participation by mission management team and mission evaluating room managers, that Rocha would pursue the request through his division, the engineering directorate at Johnson Space Center. Rocha sent the following email to Paul Schack shortly after the meeting adjourned. Original message from Rocha Alan R., sent Tuesday, January 21, 2003, 4:41 p.m. to Schack Paul E., Hamilton David A., Miller Glenn J. Copied to Serial Grush Joyce M., Rogers Joseph E., Galbraith Gregory F. Subject, STS-107 Wing Debris Impact, Request for Outside Photo Imaging Help. Paul and Dave. The meeting participants, Boeing, United Space Alliance, NASA ES-2 and ES-3, and Kennedy Space Center, all agreed we will always have big uncertainties in any transport trajectory analyses and applicability extrapolation of the old ArcJet test data until we get definitive, better, clearer photos of the wing and body underside. Without better images, it will be very difficult to even bound the problem and initialize thermal, trajectory, and structural analyses. Their answers may have a wide spread, ranging from acceptable to not acceptable to horrible, and no way to reduce the uncertainty. Thus, giving Mission Operations Directorate options for entry will be very difficult. Can we petition, beg, for outside agency assistance? We are asking for Frank Benz with Ralph Rowe or Ron Ditmore to ask for such. Some of the old-timers here remember we got such help in the early 1980s when we had missing tile concerns. Despite some naysayers, there are some options for the team to talk about. On-orbit thermal conditioning for the major structure, but is in contradiction with tire pressure temperature cold limits, limiting high cross-range deorbit entries, constraining right or left hard turns during the heading alignment circle, only if there is structural damage to the RCC panels to the extent it affects flight control. Rodney Rocha, Structural Engineering Division, ESSED, ES Division Chief Engineer, Space Shuttle DCE, Chair, Space Shuttle Loads and Dynamics Panel, Mail Code ES2. Routing this request through the Engineering Department led in part to its being viewed by shuttle program managers as a non-critical engineering desire rather than a critical operational need. Flight Day 7, Wednesday, January 22, 2003. Conversations and log entries on Flight Day 7 document how 3 requests for images, Bob Page to Wayne Hale, Bob White to Lambert Austin, and Rodney Rocha to Paul Schack, were ultimately dismissed by the mission management team, and how the order to halt those requests was then interpreted by the debris assessment team as a direct and final denial of their request for imagery. End of Section 25. Recording by Maria Kasper. Section 26 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6F, Decision-Making at NASA, Part 6. Missed Opportunity 4. On the morning of Flight Day 7, Wayne Hale responded to the earlier Flight Day 2 request from Bob Page and a call from Lambert Austin on Flight Day 5, during which Austin mentioned that some analysts from the debris assessment team were interested in getting imagery. Hale called a Department of Defense representative at Kennedy Space Center, who was not the designated Department of Defense official for coordinating imagery requests, and asked that the military start the planning process for imaging Columbia on orbit. Within an hour, the Defense Department representative at NASA contacted U.S. Strategic Command, U.S. STRATCOM, at Colorado's Cheyenne Mountain Air Force Station and asked what it would take to get imagery of Columbia on orbit. This call was similar to Austin's call to the Department of Defense Manned Spaceflight Support Office, in that the caller characterized it as information gathering rather than a request for action. A representative from U.S. STRATCOM Plans Office initiated actions to identify ground-based and other imaging assets that could execute the request. Hale's earlier call to the Defense Department representative at Kennedy Space Center was placed without authorization from Mission Management Team Chair Linda Ham. Also, the call was made to a Department of Defense representative who was not the designated liaison for handling such requests. In order to initiate the imagery request through official channels, Hale also called Phil Engelhoff at the Mission Operations Directorate, told him he had started Defense Department action, and asked if Engelhoff could have the Flight Dynamics Officer at Johnson Space Center make an official request to the Cheyenne Mountain Operations Center. Engelhoff started to comply with Hale's request. After the Department of Defense representatives were called, Lambert Austin telephoned Linda Ham to inform her about the imagery requests that he and Hale had initiated. Austin also told Wayne Hale that he had asked Lieutenant Colonel Lee at the Department of Defense Manned Spaceflight Support Office about what actions were necessary to get on-orbit imagery. Missed Opportunities 5 and 6. Mike Card, a NASA headquarters manager from the Safety and Mission Assurance Office, called Mark Erminger at the Johnson Space Center Safety and Mission Assurance for Shuttle Safety Program, and Brian O'Connor, Associate Administrator for Safety and Mission Assurance, to discuss a potential Department of Defense imaging request. Erminger said that he was told this was an in-family event. O'Connor stated he would defer to shuttle management in handling such a request. Despite two safety officials being contacted, one of whom was NASA's highest-ranking safety official, safety personnel took no actions to obtain imagery. The following is an 8:09 a.m. entry in the Mission Evaluation Room console log. We received a visit from Mission Manager Vanessa Ellerby and Flight Director Office Phil Engelhoff regarding two items. One, the Mission Management Team's action item to the Mission Evaluation Room to determine the impacts to the vehicle's 150 pounds of additional weight. And two, Mr. Engelhoff wants to know who is requesting the Air Force to look at the vehicle. Cancellation of the request for imagery. At 8:30 a.m., the NASA Department of Defense liaison officer called U.S. Stratcom and canceled the request for imagery. The reason given for the cancellation was that NASA had identified its own in-house resources and no longer needed the military's help. The NASA request to the Department of Defense to prepare to image Columbia on orbit was both made and rescinded within 90 minutes. The board has determined that the following sequence of events likely occurred within that 90-minute period. Linda Ham asked Lambert Austin if he knew who was requesting the imagery. After admitting his participation in helping to make the imagery request outside the official chain of command and without first gaining Ham's permission, Austin referred to his conversation with United Space Alliance Shuttle Integration Manager Bob White on Flight Day 6, in which White had asked Austin, in response to White's debris assessment team employee concerns, what it would take to get orbiter imagery. Even though Austin had already informed Ham of the request for imagery, Ham later called Mission Management Team members Ralph Rowe, manager of the Space Shuttle Vehicle Engineering Office, Lauren Shriver, United Space Alliance Deputy Program Manager for Shuttle, and David Moyer, the on-duty Mission Evaluation Room Manager, to determine the origin of the request and to confirm that there was a requirement for a request. Ham also asked Flight Director Phil Engelhoff if he had a requirement for imagery of Columbia's left wing. These individuals all stated that they had not requested imagery, that they were not aware of any official requests for imagery, and could not identify a requirement for imagery. Linda Ham later told several individuals that nobody had a requirement for imagery. What started as a request by the Intercenter Photo Working Group to seek outside help in obtaining images on Flight Day 2 in anticipation of analysts' needs had become by Flight Day 6 an actual engineering request by members of the debris assessment team made informally through Bob White to Lambert Austin and formally in Rodney Roach's email to Paul Schack. These requests had then caused Lambert Austin and Wayne Hale to contact Department of Defense representatives. When Ham officially terminated the actions that the Department of Defense had begun, she effectively terminated both the Intercenter Photo Working Group request and the Debris Assessment Team request. While Ham has publicly stated she did not know of the Debris Assessment Team members' desire for imagery, she never asked them directly if the request was theirs, even though they were the team analyzing the foam strike. Also, on Flight Day 7, Ham raised concerns that the extra time spent maneuvering Columbia to make the left wing visible for imaging would unduly impact the mission schedule. For example, science experiments would have to stop while the imagery was taken. According to personal notes obtained by the board, Linda Ham said it was no longer being pursued, since even if we saw something, we couldn't do anything about it. The program didn't want to spend the resources. Shuttle managers, including Ham, also said they were looking for very small areas on the orbiter, and that past imagery resolution was not very good. The board notes that no individuals in the STS-107 operational chain of command had the necessary security clearance to know about national imaging capabilities. Additionally, no evidence has been uncovered that anyone from NASA, United Space Alliance, or Boeing sought to determine the expected quality of images and the difficulty and costs of obtaining Department of Defense assistance. Therefore, members of the mission management team were making critical decisions about imagery capabilities based on little or no knowledge. The following is an entry in the Flight Director Handover Log. NASA Resident Office, Peterson Air Force Base called, and spacecraft object identification at U.S. Spacecom was officially turned off. This went all the way up to 4-star general. Post-flight, we will write a memo to U.S. Spacecom telling them whom they should take spacecraft object identification requests from. After canceling the Department of Defense imagery request, Linda Ham continued to explore whether foam strikes posed a safety of flight issue. She sent an email to Lambert Austin and Ralph Rowe. Original message from Ham, Linda J., sent Wednesday, January 22, 2003, 9:33 a.m. to Austin, Lambert D., Rowe, Ralph R. Subject, external tank foam loss. Can we say that for any external tank foam lost, no safety of flight damage can occur to the orbiter because of the density? Responses included the following. Original message from Rowe, Ralph R., sent Wednesday, January 22, 2003, 9:38 a.m. to Schomburg, Calvin. Subject, forward, external tank foam loss. Calvin, I wouldn't think we could make such a generic statement, but can we bound it some? How, by size or acreage? Note, acreage equals larger areas of foam coverage. End note. Ron Ditmore emailed Linda Ham the following. Original message from Ditmore Ronald D., sent Wednesday, January 22, 2003, 10:15 a.m. to Ham, Linda J. Subject, external tank briefing, STS-112 foam loss. Another thought, we need to make sure that the density of the external tank foam cannot damage the tile to where it is an impact to the orbiter. Lambert and Ralph need to get some folks working with external tank. The following is an email from Calvin Schomburg to Ralph Rowe. Original message from Schomburg Calvin, sent Wednesday, January 22, 2003, 10:53 a.m. to Rowe, Ralph R. Subject, external tank foam loss. No, the amount of damage external tank foam can cause to the thermal protection system material tiles is based on the amount of impact energy, the size of the piece and its velocity, from just after pad clear until about 120 seconds. After that it will not hit, or it will not have enough energy to cause any damage. It is a pure kinetic problem. There is a size that can cause enough damage to a tile that enough of the material is lost that we could burn a hole through the skin and have a bad day. Loss of vehicle and crew. About 200 to 400 tile locations out of the 23,000 on the lower surface. The foam usually fails in small popcorn pieces. That is why it is vented, to make small hits. The 2 or 3 times we have been hit with a piece as large as the one this flight, we got a gouge about 8 to 10 inches long, about 2 inches wide, and 3/4 to 1 inch deep across 2 or 3 tiles. That is what I expect this time, nothing worse. If that is all we get, we have no problem. We will have to replace a couple of tiles, but nothing else. The following is a response from Lambert Austin to Linda Ham. Original message from Austin Lambert D., sent Wednesday, January 22, 2003, 3:22 p.m. to Ham, Linda J. Copy to Wallace Rodney O., Noah Donald S. Subject: external tank foam loss. No. I will cover some of the pertinent rationale. There could be more if I spent more time thinking about it. Recall this issue has been discussed from time to time since the inception of the basic no debris requirement in Volume 10, and at each review the Space Shuttle program has concluded that it is not possible to preclude a potential catastrophic event as a result of debris impact damage to the flight elements. As regards the orbiter, both windows and tiles are areas of concern. You can talk to Carl Schomburg, and he will verify the many times we have covered this in Space Shuttle program reviews. While there is much tolerance to window and tile damage, external tank foam loss can result in impact damage that under subsequent entry environments can lead to loss of structural integrity of the orbiter area impacted, or a penetration in a critical function area that results in loss of that function. My recollection of the most critical orbiter bottom acreage areas are the wing spar, main landing gear door seal, and reinforced carbon-carbon panels. Of course, Cal can give you a much better rundown. We can and have generated parametric impact zone characterizations for many areas of the orbiter for a few of our more typical external tank foam loss areas. Of course, the impact damage significance is always a function of debris size and density, impact velocity, and impact angle, these latter two being a function of the flight time at which the external tank foam becomes debris. For STS-107 specifically, we have generated this info and provided it to Orbiter. Of course, even this is based on the assumption that the location and size of the debris is the same as occurred on STS-112. This cannot be verified until we receive the onboard external tank separation photo evidence post-orbiter landing. We are requesting that this be expedited. I have the STS-107 orbiter impact map based on the assumptions noted herein being sent down to you. Rod is in a review with the orbiter on this info right now. The board notes that these email exchanges indicate that senior mission management team managers, including the shuttle program manager, mission management team chair, head of the Space Shuttle Systems Integration, and a shuttle tile expert, correctly identified the technical bounds of the foam strike problem and its potential seriousness. Mission managers understood that the relevant question was not whether the foam posed a safety of flight issue, it did, but rather whether the observed foam strike contained sufficient kinetic energy to cause damage that could lead to a burn-through. Here, all the key managers were asking the right question and admitting the danger. They even identified reinforced carbon-carbon as the critical impact zone. Yet little follow-through occurred with either the request for imagery or the debris assessment team analysis. See Section 3.4 and 3.6 for details on the kinetics of foam strikes. A mission evaluation room log entry at 10:37 a.m. records the decision not to seek imaging of Columbia's left wing. United Space Alliance Program Manager Lauren Shriver, NASA Manager, Program Integration, Linda Ham, and NASA Space Shuttle Vehicle Engineering Office, Ralph Rowe, have stated that there is no need for the Air Force to take a look at the vehicle. At 11:22 a.m., Debris Assessment Team co-chair Pam Madeira sent an email to team members setting the agenda for the team's second formal meeting that afternoon that included discussion on need, rationale for mandatory viewing of damage site, all. Earlier email agenda wording did not include need, rationale for mandatory wording, as listed here, which indicates that Madeira knew of management's decision not to seek images of Columbia's left wing, and anticipated having to articulate a mandatory rationale to reverse that decision. In fact, a United Space Alliance manager had informed Madeira that imagery would be sought only if the request was a mandatory need. 23 minutes later, an email from Paul Schack to Rodney Rocha, who the day before had carried forward the debris assessment team's request for imaging, stated the following: FYI, according to the Mission Evaluation Room, Ralph Rowe has told Program that Orbiter is not requesting any outside imaging help. Earlier that morning, Ralph Rowe's deputy manager, Trish Petit, had separate conversations with Paul Schack and tile expert Calvin Schomburg. In those conversations, Petit noted that an analysis of potential damage was in progress, and they should wait to see what the analysis showed before asking for imagery. Schomburg, though aware of the debris assessment team's request for imaging, told Schack and Petit that he believed on-orbit imaging of potentially damaged areas was not necessary. As the morning wore on, debris assessment team engineers, shuttle program management, and other NASA personnel exchanged email. Most messages centered on technical matters to be discussed at the debris assessment team's afternoon meeting, including debris density, computer-aided design models, and the highest angle of incidence to use for a particular material property. One email from Rocha to his managers and other Johnson engineers at 11:19 a.m. included the following: There are good scenarios, acceptable and minimal damage, to horrible ones, depending on the extent of damage incurred by the wing and location. The most critical locations seem to be the 1191 wing spar region, the main landing gear door seal, and the RCC panels. We do not know yet the exact extent or nature of the damage without being provided better images, and without such, all the high-powered analyses and assessments in work will retain significant uncertainties. Second Debris Assessment Team Meeting. Some, but not all, of the engineers attending the Debris Assessment Team's second meeting had learned that the shuttle program was not pursuing imaging of potentially damaged areas. What team members did not realize was the shuttle program's decision not to seek on-orbit imagery was not necessarily a direct and final response to their request. Rather, the no was partly in response to the Kennedy Space Center action initiated by United Space Alliance engineers and managers, and finally by Wayne Hale. Not knowing that this was the case, debris assessment team members speculated as to why their request was rejected and whether their analysis was worth pursuing without new imagery. Discussion then moved on to whether the debris assessment team had a mandatory need for Department of Defense imaging. Most team members, when asked by the board what mandatory need meant, replied with a shrug of their shoulders. They believed the need for imagery was obvious. Without better pictures, engineers would be unable to make reliable predictions of the depth and area of damage caused by a foam strike that was outside of the experience base. However, team members concluded that although their need was important, they could not cite a mandatory requirement for the request. Analysts on the debris assessment team were in the unenviable position of wanting images to more accurately assess damage, while simultaneously needing to prove to program managers as a result of their assessment that there was a need for images in the first place. After the meeting adjourned, Rocha read the 11:45 a.m. email from Paul Schack, which said that the orbiter project was not requesting any outside imaging help. Rocha called Schack to ask if Schack's boss, Johnson Space Center Engineering Director Frank Benz, knew about the request. Rocha then sent several emails consisting of questions about the ongoing analyses and details on the shuttle program's cancellation of the imaging request. An email that he did not send, but instead printed out and shared with a colleague, follows. In my humble technical opinion, this is the wrong, and bordering on irresponsible, answer from the Space Shuttle program and orbiter not to request additional imaging help from any outside source. I must emphasize again that severe enough damage, 3 or 4 multiple tiles knocked out down to the densification layer, combined with the heating and resulting damage to the underlying structure at the most critical location, namely main landing gear door, wheels, tires, hydraulics, or the X1191 spar cap, could present potentially grave hazards. The engineering team will admit it might not achieve definitive high-confidence answers without additional images, but without action to request help to clarify the damage visually, we will guarantee it will not. Can we talk to Frank Benz before Friday's mission management team? Remember the NASA safety posters everywhere around stating, "If it's not safe, say so." Yes, it's that serious. When asked why he did not send this email, Rocha replied that he did not want to jump the chain of command. Having already raised the need to have the orbiter imaged with Schack, he would defer to management's judgment on obtaining imagery. Even after the imagery request had been canceled by program management, engineers in the debris assessment team and mission control continued to analyze the foam strike. A structural engineer in the mechanical, maintenance, arm, and crew systems sent an email to a flight dynamics engineer that stated, "There is lots of speculation as to the extent of the damage, and we could get a burn-through into the wheel well upon entry." Less than an hour later, at 6:09 p.m., a mission evaluation room console log entry stated the following: "Mechanical, maintenance, arm, and crew systems is trying to view a QuickTime movie on the debris impact, but doesn't have QuickTime software on his console. He needs either an AVI MPEG file or a VHS tape. He is asking us for help." The controller at the Mechanical, Maintenance, Arm, and Crew Systems console would be among the first in mission control to see indications of burn-through during Columbia's re-entry on the morning of February 1st. This log entry also indicates that mission control personnel were aware of the strike. Flight Day 8, Thursday, January 23, 2003. The morning after shuttle program management decided not to pursue on-orbit imagery, Rodney Rocha received a return call from Mission Operations Directorate Representative Barbara Conti to discuss what kinds of imaging capabilities were available for STS-107. End of Section 26. Recording by Maria Kasper. Section 27 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6G, Decision-Making at NASA, Part 7. Missed Opportunity 7. Conte explained to Rocha that the Mission Operations Directorate at Johnson did have U.S. Air Force standard services for imaging the shuttle during solid rocket booster separation and external tank separation. Conte explained that the orbiter would probably have to fly over Hawaii to be imaged. The board notes that this statement illustrates an unfamiliarity with national imaging assets. Hawaii is only one of many sites where relevant assets are based. Conte asked Rocha if he wanted her to pursue such a request through Missions Operations Directorate channels. Rocha said no, because he believed program managers would still have to support such a request, since they had already decided that imaging of potentially damaged areas was not necessary. Rocha thought it unlikely that the debris assessment team could convince them otherwise without definitive data. Later that day, Conte and another Mission Operations Directorate representative were attending an unrelated meeting with Leroy Kane, the STS-107 Ascent Entry Flight Director. At that meeting, they conveyed Rocha's concern to Kane and offered to help with obtaining imaging. After checking with Phil Engeloff, Kane distributed the following email. Original message from Kane, Leroy E., sent Thursday, January 23, 2003, 12:07 p.m. to Jones, Richard S., Oliver, Gregory T., Conte, Barbara A. Copy to Engeloff, Philip L., Austin, Brian P., Beck, Kelly B., Hanley, Jeffrey M., Stitch, J. S. Subject: Help with debris hit. The Space Shuttle program was asked directly if they had any interest or desire in requesting resources outside of NASA to view the orbiter. Reference the wing leading edge debris concern. They said no. After talking to Phil, I consider it to be a dead issue. Also on Flight Day 8, Debris Assessment Team engineers presented their final debris trajectory estimates to their NASA, United Space Alliance, and Boeing managers. These estimates formed the basis for predicting the orbiter's damaged areas, as well as the extent of damage, which in turn determined the ultimate threat to the orbiter during re-entry. Mission Control personnel thought they should tell Commander Rick Husband and pilot William McCool about the debris strike, not because they thought that it was worthy of the crew's attention, but because the crew might be asked about it in an upcoming media interview. Flight Director Steve Stitch sent the following email to Husband and McCool and copied other flight directors. Original message from Stitch J.S. sent Thursday, January 23, 2003, 11:13 p.m. to Commander and Pilot. Copy to Beck, Kelly B., Engeloff, Philip L., Kane, Leroy E., Hanley, Jeffrey M., Austin, Brian P. Subject: Info. Possible Public Affairs Officer event question. Rick and Willie: You guys are doing a fantastic job staying on the timeline and accomplishing great science. Keep up the good work and let us know if there is anything that we can do better from a Mission Control Center, Payload Operations Control Center standpoint. There is one item I would like to make you aware of for the upcoming Public Affairs Officer event on Blue Flight Day 10 and for future Public Affairs Officer events later in the mission. This item is not even worth mentioning other than wanting to make sure that you are not surprised by it in a question from a reporter. During ascent, at approximately 80 seconds, photo analysis shows that some debris from the area of the left external tank bipod attach point came loose and subsequently impacted the orbiter left wing in the area of transition from chine to main wing, creating a shower of smaller particles. The impact appears to be totally on the lower surface, and no particles were seen to traverse over the upper surface of the wing. Experts have reviewed the high-speed photography, and there is no concern for reinforced carbon-carbon or tile damage. We have seen this same phenomenon on several other flights, and there is absolutely no concern for entry. That is all for now. It's a pleasure working with you every day. This email was followed by another to the crew with an attachment of the video showing the debris impact. Husband acknowledged receipt of these messages. Later, a NASA liaison to U.S. Stratcom sent an email thanking personnel for the prompt response to the imagery request. The email asked that they help NASA observe official channels for this type of support in the future. Excerpts from this message follow. Let me assure you that as of yesterday afternoon, the shuttle was in excellent shape, mission objectives were being performed, and that there were no major debris system problems identified. The request that you received was based on a piece of debris, most likely ice or insulation from the external tank, that came off shortly after launch and hit the underside of the vehicle. Even though this is not a common occurrence, it is something that has happened before and is not considered to be a major problem. The one problem that this has identified is the need for some additional coordination within NASA to assure that when a request is made, it is done through official channels. The NASA U.S. Strat U.S. Space Memorandum of Agreement identifies the need for this type of support and that it will be provided by U.S. Strat. Procedures have been long established that identifies the Flight Dynamics Officer for the shuttle and the Trajectory Operations Officer for the International Space Station as the points of contact to work these issues with the personnel in Cheyenne Mountain. One of the primary purposes for this chain is to make sure that requests like this one does not slip through the system and spin the community up about potential problems that have not been fully vetted through the proper channels. Two things that you can help us with is to make sure that future requests of this sort are confirmed through the proper channels. For the shuttle, it is via Cheyenne Mountain Operations Center to the Flight Dynamics Officer. For the International Space Station, it is via Cheyenne Mountain Operations Center to the Trajectory Operations Officer. The second request is that no resources are spent unless this request has been confirmed. These requests are not meant to diminish the responsibilities of the Department of Defense Manned Spaceflight Support Office or to change any previous agreements, but to eliminate the confusion that can be caused by a lack of proper coordination. Third Debris Assessment Team Meeting. The Debris Assessment Team met for the third time Thursday afternoon to review updated impact analyses. Engineers noted that there were no alternate re-entry trajectories that the orbiter could fly to substantially reduce heating in the general area of the foam strike. Engineers also presented final debris trajectory data that included 3 debris size estimates to cover the continuing uncertainty about the size of the debris. Team members were told that imaging would not be forthcoming. In the face of this denial, the team discussed whether to include a presentation slide supporting their desire for images of the potentially damaged area. Many still felt it was a valid request and wanted their concerns aired at the upcoming Mission Evaluation Room brief and then at the Mission Management Team level. Eventually, the idea of including a presentation slide about the imaging request was dropped. Just prior to attending the third assessment meeting, tile expert Calvin Schomburg and Rodney Rocha met to discuss foam impacts from other missions. Schomburg implied that the STS-107 foam impact was in the orbiter's experience base and represented only a maintenance issue. Rocha disagreed and argued about the potential for burn-through on re-entry. Calvin Schomburg stated a belief that if there was severe damage to the tiles, nothing could be done. See Section 6.4. Both then joined the meeting already in progress. According to Boeing analysts who were members of the debris assessment team, Schomburg called to ask about their rationale for pursuing imagery. The Boeing analysts told him that something the size of a large cooler had hit the orbiter at 500 miles per hour. Pressed for additional reasons, and not fully understanding why their original justification was insufficient, the analysts said that at least they would know what happened if something were to go terribly wrong. The Boeing analysts next asked why they were working so hard analyzing potential damage areas if the shuttle program management believed the damage was minor and that no safety of flight issues existed. Schomburg replied that the analysts were new and they would learn from this exercise. Flight Day 9, Friday, January 24, 2003. At 7 a.m., Boeing and United Space Alliance contract personnel presented the debris assessment team's findings to Don McCormick, the mission evaluation room manager. In yet another signal that the working engineers and mission personnel shared a high level of concern for Columbia's condition, so many engineers crowded this briefing room that it was standing room only, with people lining the hallway. The presentation included view graphs that discussed the team's analytical methodology and 5 scenarios for debris damage, each based on different estimates of the debris size and impact point. A 6th scenario had not yet been completed, but early indications suggested that it would not differ significantly from the other 5. Each case was presented with a general overview of transport mechanics, results from the crater modeling, aerothermal considerations, and predicted thermal and structural effects for Columbia's re-entry. The briefing focused primarily on potential damage to the tiles, not the reinforced carbon-carbon panels. An analysis of how the poor construction of these view graphs effectively minimized key assumptions and uncertainties is presented in Chapter 7. While the team members were confident that they had conducted the analysis properly, within the limitations of the information they had, they stressed that many uncertainties remained. First, there was great uncertainty about where the debris had struck. Second, Crater, the analytical tool they used to predict the penetration depth of the debris impact, was being used on a piece of debris that was 400 times larger than the standard in Boeing's database. At the time, the team believed that the debris was 640 times larger. Engineers ultimately concluded that their analysis, limited as it was, did not show that a safety of flight issue existed. Engineers who attended this briefing indicated a belief that management focused on the answer, that analysis proved there was no safety of flight issue, rather than on concerns about the large uncertainties that may have undermined the analysis that provided that answer. At the mission management team's 8 a.m. meeting, Mission Evaluation Room Manager Don McCormick verbally summarized the debris assessment team's 7 a.m. brief. It was the third topic discussed. Unlike the earlier briefing, McCormick's presentation did not include the debris assessment team's presentation charts. The board notes that no supporting analysis or examination of minority engineering views was asked for or offered, that neither Mission Evaluation Room nor Mission Management Team members requested a technical paper of the debris assessment team's analysis, and that no technical questions were asked. January 24, 2003, Mission Management Team meeting transcript. The following is a transcript of McCormick's verbal briefing to the Mission Management Team, which Linda Ham chaired. Early in the meeting, Phil Engelhoff, chief of the flight director's office, reported that he had made clear in an email to Columbia's crew that there were no concerns that the debris strike had caused serious damage. The board notes that this conclusion about whether the debris strike posed a safety of flight issue was presented to the mission management team members before they discussed the debris strike damage assessment. Engelhoff: I will say that crew did send down a note last night asking if anybody is talking about extension days or going to go with that, and we sent up to the crew about a 15-second video clip of the strike, just so they are armed if they get any questions at the press conferences or that sort of thing. But we made it very clear to them, no concerns. Linda Ham: When is the press conference? Is it today? Engelhoff: It's later today. Ham: They may get asked because the press is aware of it. Engelhoff: The press is aware of it, I know. Folks have asked me because the press corps at the Cape have been asking. Wanted to make sure they were properly. Ham: Okay, back on the temperature. The meeting went on for another 25 minutes. Other mission-related subjects were discussed before team members returned to the debris strike. Ham. Go ahead, Don. Don McCormick. Okay. Also, we've received the data from the systems integration guys of the potential ranges of sizes and impact angles and where it might have hit. And the guys have gone off and done an analysis. They use a tool they refer to as Crater, which is their official evaluation tool to determine the potential size of the damage. So they went off and done all that work, and they've done thermal analysis to the areas where there may be damaged tiles. The analysis is not complete. There is one case yet that they wish to run, but kind of just jumping to the conclusion of all that, they do show that obviously a potential for significant tile damage is here, but thermal analysis does not indicate that there is potential for a burn-through. I mean, there could be localized heating damage. There is a lot of uncertainty in all this, in terms of the size of the debris and where it hit and the angle of incidence. Ham. No burn-through means no catastrophic damage, and the localized heating damage would mean a tile replacement. McCormick. Right, it would mean possible impacts to turnaround repair times and that sort of thing, but we do not see any kind of safety of flight issue here yet in anything that we've looked at. Ham. And no safety of flight, no issue for this mission, nothing that we're going to do different. There may be a turnaround. McCormick. Right, it could potentially hit the reinforced carbon-carbon, and we don't indicate any other possible coating damage or something. We don't see any issue if it hit the RCC, although we could have some significant tile damage if we don't see a safety of flight issue. Ham. What do you mean by that? McCormick. Well, it could be down through we could lose an entire tile, and then the ramp into and out of that. I mean, it could be a significant area of tile damage, down to the SIP perhaps, so it could be a significant piece missing, but... Note. SIP refers to the denser lower layers of tile to which the debris may have penetrated. End note. Ham. It would be a turnaround issue only. McCormick. Right. Unintelligible speaker. At this point, tile expert Calvin Schomburg states his belief that no safety of flight issue exists. However, some participants listening via teleconference to the meeting are unable to hear his comments. Ham. Okay, same thing you told me about the other day in my office. We've seen pieces of this size before, haven't we? Unknown speaker. Hey, Linda, we're missing part of that conversation. Ham. Right. Unknown speaker. Linda, we can't hear the speaker. Ham. He was just reiterating with Calvin that he doesn't believe there is any burn-through, so no safety of flight kind of issue. It's more of a turnaround issue, similar to what we've had on other flights. That's it? All right. Any questions on that? The board notes that when the official minutes of the January 24th mission management team were produced and distributed, there was no mention of the debris strike. These minutes were approved and signed by Frank Moreno, STS-107 Lead Payload Integration Manager, and Linda Ham. For anyone not present at the January 24th mission management team, who was relying on these minutes to update them on key issues, they would have read nothing about the debris strike discussions between Don McCormick and Linda Ham. A subsequent 8:59 a.m. Mission Evaluation Room console log entry follows. Mission Management Team Summary. McCormick also summarized the debris assessment. Bottom line is that there appears to be no safety of flight issue, but good chance of turnaround impact to repair tile damage. Flight Day 10 through 16, Saturday through Friday, January 25th through 31st, 2003. Although no safety of flight issue had officially been noted in the Mission Evaluation Room log, the debris assessment team was still working on parts of its analysis of potential damage to the wing and main landing gear door. On Sunday, January 26th, Rodney Rocha spoke with a Boeing thermal analyst and a Boeing stress analyst by telephone to express his concern about the debris assessment team's overall analysis, as well as the remaining work on the main landing gear door analysis. After the Boeing engineers stated their confidence with the analyses, Rocha became more comfortable with the damage assessment and sent the following email to his management. Original message from Rocha Alan R., sent Sunday, January 26, 2003, 7:45 p.m. to Shack Paul E., McCormick Donald L., Oyet Fred A., copy to Rogers Joseph E., Galbraith Gregory F., Jacobs Jeremy B., Ciriali Grush Joyce M., Kramer Julie A., Curry Donald M., Kowal T. J., Rickman Stephen L., Schomburg Calvin, Campbell Carlisle C., Jr. Subject: STS-107 Wing Debris Impact on Ascent. Final analysis case completed. As you recall from Friday's briefing to the Mission Evaluation Room, there remained open work to assess analytically predicted impact damage to the wing underside in the region of the main landing gear door. This area was considered a low-probability hit area by the image analysis teams, but they admitted a debris strike here could not be ruled out. As with the other analyses, performed and reported on Friday, this assessment by the Boeing multi-technical discipline engineering teams also employed the system integration's dispersed trajectories, followed by serial results from the crater damage prediction tool, thermal analysis, and stress analysis. It was reviewed and accepted by Structural Engineering Division Shuttle Chief Engineer R. Rocha by Sunday morning, January 26th. The case is defined by a large area gouge about 7-inch wide and about 30-inch long, with sloped sides like a crater and reaching down to the densified layer of the thermal protection system. Summary. Though this case predicted some higher temperatures at the outer layer of the honeycomb aluminum face sheet and subsequent debonding of the sheet, there is no predicted burn-through of the door, no breaching of the thermal and gas seals, nor is there door structural deformation or thermal warpage to open the seal to hot plasma intrusion. Though degradation of the thermal protection system and door structure is likely if impact occurred here, there is no safety of flight, entry, descent, landing issue. Note to Don M. and Fred O. On Friday, I believe, the Mission Evaluation Room was thoroughly briefed, and it was clear that open work remained, namely the case summarized above. The message of open work was not clearly given, in my opinion, to Linda Ham at the Mission Management Team. I believe we left her the impression that engineering assessments and cases were all finished, and that we could state with finality no safety of flight issues or questions remaining. This very serious case could not be ruled out, and it was a very good thing we carried it through to a finish. Rodney Rocha, Division Shuttle Chief Engineer, ES Structural Engineering Division, Chair, Space Shuttle Loads and Dynamics Panel. In response to this email, Don McCormick told Rocha that he would make sure to correct Linda Ham's possible misconception that the debris assessment team's analysis had been finished as of the briefing to the mission management team. McCormick informed Ham at the next mission management team meeting on January 27th that the damage assessment had in fact been ongoing and that their final conclusion was that no safety of flight issue existed. The debris strike, in the official estimation of the debris assessment team, amounted to only a post-landing turnaround maintenance issue. On Monday morning, January 27th, Doug Drury, a structural engineering manager from Johnson Space Center, summoned several Johnson engineers and Rocha to his office and asked them if they all agreed with the completed analyses and with the conclusion that no safety of flight issues existed. Although all participants agreed with that conclusion, they also knew that the debris assessment team members and most structural engineers at Johnson still wanted images of Columbia's left wing, but had given up trying to make that desire fit the mandatory requirement that shuttle management had set. Langley Research Center. Although the debris analysis team had completed its analysis and rendered a no safety of flight verdict, concern persisted among engineers elsewhere at NASA as they learned about the debris strike and potential damage. On Monday, January 27th, Carlisle Campbell, the design engineer responsible for landing gear, tires, and brakes at Johnson Space Center, forwarded Rodney Roach's January 26th email to Bob Doherty, an engineer at Langley Research Center who specialized in landing gear design. Engineers at Langley and Ames Research Center and Johnson Space Center did not entertain the possibility of Columbia breaking up during re-entry, but rather focused on the idea that the landing might not be safe, that the crew might need to ditch the vehicle, crash land in water, or be prepared to land with a damaged landing gear. Campbell initially contacted Doherty to ask his opinion of the arguments used to declare the debris strike not a safety of flight issue. Campbell commented that someone had brought up worst-case scenarios in which a breach in the main landing gear door causes two tires to go flat. To help Doherty understand the problem, Campbell forwarded him emails, briefing slides, and film clips from the debris damage analysis. Both engineers felt that the potential ramifications of landing with two flat tires had not been sufficiently explored. They discussed using shuttle simulator facilities at Ames Research Center to simulate a landing with two flat tires, but initially ruled it out because there was no formal request from the mission management team to work on the problem. Because astronauts were training in the Ames simulation facility, the two engineers looked into conducting their simulations after hours. Doherty contacted his management on Tuesday, January 28th, to update them on the plan for an after-hours simulation. He reviewed previous data runs, current simulation results, and prepared scenarios that could result from main landing gear problems. The simulated landings with two flat tires that Doherty eventually conducted indicated that it was a survivable but very serious malfunction. Of the various scenarios he prepared, Doherty shared the most unfavorable only with his management and selected Johnson Space Center engineers. In contrast, his favorable simulation results were forwarded to a wider Johnson audience for review, including Rodney Rocha and other debris assessment team members. The board is disappointed that Doherty's favorable scenarios received a wider distribution than his discovery of a potentially serious malfunction, and also does not approve of the reticence that he and his managers displayed in not notifying the mission management team of their concerns or his assumption that they could not displace astronauts who were training in the Ames simulator. At 4:36 p.m. on Monday, January 27th, Doherty sent the following to Campbell. Original message from Robert H. Doherty, sent Monday, January 27, 2003, 3:35 p.m. to Campbell, Carlisle C. Subject, video you sent. Wow, I bet there are a few pucker strings pulled tight around there. Thinking about a belly landing versus bailout, I would say that if there is a question about main gear well burn through, that it's crazy to even hit the deploy gear button, the reason being that you might have failed the wheels since they are aluminum. They will fail before the tire heating pressure makes them fail, and you will send debris all over the wheel well, making it a possibility that the gear would not even deploy due to ancillary damage. 300 feet is the wrong altitude to find out you have one gear down and the other not down. You're dead in that case. Think about the pitch down moment for a belly landing when hitting not the main gear but the trailing edge of the wing or body flap when landing gear is up. Even if you come in fast and at slightly less pitch altitude, the nose slap down with that pitching moment arm seems to me to be pretty scary. So much so that I would bail out before I would let a loved one land like that. My 2 cents. See you, Bob. The following reply from Campbell to Doherty was sent at 4:49 p.m. Original message from Campbell, Carlisle C., Jr., to Bob Doherty. Subject, forward, the video you sent. Date, Monday, 27 January, 2003, 15:59:53. Ex-mailer, B Internet Mail Service. Thanks. That's why they need to get all the facts in early on, such as look at the impact damage from the spy telescope. Even then we may not know the real effect of the damage. The Langley Research Center ditching model tests, 20-some years ago, showed that the orbiter was the best ditching shape that they had ever tested of many. But our structures people have said that if we ditch, we would blow such big holes in the lower panels that the orbiter might break up. Anyway, they refuse to even consider water ditching anymore. I still have the test results. Bailout seems best. On the next day, Tuesday, Doherty sent the following to Campbell. Original message from Robert H. Doherty, sent Tuesday, January 28, 2003, 12:39 p.m., to Campbell, Carlisle C., Jr., subject, tile damage. Any more activity today on the tile damage, or are people just relegated to crossing their fingers and hoping for the best? See ya, Bob. Campbell's reply. From Campbell, Carlisle C., Jr., to Robert H. Doherty, subject, re-tile damage, date Tuesday, 28 January 2003, 13:29:58, ex-mailer Internet Mail Service. I have not heard anything new. I'll let you know if I do. CCC. Carlisle Campbell sent the following email to Johnson Space Center engineering managers on January 31st. In order to alleviate concerns regarding the worst-case scenario which could potentially be caused by the debris impact under the orbiter's left wing during launch, EG, Aeroscience and Flight Mechanics Division, conducted some landing simulations on the Ames Vertical Motion Simulator, which tested the ability of the crew and vehicle to survive a condition where two main gear tires are deflated before landing. The results, although limited, showed that this condition is controllable, including the nose slapdown rates. These results may give Mission Operations Directorate a different decision path, should this scenario become a reality. Previous opinions were that bailout was the only answer. In the Mission Evaluation Room, a safety representative from Science Applications International Corporation, SAIC, NASA's contract safety company, made a log entry at the Safety and Quality Assurance Console on January 28th at 12:15 p.m. It was only the second mention of the debris strike in the safety console log during the mission. The first was also minor. Mission Control Center, SAIC, called asking if any safety, reliability, and quality assurance people were involved in the decision to say that the ascent debris hit left wing is safe. SAIC engineer has indeed been involved in the analysis and stated that he concurs with the analysis. Details about the debris hit are found in the Flight Day 12 Mission Evaluation Room Manager and our daily report. End of Section 27. Recording by Maria Kasper. Section 28 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6H. Decision-Making at NASA, Part 8. Missed Opportunity 8. According to a memorandum for the record written by William Reddy, Associate Administrator for Spaceflight, Reddy and Michael Card, from NASA's Safety and Mission Assurance Office, discussed an offer of Department of Defense imagery support for Columbia. This January 29th conversation ended with Reddy telling Card that NASA would accept the offer, but because the mission management team had concluded that this was not a safety of flight issue, the imagery should be gathered only on a low priority, not to interfere basis. Ultimately, no imagery was taken. The board notes that at the January 31st mission management team meeting, there was only a minor mention of the debris strike. Other issues discussed included onboard crew consumables, the status of the leaking water separator, an intercom anomaly, spacehab water flow rates, an update of the status of onboard experiments, end-of-mission weight concerns, landing day weather forecasts, and landing opportunities. The only mention of the debris strike was a brief comment by Bob Page, representing Kennedy Space Center's Launch Integration Office, who stated that the crew's handheld cameras and external tank films would be expedited to Marshall Space Flight Center via the shuttle training aircraft for post-flight foam debris imagery analysis per Linda Ham's request. Summary. Mission Management Decision-Making. Discovery and Initial Analysis of Debris Strike. In the course of examining film and video images of Columbia's ascent, the Intercenter Photo Working Group identified on the day after the launch a large debris strike to the leading edge of Columbia's left wing. Alarmed at seeing so severe a hit so late in the ascent, and at not having a clear view of damage the strike might have caused, Intercenter Photo Working Group members alerted senior program managers by phone and sent a digitized clip of the strike to hundreds of NASA personnel via email. These actions initiated a contingency plan that brought together an interdisciplinary group of experts from NASA, Boeing, and the United Space Alliance to analyze this strike. So concerned were Intercenter Photo Working Group personnel that on the day they discovered the debris strike, they tapped their chair, Bob Page, to see through a request to image the left wing with Department of Defense assets in anticipation of analysts needing these images to better determine potential damage. By the board's count, this would be the first of 3 requests to secure imagery of Columbia on orbit during the 16-day mission. Imagery requests. 1. Flight Day 2. Bob Page, Chair, Intercenter Photo Working Group. 2. Wayne Hale, Shuttle Program Manager for Launch Integration at Kennedy Space Center, in person. 2. Flight Day 6. Bob White, United Space Alliance Manager. 2. Lambert Austin, Head of the Space Shuttle Systems Integration at Johnson Space Center, by phone. 3. Flight Day 6. Rodney Rocha, Co-Chair of Debris Assessment Team, to Paul Schack, Manager Shuttle Engineering Office, by email. Missed Opportunities. 1. Flight Day 4. Rodney Rocha inquires if crew has been asked to inspect for damage. No response. 2. Flight Day 6. Mission Control fails to ask crew member David Brown to downlink video he took of external tank separation, which may have revealed missing bipod foam. 3. Flight Day 6. NASA and National Imagery and Mapping Agency personnel discuss possible request for imagery. No action taken. 4. Flight Day 7. Wayne Hale phones Department of Defense representative, who begins identifying imaging assets, only to be stopped per Linda Ham's orders. 5. Flight Day 7. Mike Card, a NASA headquarters manager from the Safety and Mission Assurance Office, discusses imagery request with Mark Erminger, Johnson Space Center Safety and Mission Assurance. No action taken. 6. Flight Day 7. Mike Card discusses imagery request with Brian O'Connor, Associate Administrator for Safety and Mission Assurance. No action taken. 7. Flight Day 8. Barbara Conti, after discussing imagery request with Rodney Rocha, calls Leroy Kane, the STS-107 Ascent Entry Flight Director. Kane checks with Phil Engelhoff and then delivers a no answer. 8. Flight Day 14. Michael Card, from NASA's Safety and Mission Assurance Office, discusses the imaging request with William Reddy, Associate Administrator for Spaceflight. Reddy directs that imagery should only be gathered on a not-to-interfere basis. None was forthcoming. Upon learning of the debris strike on Flight Day 2, the responsible System Area Manager from United Space Alliance and her NASA counterpart formed a team to analyze the debris strike in accordance with mission rules requiring the careful examination of any out-of-family event. Using film from the Intercenter Photo Working Group, Boeing Systems Integration Analysts prepared a preliminary analysis that afternoon. Initial estimates of debris size and speed, origin of debris, and point of impact would later prove remarkably accurate. As Flight Day 3 and 4 unfolded over the Martin Luther King Jr. holiday weekend, engineers began their analysis. One Boeing analyst used Crater, a mathematical prediction tool, to assess possible damage to the thermal protection system. Analysis predicted tile damage deeper than the actual tile depth and penetration of the reinforced carbon-carbon coating at impact angles above 15 degrees. This suggested the potential for a burn-through during re-entry. Debris assessment team members judged that the actual damage would not be as severe as predicted because of the inherent conservatism in the Crater model and because, in the case of tile, Crater does not take into account the tile's stronger and more impact-resistant densified layer, and in the case of reinforced carbon-carbon, the lower density of foam would preclude penetration at impact angles under 21 degrees. On Flight Day 5, impact assessment results for tile and reinforced carbon-carbon were presented at an informal meeting of the debris assessment team, which was operating without direct shuttle program or mission management leadership. Mission Control's engineering support, the Mission Evaluation Room, provided no direction for the team activities other than to request the team's results by January 24th. As the problem was being worked, shuttle managers did not formally direct the actions of or consult with the debris assessment team leaders about the team's assumptions, uncertainties, progress, or interim results, an unusual circumstance given that NASA managers are normally engaged in analyzing what they view as problems. At this meeting, participants agreed that an image of the area of the wing in question was essential to refine their analysis and reduce the uncertainties in their damage assessment. Each member supported the idea to seek imagery from an outside source. Due in part to a lack of guidance from the mission management team or mission evaluation room managers, the debris assessment team took an unconventional route for this request. Rather than working the request up the normal chain of command through the mission evaluation room and the mission management team for action to mission control, team members nominated Rodney Rocha, the team's co-chair, to pursue the request through the engineering directorate at Johnson Space Center. As a result, even after the accident, the debris assessment team's request was viewed by shuttle program managers as a non-critical engineering desire rather than a critical operational need. When the team learned that the mission management team was not pursuing on-orbit imaging, members were concerned. What debris assessment team members did not realize was that the negative response from the program was not necessarily a direct and final response to their official request. Rather, the no was in part a response to requests for imagery initiated by the Intercenter Photo Working Group at Kennedy on Flight Day 2, in anticipation of analysts' needs that had become by Flight Day 6 an actual engineering request by the debris assessment team, made informally through Bob White to Lambert Austin, and formally through Rodney Rocha's email to Paul Schack. Even after learning that the shuttle program was not going to provide the team with imagery, some members sought information on how to obtain it anyway. Debris assessment team members believed that imaging of potentially damaged areas was necessary even after the January 24th Mission Management Team meeting, where they had reported their results. Why they did not directly approach shuttle program managers and share their concern and uncertainty, and why shuttle program managers claimed to be isolated from the engineers, are points that the board labored to understand. Several reasons for this communications failure relate to NASA's internal culture and the climate established by shuttle program management, which are discussed in more detail in chapters 7 and 8. A flawed analysis. An inexperienced team, using a mathematical tool that was not designed to assess an impact of this estimated size, performed the analysis of the potential effect of the debris impact. Crater was designed for in-family impact events and was intended for day-of-launch analysis of debris impacts. It was not intended for large projectiles like those observed on STS-107. Crater initially predicted possible damage, but the debris assessment team assumed, without theoretical or experimental validation, that because Crater is a conservative tool, that is, it predicts more damage than will actually occur, that the debris would stop at the tile's densified layer, even though their experience did not involve debris strikes as large as STS-107's. Crater-like equations were also used as part of the analysis to assess potential impact damage to the wing leading-edge reinforced carbon-carbon. Again, the tool was used for something other than that for which it was designed. Again, it predicted possible penetration, and again, the debris assessment team used engineering arguments and their experience to discount the results. As a result of a transition of responsibility for crater analysis from Boeing Huntington Beach facility to the Houston-based Boeing office, the team that conducted the crater analyses had been formed fairly recently, and therefore could be considered less experienced when compared with the more senior Huntington Beach analysts. In fact, STS-107 was the first mission for which they were solely responsible for providing analysis with the crater tool. Though post-accident interviews suggested that the training for the Houston Boeing analysts was of high quality and adequate in substance and duration, communications and theoretical understandings of the crater model among the Houston-based team members had not yet developed to the standard of a more senior team. Due in part to contractual arrangements related to this transition, the Houston-based team did not take full advantage of the Huntington Beach engineers' experience. At the January 24th Mission Management Team meeting, at which the No Safety of Flight conclusion was presented, there was little engineering discussion about the assumptions made and how the results would differ if other assumptions were used. Engineering solutions presented to management should have included a quantifiable range of uncertainty and risk analysis. Those types of tools were readily available, routinely used, and would have helped management to understand the risk involved in the decision. Management, in turn, should have demanded such information. The very absence of a clear and open discussion of uncertainties and assumptions in the analysis presented should have caused management to probe further. Shuttle program management's low level of concern. While the debris strike was well outside the activities covered by normal mission flight rules, mission management team members and shuttle program managers did not treat the debris strike as an issue that required operational action by mission control. Program managers, from Ron Ditmore to individual mission management team members, had, over the course of the Space Shuttle program, gradually become inured to external tank foam losses, and on a fundamental level did not believe that foam striking the vehicle posed a critical threat to the orbiter. In particular, shuttle managers exhibited a belief that reinforced carbon-carbon panels are impervious to foam impacts. Even after seeing the video of Columbia's debris impact, learning estimates of the size and location of the strike, and noting that a foam strike with sufficient kinetic energy could cause thermal protection system damage, management's level of concern did not change. The opinions of shuttle program managers and debris and photo analysts on the potential severity of the debris strike diverged early in the mission and continued to diverge as the mission progressed, making it increasingly difficult for the debris assessment team to have their concerns heard by those in a decision-making capacity. In the face of mission managers' low level of concern and the desire to get on with the mission, debris assessment team members had to prove unequivocally that a safety of flight issue existed before shuttle program management would move to obtain images of the left wing. The engineers found themselves in the unusual position of having to prove that a situation was unsafe, a reversal of the usual requirement to prove that a situation is safe. Other factors contributed to mission management's ability to resist the debris assessment team's concerns. A tile expert told managers during frequent consultations that strike damage was only a maintenance-level concern and that on-orbit imaging of potential wing damage was not necessary. Mission management welcomed this opinion and sought no others. This constant reinforcement of managers' pre-existing beliefs added another block to the wall between decision-makers and concerned engineers. Another factor that enabled mission management's detachment from the concerns of their own engineers is rooted in the culture of NASA itself. The board observed an unofficial hierarchy among NASA programs and directorates that hindered the flow of communications. The effects of this unofficial hierarchy are seen in the attitude that members of the debris assessment team held. Part of the reason they chose the institutional route for their imagery request was that without direction from the mission evaluation room or mission management team, they felt more comfortable within their own chain of command, which was outside the shuttle program. Further, when asked by investigators why they were not more vocal about their concerns, debris assessment team members opined that by raising contrary points of view about shuttle mission safety, they would be singled out for possible ridicule by their peers and managers. A lack of clear communication. Communication did not flow effectively up to or down from program managers. As it became clear during the mission that managers were not as concerned as others about the danger of the foam strike, the ability of engineers to challenge those beliefs greatly diminished. Managers' tendency to accept opinions that agree with their own dams the flow of effective communications. After the accident, program managers stated privately and publicly that if engineers had a safety concern, they were obligated to communicate their concern to management. Managers did not seem to understand that as leaders they had a corresponding and perhaps greater obligation to create viable routes for the engineering community to express their views and receive information. This barrier to communications not only blocked the flow of information to managers, but it also prevented the downstream flow of information from managers to engineers, leaving debris assessment team members with no basis for understanding the reasoning behind mission management team decisions. The January 23rd to January 31st phone and email exchanges, primarily between NASA engineers at Langley and Johnson, illustrate another symptom of the cultural fence that impairs open communications between mission managers and working engineers. These exchanges and the reaction to them indicated that during the evaluation of a mission contingency, the mission management team failed to disseminate information to all system and technology experts who could be consulted. Issues raised by two Langley and Johnson engineers led to the development of what-if landing scenarios of the potential outcome if the main landing gear door had sustained damage. This led to behind-the-scenes networking by these engineers to use NASA facilities to make simulation runs of a compromised landing configuration. These engineers, who understood their systems and the related technology, saw the potential for a problem on landing, and ran it down in case the unthinkable occurred, but their concerns never reached the managers on the mission management team that had operational control over Columbia. A lack of effective leadership. The shuttle program, the mission management team, and through it the mission evaluation room, were not actively directing the efforts of the debris assessment team. These management teams were not engaged in scenario selection or discussions of assumptions, and did not actively seek status, inputs, or even preliminary results from the individuals charged with analyzing the debris strike. They did not investigate the value of the imagery, did not intervene to consult the more experienced crater analysts at Boeing's Huntington Beach facility, did not probe the assumptions of the debris assessment team's analysts, and did not consider actions to mitigate the effects of the damage on re-entry. Managers' claims that they didn't hear the engineers' concerns were due in part to their not asking or listening. The failure of safety's role. As will be discussed in Chapter 7, safety personnel were present but passive and did not serve as a channel for the voicing of concerns or dissenting views. Safety representatives attended meetings of the debris assessment team, the mission evaluation room, and mission management team, but were merely party to the analysis process and conclusions instead of an independent source of questions and challenges. Safety contractors in the mission evaluation room were only marginally aware of the debris strike analysis. One contractor did question the debris assessment team safety representative about the analysis and was told that it was adequate. No additional inquiries were made. The highest-ranking safety representative at NASA headquarters deferred to program managers when asked for an opinion on imaging of Columbia. The safety manager he spoke to also failed to follow up. Summary. Management decisions made during Columbia's final flight reflect missed opportunities, blocked or ineffective communications channels, flawed analysis, and ineffective leadership. Perhaps most striking is the fact that management, including shuttle program, mission management team, mission evaluation room, and flight director and mission control, displayed no interest in understanding a problem and its implications. Because managers failed to avail themselves of the wide range of expertise and opinion necessary to achieve the best answer to the debris strike question, was this a safety of flight concern, some Space Shuttle program managers failed to fulfill the implicit contract to do whatever is possible to ensure the safety of the crew. In fact, their management techniques unknowingly created barriers that kept at bay both engineering concerns and dissenting views, and ultimately helped create blind spots that prevented them from seeing the danger the foam strike posed. Because this chapter has focused on key personnel who participated in STS-107 bipod foam debris strike decisions, it is tempting to conclude that replacing them will solve all NASA's problems. However, solving NASA's problems is not quite so easily achieved. People's actions are influenced by the organization in which they work, shaping their choices in directions that even they may not realize. The board explores this organizational context of decision-making more fully in Chapters 7 and 8. Findings. Intercenter Photo Working Group. F6.3-1. The foam strike was first seen by the Intercenter Photo Working Group on the morning of Flight Day 2 during the standard review of launch video and high-speed photography. The strike was larger than any seen in the past, and the group was concerned about possible damage to the orbiter. No conclusive images of the strike existed. One camera that may have provided an additional view was out of focus because of an improperly maintained lens. F6.3-2. The chair of the Intercenter Photo Working Group asked management to begin the process of getting outside imagery to help in damage assessment. This request, the first of 3, began its journey through the management hierarchy on Flight Day 2. F6.3-3. The Intercenter Photo Working Group distributed its first report, including a digitized video clip and initial assessment of the strike, on Flight Day 2. This information was widely disseminated to NASA and contractor engineers, shuttle program managers, and Mission Operations Directorate personnel. F6.3-4. Initial estimates of debris size, speed, and origin were remarkably accurate. Initial information available to managers stated that the debris originated in the left bipod area of the external tank, was quite large, had a high velocity, and struck the underside of the left wing near its leading edge. The report stated that the debris could have hit the reinforced carbon-carbon or tile. The Debris Assessment Team. F6.3-5. A debris assessment team began forming on Flight Day 2 to analyze the impact. Once the debris strike was categorized as out of family by United Space Alliance, contractual obligations led to the team being co-chaired by the cognizant contractor subsystem manager and her NASA counterpart. The team was not designated a Tiger team by the Mission Evaluation Room or Mission Management Team. F6.3-6. Though the team was clearly reporting its plans and final results through the Mission Evaluation Room to the Mission Management Team, no mission manager appeared to own the team's actions. The Mission Management Team, through the Mission Evaluation Room, provided no direction for the team's activities, and shuttle managers did not formally consult the team's leaders about their progress or their interim results. F6.3-7. During an organizational meeting, the team discussed the uncertainty of the data and the value of on-orbit imagery to bound their analysis. In its first official meeting the next day, the team gave its NASA co-chair the action to request imagery of Columbia on orbit. F6.3-8. The team routed its request for imagery through Johnson Space Center's Engineering Directorate rather than through the Mission Evaluation Room to the Mission Management Team to the Flight Dynamics Officer, the channel used during a mission. This routing diluted the urgency of their request. Managers viewed it as a non-critical engineering desire rather than a critical operational need. F6.3-9. Team members never realized that management's decision against seeking imagery was not intended as a direct and final response to their request. F6.3-10. The team's assessment of possible tile damage was performed using an impact simulation that was well outside Crater's test database. The Boeing analyst was inexperienced in the use of Crater and in the interpretation of its results. Engineers with extensive thermal protection system expertise at Huntington Beach were not actively involved in determining if the Crater results were properly interpreted. F6.3-11. Crater initially predicted tile damage deeper than the actual tile depth, but engineers used their judgment to conclude that damage would not penetrate the densified layer of tile. Similarly, reinforced carbon-carbon damage conclusions were based primarily on judgment and experience rather than analysis. F6.3-12. For a variety of reasons, including management failures, communication breakdowns, inadequate imagery, inappropriate use of assessment tools, and flawed engineering judgments, the damage assessments contained substantial uncertainties. F6.3-13. The assumptions and their uncertainties used in the analysis were never presented or discussed in full to either the Mission Evaluation Room or the Mission Management Team. F6.3-14. While engineers and managers knew the foam could have struck reinforced carbon-carbon panels, the briefings on the analysis to the Mission Evaluation Room and Mission Management Team did not address RCC damage, and neither the Mission Evaluation Room nor Mission Management Team managers asked about it. Space Shuttle Program Management F 6.3-15. There were lapses in leadership and communications that made it difficult for engineers to raise concerns or to understand decisions. Management failed to actively engage in the analysis of potential damage caused by the foam strike. F 6.3-16. Mission Management Team meetings occurred infrequently, 5 times during a 16-day mission, not every day as specified in Shuttle Program Management rules. F 6.3-17. Shuttle Program managers entered the mission with the belief, recently reinforced by the STS-113 Flight Readiness Review, that a foam strike is not a safety of flight issue. F 6.3-18. After program managers learned about the foam strike, their belief that it would not be a problem was confirmed early and without analysis by a trusted expert who was readily accessible and spoke from experience. No one in management questioned this conclusion. F 6.3-19. Managers asked who's requesting the photos instead of assessing the merits of the request. Management seemed more concerned about staff following proper channels, even while they were themselves taking informal advice, than they were about the analysis. F 6.3-20. No one in the operational chain of command for STS-107 held a security clearance that would enable them to understand the capabilities and limitations of national imagery resources. F 6.3-21. Managers associated with STS-107 began investigating the implications of the foam strike on the launch schedule and took steps to expedite post-flight analysis. F 6.3-22. Program managers required engineers to prove that the debris strike created safety of flight issues. That is, engineers had to produce evidence that the system was unsafe, rather than prove that it was safe. F 6.3-23. In both the Mission Evaluation Room and Mission Management Team meetings over the Debris Assessment Team's results, the focus was on the bottom line. Was there a safety of flight issue or not? There was little discussion of the analysis, assumptions, issues, or ramifications. Communication. F 6.3-24. Communication did not flow effectively up to or down from program managers. F 6.3-25. 3 independent requests for imagery were initiated. F 6.3-26. Much of program managers' information came through informal channels, which prevented relevant opinion and analysis from reaching decision makers. F 6.3-27. Program managers did not actively communicate with the debris assessment team. Partly as a result of this, the team went through institutional, not mission-related channels with its request for imagery, and confusion surrounded the origin of imagery requests and their subsequent denial. F 6.3-28. Communication was stifled by the shuttle program attempts to find out who had a mandatory requirement for imagery. Safety representatives' role. F 6.3-29. Safety representatives from the appropriate organizations attended meetings of the Debris Assessment Team, Mission Evaluation Room, and Mission Management Team, but they were passive and therefore were not a channel through which to voice concerns or dissenting views. Recommendations. R 6.3-1. Implement an expanded training program in which the mission management team faces potential crew and vehicle safety contingencies beyond launch and ascent. These contingencies should involve potential loss of shuttle or crew, contain numerous uncertainties and unknowns, and require the mission management team to assemble and interact with support organizations across NASA and contractor lines and in various locations. R 6.3-2. Modify the Memorandum of Agreement with the National Imagery and Mapping Agency, NIMA, to make the imaging of each shuttle flight while on orbit a standard requirement. End of Section 28. Recording by Maria Kasper. Section 29 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 6I, Decision-Making at NASA, Part 9. 6.4. Possibility of rescue or repair. To put the decisions made during the flight of STS-107 into perspective, the board asked NASA to determine if there were options for the safe return of the STS-107 crew. In this study, NASA was to assume that the extent of damage to the leading edge of the left wing was determined by national imaging assets or by a spacewalk. NASA was then asked to evaluate the possibility of 1. Rescuing the STS-107 crew by launching Atlantis. Atlantis would be hurried to the pad, launched, rendezvous with Columbia, and take on Columbia's crew for a return. It was assumed that NASA would be willing to expose Atlantis and its crew to the same possibility of external tank bipod foam loss that had damaged Columbia. 2. Repairing the damage to Columbia's wing on orbit. In this repair scenario, astronauts would use onboard materials to rig a temporary fix. Some of Columbia's cargo might be jettisoned, and a different re-entry profile would be flown to lessen the heating on the left wing leading edge. The crew would be prepared to bail out if the wing structure was predicted to fail on landing. In its study of these two options, NASA assumed the following timeline. Following the debris strike discovery on Flight Day 2, mission managers requested imagery by Flight Day 3. That imagery was inconclusive, leading to a decision on Flight Day 4 to perform a spacewalk on Flight Day 5. That spacewalk revealed potentially catastrophic damage. The crew was directed to begin conserving consumables such as oxygen and water, and shuttle managers began around-the-clock processing of Atlantis to prepare it for launch. Shuttle managers pursued both the rescue and the repair options from Flight Day 6 to Flight Day 26, and on that day, February 10th, decided which one to abandon. The NASA team deemed this timeline realistic for several reasons. First, the team determined that a spacewalk to inspect the left wing could be easily accomplished. The team then assessed how long the crew could limit its use of consumables to determine how long Columbia could stay in orbit. The limiting consumable was the lithium hydroxide canisters, which scrub from the cabin atmosphere the carbon dioxide the crew exhales. After consulting with flight surgeons, the team concluded that by modifying crew activity and sleep time, carbon dioxide could be kept to acceptable levels until Flight Day 30, the morning of February 15th. All other consumables would last longer. Oxygen, the next most critical, would require the crew to return on Flight Day 31. Repairing damage on orbit. The repair option, while logistically viable using existing materials on board Columbia, relied on so many uncertainties that NASA rated this option as high risk. To complete a repair, the crew would perform a spacewalk to fill an assumed 6-inch hole in an RCC panel with heavy metal tools, small pieces of titanium, or other metal scavenged from the crew cabin. These heavy metals, which would help protect the wing structure, would be held in place during re-entry by a water-filled bag that had turned into ice in the cold of space. The ice and metal would help restore wing leading-edge geometry, preventing a turbulent airflow over the wing, and therefore keeping heating and burn-through levels low enough for the crew to survive re-entry and bail out before landing. Because the NASA team could not verify that the repairs would survive even modified re-entry, the rescue option had a considerably higher chance of bringing Columbia's crew back alive. Rescuing the STS-107 crew with Atlantis. Accelerating the processing of Atlantis for early launch and rendezvous with Columbia was by far the most complex task in the rescue scenario. On Columbia's Flight Day 4, Atlantis was in the orbiter processing facility at Kennedy Space Center, with its main engines installed, and only 41 days from its scheduled March 1st launch. The solid rocket boosters were already mated with the external tank in the vehicle assembly building. By working 3 around-the-clock shifts 7 days a week, Atlantis could be ready for launch, with no necessary testing skipped, by February 10th. If launch processing and countdown proceeded smoothly, this would provide a 5-day window from February 10th to February 15th, in which Atlantis could rendezvous with Columbia before Columbia's consumables ran out. According to records, the weather on these days allowed a launch. Atlantis would be launched with a crew of 4, a commander, pilot, and 2 astronauts trained for spacewalks. In January, 7 commanders, 7 pilots, and 9 spacewalk-trained astronauts were available. During the rendezvous on Atlantis's first day in orbit, the 2 orbiters would maneuver to face each other with their payload bay doors open. Suited Columbia crew members would then be transferred to Atlantis via spacewalks. Atlantis would return with 4 crew members on the flight deck and 7 in the mid-deck. Mission Control would then configure Columbia for a de-orbit burn that would ditch the orbiter in the Pacific Ocean, or would have the Columbia crew take it to a higher orbit for a possible subsequent repair mission if more thorough repairs could be developed. This rescue was considered challenging but feasible. To succeed, it required problem-free processing for Atlantis and a flawless launch countdown. If program managers had understood the threat that the bipod foam strike posed and were able to unequivocally determine before Flight Day 7 that there was potentially catastrophic damage to the left wing, these repair and rescue plans would most likely have been developed, and the rescue would have been conceivable. For a detailed discussion of the rescue and repair options, see Appendix D13. Findings. F6.4-1. The repair option, while logistically viable using existing materials on board Columbia, relied on so many uncertainties that NASA rated this option high risk. F6.4-2. If program managers were able to unequivocally determine before Flight Day 7 that there was potentially catastrophic damage to the left wing, accelerated processing of Atlantis might have provided a window in which Atlantis could rendezvous with Columbia before Columbia's limited consumables ran out. Recommendation. R6.4-1. For missions to the International Space Station, develop a practicable capability to inspect and effect emergency repairs to the widest possible range of damage to the thermal protection system, including both tile and reinforced carbon-carbon, taking advantage of the additional capabilities available when near to or docked at the International Space Station. For non-station missions, develop a comprehensive, autonomous, independent of station, inspection and repair capability to cover the widest possible range of damage scenarios, accomplish an on-orbit thermal protection system inspection using appropriate assets and capabilities early in all missions. The ultimate objective should be a fully autonomous capability for all missions to address the possibility that an International Space Station mission fails to achieve the correct orbit, fails to dock successfully, or is damaged during or after undocking. End of Section 29. Recording by Maria Kasper.
Section 30 of the Columbia Accident Investigation Board Final Report, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. The Columbia Accident Investigation Board Final Report, Volume 1, by the Columbia Accident Investigation Board. Chapter 7A. The Accident's Organizational Causes, Part 1. Many accident investigations make the same mistake in defining causes. They identify the widget that broke or malfunctioned, then locate the person most closely connected with the technical failure, the engineer who miscalculated an analysis, the operator who missed signals or pulled the wrong switches, the supervisor who failed to listen, or the manager who made bad decisions. When causal chains are limited to technical flaws and individual failures, the ensuing responses aimed at preventing a similar event in the future are equally limited. They aim to fix the technical problem and replace or retrain the individual responsible. Such corrections lead to a misguided and potentially disastrous belief that the underlying problem has been solved. The board did not want to make these errors. A central piece of our expanded cause model involves NASA as an organizational whole. Organizational Cause Statement. The organizational causes of this accident are rooted in the Space Shuttle program's history and culture, including the original compromises that were required to gain approval for the shuttle program, subsequent years of resource constraints, fluctuating priorities, schedule pressures, mischaracterizations of the shuttle as operational rather than developmental, and lack of an agreed national vision. Cultural traits and organizational practices detrimental to safety and reliability were allowed to develop, including reliance on past success as a substitute for sound engineering practices, such as testing to understand why systems were not performing in accordance with requirements/specifications. Organizational barriers which prevented effective communication of critical safety information and stifled professional differences of opinion. Lack of integrated management across program elements, and the evolution of an informal chain of command and decision-making processes that operated outside the organization's rules. Understanding causes. In the board's view, NASA's organizational culture and structure had as much to do with this accident as the external tank foam. Organizational culture refers to the values, norms, beliefs, and practices that govern how an institution functions. At the most basic level, organizational culture defines the assumptions that employees make as they carry out their work. It is a powerful force that can persist through reorganizations and the reassignment of key personnel. Given that today's risks in human spaceflight are as high and the safety margins as razor-thin as they have ever been, there is little room for overconfidence. Yet the attitudes and decision-making of shuttle program managers and engineers during the events leading up to this accident were clearly overconfident and often bureaucratic in nature. They deferred to layered and cumbersome regulations rather than the fundamentals of safety. The shuttle program's safety culture is straining to hold together the vestiges of a once robust systems safety program. As the board investigated the Columbia accident, it expected to find a vigorous safety organization, process, and culture at NASA, bearing little resemblance to what the Rogers Commission identified as the ineffective silent safety system, in which budget cuts resulted in lack of resources, personnel, independence, and authority. NASA's initial briefings to the board on its safety programs espoused a risk-adverse philosophy that empowered any employee to stop an operation at the mere glimmer of a problem. Unfortunately, NASA's views of its safety culture in those briefings did not reflect reality. Shuttle program safety personnel failed to adequately assess anomalies and frequently accepted critical risks without qualitative or quantitative support, even when the tools to provide more comprehensive assessments were available. Similarly, the board expected to find NASA's Safety and Mission Assurance Organization deeply engaged at every level of shuttle management: the Flight Readiness Review, the Mission Management Team, the Debris Assessment Team, the Mission Evaluation Room, and so forth. This was not the case. In briefing after briefing, interview after interview, NASA remained in denial. In the agency's eyes, there were no safety of flight issues and no safety compromises in the long history of debris strikes on the thermal protection system. The silence of program-level safety processes undermined oversight. When they did not speak up, safety personnel could not fulfill their stated mission to provide checks and balances. A pattern of acceptance prevailed throughout the organization that tolerated foam problems without sufficient engineering justification for doing so. This chapter presents an organizational context for understanding the Columbia accident. Section 7.1 outlines a short history of safety at NASA, beginning in the pre-Apollo era, when the agency reputedly had the finest system safety engineering programs in the world. Section 7.2 discusses organizational theory and its importance to the board's investigation, and Section 7.3 examines the practices of 3 organizations that successfully manage high risk. Sections 7.4 and 7.5 look at NASA today and answer the question, how could NASA have missed the foam signal? By highlighting the blind spots that render the shuttle program's risk perspective myopic. The board's conclusion and recommendation are presented in 7.6. See Chapter 10 for a discussion of the differences between industrial safety and mission assurance/quality assurance. 7.1. Organizational Causes – Insights from History. NASA's organizational culture is rooted in history and tradition. From NASA's inception in 1958 to the Challenger accident in 1986, the agency's safety, reliability, and quality assurance (SRQA) activities, although distinct disciplines, were typically treated as one function in the design, development, and operations of NASA's manned spaceflight programs. Contractors and NASA engineers collaborated closely to assure the safety of human spaceflight. Solid engineering practices emphasized defining goals and relating system performance to them, establishing and using decision criteria, developing alternatives, modeling systems for analysis, and managing operations. Although a NASA Office of Reliability and Quality Assurance existed for a short time during the early 1960s, it was funded by the Human Spaceflight Program. By 1963, the office disappeared from the agency's organization charts. For the next few years, the only type of safety program that existed at NASA was a decentralized, loose federation of risk assessment oversight, run by each program's contractors and the project offices at each of the 3 human spaceflight centers. Fallout from Apollo, 1967. In January 1967, months before the scheduled launch of Apollo 1, 3 astronauts died when a fire erupted in a ground test capsule. In response, Congress, seeking to establish an independent safety organization to oversee spaceflight, created the Aerospace Safety Advisory Panel, ASAP. The ASAP was intended to be a senior advisory committee to NASA, reviewing spaceflight safety studies and operations plans, and evaluating systems procedures and management policies that contribute to risk. The panel's main priority was human spaceflight mission. Although 4 of the panel's 9 members can be NASA employees, in recent years few have served as members. While the panel's support staff generally consists of full-time NASA employees, the group technically remains an independent oversight body. Congress simultaneously mandated that NASA create separate safety and reliability offices at the agency's headquarters and at each of its human spaceflight centers and programs. Overall safety oversight became the responsibility of NASA's chief engineer. Although these offices were not totally independent, their funding was linked to the very programs they were supposed to oversee. Their existence allowed NASA to treat safety as a unique function. Until the Challenger accident in 1986, NASA safety remained linked organizationally and financially to the agency's human spaceflight program.
Challenger, 1986. In the aftermath of the Challenger accident, the Rogers Commission issued recommendations intended to remedy what it considered to be basic deficiencies in NASA's safety system. These recommendations centered on an underlying theme: the lack of independent safety oversight at NASA. Without independence, the Commission believed, the slate of safety failures that contributed to the Challenger accident, such as the undue influence of scheduled pressures and the flawed flight readiness process, would not be corrected. NASA should establish an Office of Safety, Reliability, and Quality Assurance to be headed by an associate administrator, reporting directly to the NASA administrator, concluded the Commission. It would have direct authority for safety, reliability, and quality assurance throughout the agency. The office should be assigned the workforce to ensure adequate oversight of its functions and should be independent of other NASA functional and program responsibilities. Emphasis added. In July 1986, NASA Administrator James Fletcher created a Headquarters Office of Safety, Reliability, and Quality Assurance, which was given responsibility for all agency-wide safety-related policy functions. In the process, the position of the chief engineer was abolished. The new office's associate administrator promptly initiated studies on shuttle in-flight anomalies, overtime levels, the lack of spare parts, and landing and crew safety systems, among other issues. Yet NASA's response to the Rogers Commission recommendation did not meet the Commission's intent. The associate administrator did not have direct authority, and safety, reliability, and mission assurance activities across the agency remained dependent on other programs and centers for funding. General Accounting Office Review, 1990. A 1990 review by the U.S. General Accounting Office questioned the effectiveness of NASA's new safety organization in a report titled Space Program Safety: Funding for NASA's Safety Organization Should Be Centralized. The report concluded NASA did not have an independent and effective safety organization. Emphasis added. Although the safety organizational structure may have appeared adequate, in the late 1980s, the space agency had concentrated most of its efforts on creating an independent safety office at NASA headquarters. In contrast, the safety offices at NASA's field centers were not entirely independent because they obtained most of their funds from activities whose safety-related performance they were responsible for overseeing. The General Accounting Office worried that the lack of centralized independent funding may also restrict the flexibility of center safety managers. It also suggested most NASA safety managers believe that centralized SRM and QA, safety, reliability, maintainability, and quality assurance funding would ensure independence. NASA did not institute centralized funding in response to the General Accounting Office report, nor has it since. The problems outlined in 1990 persist to this day. Spaceflight Operations Contract, 1996. The Spaceflight Operations Contract was intended to streamline and modernize NASA's cumbersome contracting practices, thereby freeing the agency to focus on research and development. See Chapter 5. Yet its implementation complicated issues of safety independence. A single contractor would, in principle, provide oversight on production, safety, and mission assurance, as well as cost management, while NASA maintained insight into safety and quality assurance through reviews and metrics. Indeed, the reduction to a single primary contract simplified some aspects of the NASA contractor interface. However, as a result, experienced engineers changed jobs. NASA grew dependent on contractors for technical support, contract monitoring requirements increased, and positions were subsequently staffed by less experienced engineers who were placed in management roles. Collectively, this eroded NASA's in-house engineering and technical capabilities and increased the agency's reliance on the United Space Alliance and its subcontractors to identify, track, and resolve problems. The contract also involved substantial transfers of safety responsibility from the government to the private sector, rollback of tens of thousands of government-mandated inspection points, and vast reductions in NASA's in-house safety-related technical expertise. See Chapter 10. In the aggregate, these mid-1990s transformations rendered NASA's already problematic safety system simultaneously weaker and more complex. The effects of transitioning shuttle operations to the Safety Flight Operations contract were not immediately apparent in the years following implementation. In November 1996, as the contract was being implemented, the Aerospace Safety Advisory Panel published a comprehensive contract review, which concluded that the effort to streamline the Space Shuttle program has not inadvertently created unacceptable flight or ground risks. The Aerospace Safety Advisory Panel's passing grades proved temporary. Shuttle Independent Assessment Team, 1999. Just 3 years later, after a number of close calls, NASA chartered the Shuttle Independent Assessment Team to examine shuttle subsystems and maintenance practices. See Chapter 5. The Shuttle Independent Assessment Team report sounded a stern warning about the quality of NASA's safety and mission assurance efforts and noted that the Space Shuttle program had undergone a massive change in structure and was transitioning to a slimmed-down contractor-run operation. The team produced several pointed conclusions. The shuttle program was inappropriately using previous success as a justification for accepting increased risk. The shuttle program's ability to manage risk was being eroded by the desire to reduce costs. The size and complexity of the shuttle program and NASA contractor relationships demanded better communication practices. NASA's Safety and Mission Assurance Organization was not sufficiently independent, and the workforce has received a conflicting message due to emphasis on achieving cost and staff reductions, and the pressures placed on increasing scheduled flights as a result of the space station. Emphasis added. The Shuttle Independent Assessment Team found failures of communication to flow up from the shop floor and down from supervisors to workers, deficiencies in problem and waiver tracking systems, potential conflicts of interest between program and contractor goals, and a general failure to communicate requirements and changes across organizations. In general, the program's organizational culture was deemed too insular. NASA subsequently formed an integrated action team to develop a plan to address the recommendations from previous program-specific assessments, including the Shuttle Independent Assessment Team, and to formulate improvements. In part, this effort was also a response to program missteps in the drive for efficiency, seen in the faster, better, cheaper NASA of the 1990s. The NASA Integrated Action Team observed, NASA should continue to remove communication barriers and foster an inclusive environment where open communication is the norm. The intent was to establish an initiative where the importance of communication and a culture of trust and openness permeate all facets of the organization. The report indicated that multiple processes to get the messages across the organizational structure would need to be explored and fostered. Emphasis added. The report recommended that NASA solicit expert advice in identifying and removing barriers, providing tools, training, and education, and facilitating communication processes. The Shuttle Independent Assessment Team and NASA Integrated Action Team findings mirror those presented by the Rogers Commission. The same communication problems persisted in the Space Shuttle program at the time of the Columbia accident. Space Shuttle Competitive Source Task Force, 2002. In 2002, a 14-member Space Shuttle Competitive Task Force, supported by the RAND Corporation, examined competitive sourcing options for the shuttle program. In its final report to NASA, the team highlighted several safety-related concerns, which the board shares. Flight and ground hardware and software are obsolete, and safety upgrades and aging infrastructure repairs have been deferred. Budget constraints have impacted personnel and resources required for maintenance and upgrades. International Space Station schedules exert significant pressures on the shuttle program. Certain mechanisms may impede worker anonymity in reporting safety concerns. NASA does not have a truly independent safety function with the authority to halt the progress of a critical mission element. Based on these findings, the task force suggested that an independent safety assurance function should be created that would hold one of the 3 keys in the certification of flight readiness process. NASA and the operating contractor hold the other 2, effectively giving the function the ability to stop any launch. Although, in the board's view, the 3rd key, certification of flight readiness process, is not a perfect solution, independent safety and verification functions are vital to continued shuttle operations. This independent function should possess the authority to shut down the flight preparation processes or intervene post-launch when an anomaly occurs. 7.2. Organizational causes. Insights from theory. To develop a thorough understanding of accident causes and risk, and to better interpret the chain of events that led to the Columbia accident, the board turned to the contemporary social science literature on accidents and risk and sought insight from experts in high reliability, normal accident, and organizational theory. Additionally, the board held a forum, organized by the National Safety Council, to define the essential characteristics of a sound safety program. High reliability theory argues that organizations operating high-risk technologies, if properly designed and managed, can compensate for inevitable human shortcomings and therefore avoid mistakes that under other circumstances would lead to catastrophic failures. Normal accident theory, on the other hand, has a more pessimistic view of the ability of organizations and their members to manage high-risk technology. Normal accident theory holds that organizational and technological complexity contributes to failures. Organizations that aspire to failure-free performance are inevitably doomed to fail because of inherent risks in the technology they operate. Normal accident models also emphasize systems approaches and systems thinking, while the high reliability model works from the bottom up. If each component is highly reliable, then the system will be highly reliable and safe. Though neither high reliability theory nor normal accident theory is entirely appropriate for understanding this accident, insights from each figured prominently in the board's deliberation. Fundamental to each theory is the importance of strong organizational culture and commitment to building successful safety strategies. The board selected certain well-known traits from these models to use as a yardstick to assess the Space Shuttle program, and found them particularly useful in shaping its views on whether NASA's current organization of its human spaceflight program is appropriate for the remaining years of shuttle operation and beyond. Additionally, organizational theory, which encompasses organizational culture, structure, history, and hierarchy, is used to explain the Columbia accident, and ultimately combines with chapters 5 and 6 to produce an expanded explanation of the accident's causes. The board believes the following considerations are critical to understand what went wrong during STS-107. They will become the central motifs of the board's analysis later in this chapter. Commitment to a safety culture. NASA's safety culture has become reactive, complacent, and dominated by unjustified optimism. Over time, slowly and unintentionally, independent checks and balances intended to increase safety have been eroded in favor of detailed processes that produce massive amounts of data and unwarranted consensus, but little effective communication. Organizations that successfully deal with high-risk technologies create and sustain a disciplined safety system capable of identifying, analyzing, and controlling hazards throughout a technology's lifecycle. Ability to operate in both a centralized and decentralized manner. The ability to operate in a centralized manner when appropriate and to operate in a decentralized manner when appropriate is the hallmark of a high-reliability organization. On the operational side, the Space Shuttle program has a highly centralized structure. Launch commit criteria and flight rules govern every imaginable contingency. The Mission Control Center and the Mission Management Team have very capable decentralized processes to solve problems that are not covered by such rules. The process is so highly regarded that it is considered one of the best problem-solving organizations of its type. In these situations, mature processes anchor rules, procedures, and routines to make the shuttle program's matrixed workforce seamless, at least on the surface. Nevertheless, it is evident that the position one occupies in this structure makes a difference. When supporting organizations try to push back against centralized program direction, like the debris assessment team did during STS-107, independent analysis generated by a decentralized decision-making process can be stifled. The debris assessment team, working in an essentially decentralized format, was well-led and had the right expertise to work the problem, but their charter was fuzzy, and the team had little direct connection to the mission management team. This lack of connection to the mission management team and the mission evaluation room is the single most compelling reason why communications were so poor during the debris assessment. In this case, the shuttle program was unable to simultaneously manage both the centralized and decentralized systems. Importance of communication. At every juncture of STS-107, the shuttle program's structure and processes, and therefore the managers in charge, resisted new information. Early in the mission, it became clear that the program was not going to authorize imaging of the orbiter because, in the program's opinion, images were not needed. Overwhelming evidence indicates that program leaders decided the foam strike was merely a maintenance problem long before any analysis had begun. Every manager knew the party line: "We'll wait for the analysis, no safety of flight issue expected." Program leaders spent at least as much time making sure hierarchical rules and processes were followed as they did trying to establish why anyone would want a picture of the orbiter. These attitudes are incompatible with an organization that deals with high-risk technology. Avoiding oversimplification. The Columbia accident is an unfortunate illustration of NASA's strong cultural bias and its optimistic organizational thinking undermined effective decision-making. Over the course of 22 years, foam strikes were normalized to the point where they were simply a maintenance issue, a concern that did not threaten a mission's success. This oversimplification of the threat posed by foam debris rendered the issue a low-level concern in the minds of shuttle managers. Ascent risk, so evident in Challenger, biased leaders to focus on strong signals from the shuttle system main engine and the solid rocket boosters. Foam strikes, by comparison, were a weak and consequently overlooked signal, although they turned out to be no less dangerous. Conditioned by success. Even after it was clear from the launch videos that foam had struck the orbiter in a manner never before seen, Space Shuttle program managers were not unduly alarmed. They could not imagine why anyone would want a photo of something that could be fixed after landing. More importantly, learned attitudes about foam strikes diminished management's wariness of their danger. The shuttle program turned the experience of failure into the memory of success. Managers also failed to develop simple contingency plans for a re-entry emergency. They were convinced, without study, that nothing could be done about such an emergency. The intellectual curiosity and skepticism that a solid safety culture requires was almost entirely absent. Shuttle managers did not embrace safety-conscious attitudes. Instead, their attitudes were shaped and reinforced by an organization that, in this instance, was incapable of stepping back and gauging its biases. Bureaucracy and process trumped thoroughness and reason. Significance of redundancy. The human spaceflight program has compromised the many redundant processes, checks, and balances that should identify and correct small errors. Redundant systems, essential to every high-risk enterprise, have fallen victim to bureaucratic efficiency. Years of workforce reductions and outsourcing have culled from NASA's workforce the layers of experience and hands-on systems knowledge that once provided the capacity for safety oversight. Safety and mission assurance personnel have been eliminated. Careers in safety have lost organizational prestige, and the program now decides on its own how much safety and engineering oversight it needs. Aiming to align inspection regime with the International Organization for Standardization 9000/9001 protocol, commonly used in industrial environments very different than the shuttle program. The human spaceflight program shifted from a comprehensive oversight inspection process to a more limited insight process, cutting mandatory inspection points by more than half and leaving even fewer workers to make second or third shuttle systems checks. See Chapter 10. Implications for the shuttle program organization. The board's investigation into the Columbia accident revealed two major causes with which NASA has to contend. One technical, the other organizational. As mentioned earlier, the board studied the two dominant theories on complex organizations and accidents involving high-risk technologies. These schools of thought were influential in shaping the board's organizational recommendations, primarily because each takes a different approach to understanding accidents and risk. The board determined that high reliability theory is extremely useful in describing the culture that should exist in the human spaceflight organization. NASA and the Space Shuttle program must be committed to a strong safety culture, a view that serious accidents can be prevented, a willingness to learn from mistakes, from technology, and from others, and a realistic training program that empowers employees to know when to decentralize or centralize problem solving. The shuttle program cannot afford the mindset that accidents are inevitable because it may lead to unnecessarily accepting known and preventable risks. The board believes normal accident theory has a key role in human spaceflight as well. Complex organizations need specific mechanisms to maintain their commitment to safety and assist their understanding of how complex interactions can make organizations accident-prone. Organizations cannot put blind faith into redundant warning systems because they inherently create more complexity, and this complexity, in turn, often produces unintended system interactions that can lead to failure. The human spaceflight program must realize that additional protective layers are not always the best choice. The program must also remain sensitive to the fact that despite its best intentions, managers, engineers, safety professionals, and other employees can, when confronted with extraordinary demands, act in counterproductive ways. The challenges to failure-free performance highlighted by these two theoretical approaches will always be present in an organization that aims to send humans into space. What can the program do about these difficulties? The board considered three alternatives. First, the board could recommend that NASA follow traditional paths to improving safety by making changes to policy, procedures, and processes. These initiatives could improve organizational culture. The analysis provided by experts and the literature leads the board to conclude that although reforming management practices has certain merits, it also has critical limitations. Second, the board could recommend that the shuttle is simply too risky and should be grounded. As will be discussed in Chapter 9, the board is committed to continuing human space exploration and believes the shuttle program can and should continue to operate. Finally, the board could recommend a significant change to the organizational structure that controls the Space Shuttle program's technology. As will be discussed at length in this chapter's conclusion, the board believes this option has the best chance to successfully manage the complexities and risks of human spaceflight. End of Part 1 of Chapter 7.